just as a last call, if you want more breakfast, more coffee, they close the breakfast off at 8:40. So if you want more food, go get it now.
Those got the one which we
Yeah, the clicker is right by the table.
see it.
All right, good morning, everyone. Welcome to day 2 of the QSC Summer School. My name is Zach Martin. I'm a third-year PhD student studying solid-state single photon emitters under the guidance of Professor Sasha Boltzmann and Vlad Shalaev at Purdue University. Louder? Okay, sorry. With that said, it is my pleasure today is the IBM Quantum Day of Learning. So it is my pleasure to hand off the mic to Olivia Lanez of IBM Quantum.
Thank you, Zach. Hi, everybody. My name is Olivia. I'm here with Nick Braun, also from IBM Quantum. We'll be around all day and part of tomorrow as well. We're super excited to be here and very happy to sponsor this summer school. IBM loves funding any sort of workforce or educational initiative in the quantum space. We think it's super important. It's definitely one of our top priorities. So I'll be talking a little bit later on about workforce development, and if you want to join the quantum information workforce, how you might go about doing that. Nick is going to talk about quantum simulation a little bit after that and do some live coding demonstrations. So I think it'll be a really interesting day, and we're super happy to be here. I've never been to Purdue before, so it's also been a good time already. Yeah, that's all I had to say. I don't know who I'd pass it off to at this point, but super happy to be here. We'll see you around.
All right, thank you, Olivia. So our first speaker today is Professor Sabra Kai. Am I pronouncing that correctly? Kais? Okay, thank you. So I have your biography here. I'll pull it up. So Sabra Kais is a distinguished professor of chemistry and with a full professor courtesy appointments in physics, computer science, and electrical and computer engineering at Purdue University. He was the director of the NSF-funded Center for Innovation on Quantum Information for Quantum Chemistry, and served as an external research professor at Santa Fe Institute. He is known for his pioneering work on developing quantum computing algorithms and implementations for quantum chemistry problems. Without further ado, Professor Kais.
Thank you, Zach. Good morning, everyone, and thank you for coming early to listen to my talk. I would like to start by thanking the organizer, Sasha and David and the rest of the committee for organizing this exciting workshop. Yesterday, we heard 3 exciting talks by Young, Chris, and Vlad focusing on materials. And today, I'm going to shift to quantum algorithms and telling you what we are doing using quantum machine learning for quantum simulations. So I was thinking how to start this talk, and I thought maybe with one slide, trying to summarize my talk, and then go through the details. So if you look at the title of my talk, we said quantum machine learning for complex many-body systems. And I have to explain what is complex many-body systems, what is quantum machine learning, what is the task that I'm going to talk about, and then go through the details. So when we talk about many-body systems, here we're describing microscopic system. I don't have a laser pointer here, but you can see we talk about microscopic systems made of many interacting particles and focusing in chemistry, material science, and atomic and molecular physics. So we talk about electrons and protons. And since we are talking about this microscopic system, then quantum mechanics has to be used to provide accurate description of these systems. So this is where quantum comes in. We have electrons, protons, we have quantum mechanics. And then when we say quantum simulation, what exactly do we mean by quantum simulations? We are solving the Schrödinger equation. Just to here mention at the beginning, I'm going to talk about non-relativistic quantum mechanics. So we are solving the Schrödinger equation. H psi equals E psi. H is describing the system. This is the Hamiltonian. And we are after getting the state wave function psi and the spectrum E. So this is the time independent Schrödinger equation on the right-hand side. You take the energy as an operator I h bar ddt, and then you talk about the dynamics, solving the time-dependent Schrödinger equation. And then if you have a system interacting with environment, we talk about simulating the Liouville equation or von Neumann equation, where you look how the density matrix of the system, rho of t, changing as a function of time. And here also, I would like just to mention this is the density matrix for the whole system. If you said, okay, I'm interested in the subsystem and trace out the degrees of freedom for the environment, then we talk about how the density matrix of the subsystem evolve under the influence of the environment. And this is called the quantum master equation. So you will see I'm going to talk about Schrödinger equation, the time-dependent Schrödinger equation, and the quantum master equation. How do we solve it on a quantum computer? And again, I'm going to mention what is the main problem because we have Hilbert space, and this is very complex space. Now, what about machine learning or quantum machine learning? So what is machine learning? You need first a machine. And you can think about our brain doing the computation. So our brain could be the machine or the classical computer as a machine. And you have an input. Here you have an input, which is of interest, big data. And then you have the machine with algorithm that learning the data and give you an output, which is the task of these calculations. And you can ask, where does quantum come in? You see all the three steps from the initial big data to the learning process to the task. You can add the word quantum. So quantum machine learning, everything you see here is a classical machine learning. I will add the quantum. So we have quantum data. We have quantum algorithms to learn how to process and find correlations between the data, and then the task. So now this is like a summary of what I'm going to talk about, quantum machine learning for solving dynamical and electronic structure problems on a quantum device. So what is the task in my lecture? Because here in machine learning, you have the task. So what is the task? The task is to find the physical states. So the task is to find the wave function. Remember, machine learning is for you see maybe I'll go to the next one. So here, like you said, okay, maybe before I go there, you said, okay, quantum mechanics, we have it for 100 years. What I'm bringing, what is the new? Machine learning, 70 years or more. So what is the new in this field? The new is the quantum device. So we're going to add the quantum as a new tool that is going to help us in merging the two fields of machine learning and quantum simulations. And hopefully we can see new results that we could not obtain with the classical machine learning. So all of us have seen the success of machine learning in many fields of science and engineering. And it goes from solar farm optimization, drug discovery, finance, grid stability. And here you have self-driving cars. And if you are here visiting the campus, you see all these machines that deliver meals. And again, the main idea here is machine learning. I would like to zoom on a little bit on the focus of the lecture, which is chemistry and physics. And again, classical machine learning with the three topics, supervised learning, if you have labeled data, or unsupervised, or reinforcement learning has been used in simulation for now more than 10 years with a lot of success in simulating the many-body system. But again, it's going from a classification of phases in matter all the way down to describing the rate of chemical reactions. So now we add quantum to this. So what is quantum machine learning? I'm going to merge quantum algorithms with classical machine learning. And remember, like in the literature, people use quantum machine learning to talk about using classical machine learning to learn about the quantum systems. And this is not, I mean, still they use this one in the literature, quantum machine learning, but again, it's a classical machine learning to study quantum systems. Here we talk about quantum algorithms with classical machine learning, and we call this quantum machine learning. So when we say the quantum, what did we add to this equation? We add, as we heard yesterday, we did three things that we have to add to this computation. First, the idea of superposition, where we talk about the qubit instead of bits. The second idea is the interference. And since we talk about macroscopic systems, they have waves, so they interfere. And yesterday, Chris talked about how interference is used in Shor algorithm to find the factoring of a large number. And this is really the tricky part in the quantum algorithm. How do you design your quantum algorithm in a way to take advantage of the interference phenomenon? And again, we're going to use these tricks in quantum algorithms for machine learning. And the third thing, of course, the entanglement, which is a strong correlation with no classical analog. And this is not just a theoretical concept. We have seen this in action, and Vlad talked about it in communication. So we're going to add those three elements: superposition, interference, entanglement, to the quantum algorithms, and combine it with the classical machine learning to solve simulating the many-body problem. So if you look at the literature, what people have done in this field, they took all the classical machine learning, I mean, most of them, and they tried to see how do you quantize it? How do you add the quantum aspect to it? And people, you can see, start having review articles and books about all the classical machine learning algorithms that we used and what kind of speed up we expect from these quantum algorithms. And here I would like to mention, this is for the algorithm. You have 3 steps: the initial data to map, then the algorithm, then the output. This doesn't mean from end to end you have a speed up. This is for only the algorithm part. You could see speed up, but there is no speed up from end to end because you still have data to be mapped and you have output to be measured and so on. So this is just the focus on the algorithm. Now for this field, this is really a nice review article by, you see, Jacob Mayanti, Nathan Webby, and Seth Lloyd. They put together a review article. They took all the classical machine learning algorithms, and they describe what is the quantization. How do you add the quantum element to these algorithms? For example, in classical machine learning, we have the principal component analysis, which compress the data. And there's a quantum version of this, quantum, and you can see they add a quantum to each one. Support vector machine is finding the hyperplane to classify data, and then you add the quantum. So in this review article, they describe in details how do you quantize a classical machine learning. So now what is the goal of today? I'm going to focus on quantum machine learning for a quantum simulation. And again, here is not only the algorithm, we'd like to implement it on quantum devices. So this is what we add to this algorithm. When we say implementing, we have to come up with a quantum circuit that implemented on a quantum device. And I'm going to talk about electronic structure, which is our main field in chemistry, and I still believe that this is the heart of chemistry. Without electronic structure calculation, you cannot do anything in chemistry because this is give you the forces that you need for dynamics. And you can ask, we have electronic structure for over 80 years with so many success and method that we use for thousands of atoms, starting from ab initio, semi-empirical, where you parameterize the system with experimental results. You have density function theory, which is the most popular method of doing simulations with a great success. And then I grouped all the rest of the method under non-conventional, like Lie algebraic method, renormalization, DMRG, and so on. And you can see the list. We have so many Nobel laureates in the field, starting with Jean Babel, who developed what we call the wave function method. And then you have Walter Kohn, density functional theory, and the 3 Nobel laureates, Martin Karplus, Michael Levitt, and Ariel Warshaw. They also did on dynamics, but they use electronic structure to get the forces. So all of these Nobel laureates in the field, and you ask, okay, so what is the point of introducing a new tool? And this is where the chemical accuracy comes in. So we advance the method, and experimentalists advance their spectroscopic method, and they can measure these differences in states to within chemical accuracy, which is 1 kilocalorie per mole or 0.03 electron volts. To keep up with these chemical accuracy is extremely important in describing heat of reactions, binding energies, activation, and so on in chemistry. So it's very important to get chemical accuracy. To get chemical accuracy, the method that we are familiar with, which give you this chemical accuracy in a systematic way. When I say in a systematic way, in a variational principle. It's like you do variational, you increase the size. This is the CI, the configuration interaction method. You increase the number of configurations in a systematic way to optimize your energy. So this is a variational calculations, and this is the only method to get chemical accuracy or guaranteed to get chemical accuracy, but the cost is exponential with the system size. And now the hope in this field, maybe this new tool can give us advantage over the other methods. Still, we don't have any system that we see an advantage. So let's make it clear at this point, all the calculation we have done is really proof of concept. So when we solve a Schrödinger equation, first of all, the first step, you have to map it to the qubit space. Now, this is a routine way of doing it in many review articles. And you can see, you start, for example, one way is do second quantization, use Jordan-Wigner or Brevikov. So this is a routine way of transferring the Schrödinger equation from the second order differential equation to the qubit space. And then we use the basis of the Fock space, which means occupied, not occupied. And then your favorite quantum algorithm to find the eigenvectors and eigenvalues. And we early started with the phase estimation. And then recently we can see the hybrid classical and quantum algorithms to solve these equations. And at the end, you have to do a measurement to get the results. So I said routine calculation because if you look at all the major companies in this field, they have open source packages that transfer you any Schrödinger equation to qubit space. So this is no longer now, it used to be like 10, 15 years ago, an important topic, how do you transfer the equation? Now it's like you just put whatever the system, you use these open sources and they transfer the equation. So this is not really anymore a problem, and you can see the list of open sources here that can do this for you. Now, okay, summary, what we did so far, what did we achieve in this field? All we have achieved is really proof of concepts for very, very small systems within 2 to 12 qubits or 10 to 12 electrons. This is what we have so far in this field. And you can see we have this molecular system, the small system from H2 all the way down to 12 hydrogen atoms done on all the platforms. And this is what's exciting because you have the theory and you have the implementation. So this is what we said, the proof of concept that all these calculations we have done using D-Wave, NMR, optical quantum computer, trapped ions, superconducting, and so on. So we know in principle, this algorithm works for electronic structure and solving the Schrödinger equation. And you can ask, where we are standing in this field? I think we are, we heard just yesterday, we are just at the beginning of this field. And I like to just mention the early work in the 50s, where after we have the computer, so people start thinking how to solve numerically the Schrödinger equation. And if you go to the literature, they were solving the same problem. H2, lithium hydride, water, very small systems on a classical computer. So I think now you can see we are at this era where you can see these are the IBM results were published back in 2017 with 7 qubits. So we're still at early stage and there is many things to be improved in this field and get more accurate results. Now, you see the title of this, what is next? Now, what is next for the people doing the hardware? It's clear you need to improve the machine by having more qubits. We talk about the quantum gates and the error in the quantum gates, single and double quantum gates, how to reduce the error, the shallow quantum circuit, how many quantum gates you need to perform an algorithm, the connectivity of the qubits, and of course, at the end, we are looking for a fault-tolerant quantum computer with quantum error corrections. And again, I would like here to mention that, of course, we are waiting for the experimentalists to improve the machine, but at the same time, maybe also we have to start thinking about algorithms. Can we design a better algorithm and get results while we're waiting for the experimentalists to improve the hardware. So if you look at the community, what are the directions? You can see we have start seeing a lot of work on hybrid, classical and quantum. So whatever hard on classical computer, you try to push it to the quantum device, and these hybrid algorithms, you can see people start seeing the application for quantum simulations. Another one is adiabatic quantum algorithms, which means I start with a system that I know the answer and then slowly evolve the system to the target Hamiltonian. The third one is the quantum machine learning algorithms, and this is the focus of my talk. You have also algorithms with the qubit space, and maybe Andy will talk about it. How do you go from qubit to qubit space, and do we have advantage of a qubit with multi-level system instead of two-level system? And then also we have seen a lot of exciting results with the analog quantum simulator. So let me go through the challenge. What is the challenge in this field? As I mentioned, the challenge is the dimension of Hilbert space is exponential. And we'd like to figure out how to go from this exponential scaling to polynomial scaling. When we said efficient algorithm, we mean that the algorithm is scaled polynomially with the size of the system. What we have seen before, to get accurate results, you have exponential scaling. So let's say I would like to do simulation for like describing a magnetic system with just 80 spins. So the spin has 2 degrees of freedom up and down, 2 to the 80 is Avogadro number of configurations. Do you really need Avogadro number of configurations to describe the system? No, I mean, we know that from calculation, we don't need Avogadro number. Another example, which is really exciting, if you look at the average size of a human protein with 300 amino acids, and of course, we have 20 different amino acids. So take 20 to the 300, look at this number, it's 10 to the 390 possible configurations of these proteins. I was looking at the literature, this is not my field, but I look, it said the number of different existing proteins in all living organisms is 10 to the 7. So how do you go from this astronomical number, 10 to the 390 to 10 to the 7? So the summary here is that the physical states usually only access a tiny corner of the entire complex Hilbert space. And the challenge is, how do we discover these states in an efficient way, which means in a polynomial? So this is our really task. How do I go from exponential scaling to polynomial scaling? And we know these guys sitting here in the corner are not occupying Avogadro number of configurations. So before going that, we say, okay, what are these challenging problems that we're aiming at? Of course, we are not there yet. We see all the results are for small system. But if you look at the field of chemistry or biochemistry or many-body system, all the problems are complex. And if you start with complex biological system, trying to understand the structure and the transport in this system, or catalysis, drug discovery, material design, optical global optimization, like in protein folding, all the problem you see in chemistry, you have so many degrees of freedom. And it's all very complex. And the way we do the calculation, we try to simplify, do approximation over and over until we can do something with the existing methods. So we have plenty of exciting systems. I'm talking about here chemistry and biochemistry. And what we are doing in the field of theoretical chemistry is we are really focusing on 2 things, structure and dynamics. Structure and dynamics. This is the only things we need for this field to study, understand the structure. From the structure, we get the forces, and the forces will allow us to do dynamics. So in our field, we are taking a different approach to this, finding this tiny space in Hilbert space. We have the analytical approach based on complexity theory, the quantum machine learning, and recently we start looking at tensor network. So the focus of my talk will be only on the machine learning and specifically the Boltzmann machine. But I would like to mention the first one. We have exciting results, and at the end, we'd like to combine the 3 together. And this work done with my postdoc, Andrew, who that we start looking at this, how do we go systematically to this efficient polynomial states? And you can see here, Ethan is here also. He's joining the group from computer science. And we're trying to analyze the complexity of these states. And the main question is, what quantum states can be created with the polynomial steps? And how do you check these states? So our approach is, I will not go through the details, but the idea of going from very complex Hilbert space to this tiny space. So we created an efficient polynomial state with maximum entanglement. And we have this process, how to do it. We start with a product of zero state, and we analyze it by unitary U on the kth here. I don't have the laser, but we apply unitary and then follow by a C0 gate with the sequence K and K plus 1. And we created these states with maximum complexity, but still efficient with the polynomial steps. And what we're trying to do in this field, trying to find what is the common features among these coefficients, which allow probability characterization of quantum states. So we'd like to analyze these coefficients and understand the structure. Is there any structure behind these polynomial states? And if we figure out what is the structure, then the next question, how do we use these efficient polynomial states? So this is an ongoing research in the group by the postdoc, Andrew Hu and Ian here. And now back to the main topic, which is quantum machine learning. So what I'm going to do next is to introduce the machine that I'm going to use, which is the restricted Boltzmann machine. So I'll start telling you what is the restricted Boltzmann machine, why this is the machine we are using for electronic structure, what problems can we do with it, and how do we implement it on a quantum device. And then go through the details until what we're going to do in the future with this device. And I will give one exciting application, which is how do you use this method to talk about the quantum phase transitions. So this is the outline of the talk, and you see the application will start with a small molecular system and move to two-dimensional materials. So again, just to keep you focused, the goal is really to use this Boltzmann machine for electronic structure calculations. So you start, okay, what is this Boltzmann machine? So Boltzmann machine, you see from the name, it relies on the physics of the Boltzmann statistics. And why we're doing that? Because at the end of the day, I would like to understand how the machine is doing the calculations. So it's extremely important, and you see later that you rely on a physical model that you know the details of this one, so it will help you to understand how the machine is learning the process. So what is Boltzmann distribution? We all teach statistical mechanics, and you define an energy function, and the Boltzmann distribution is exponential with minus E. The energy divided by normalization, and normalization is the partition function of the system. So what is the energy function we are using? The energy function is the Ising Hamiltonian. So you can see up there is the Ising Hamiltonian. We have, in this machine, we have two layers, the visible down here. And the dimension of this will be how many nodes you put in the visible layer, and then the second layer is the hidden layer. And you can see the parameters B and C are you can think about the Ising Hamiltonian as the tuning fields or the biases in this model. So we have fields on the visible, the fields on the hidden, and then the connection matrix omega ij, which connect the two layers. So the connection matrix is omega ij, and you see restricted, the only possible interaction between the two layers, hidden and visible. There is no interaction between nodes within each layer. And this is why it's called restricted and not Boltzmann machine. And you can see we're going to map the system into this energy by finding what are the optimal parameters in the Ising Hamiltonian, which mean the coupling omega ij, the B sub j and C sub ji, that give you the distribution. So here is the joint distribution between the visible and hidden. You have to get e to the minus e. And then we get the marginal distribution for the visible, b sub v, and you sub all the hidden variables. So you trace out the hidden variables and you focus on the visible. And once you focus on the visible, you get probability distribution. And now we're getting the wave function. I mean, at the end, the task is to get the wave function. So the wave function will be obtained from the square root of the probability distribution. This is the way we're going to get our wave function. So this is the restricted Boltzmann machine. When we start looking at this one, we were really inspired by a paper appeared in Science in 2017 by Matthias Treuer and his students, where they show this Boltzmann machine can obtain the ground state of both the Ising and the Heisenberg in 1 and 2 dimensions, with excellent results comparing with the quantum Monte Carlo. Okay, now when we looked at this one, I thought this is really a very exciting field of research to combine the knowledge from Boltzmann statistics that we're all familiar with. We have the neural network and the quantum computing. So the question, how do we merge the three fields? I mean, all of these fields are really very successful in their own application. And the question, how do you put all those three together and try to find the task, which is the wave function of many-body systems? And for this one, I was inspired by lectures by our colleague here, Sabiru Data. He put together beautiful lectures on this topic where he went through the details with the physics of each subfield. In these lectures, I mean, you can see them in NanoHub, that he talked about the physics behind the Boltzmann machine, the physics of Boltzmann, and the physics behind the quantum. And what we have done, we combined the three, and then I will show you later, we designed the quantum circuit that will do this job, and we implemented on a quantum computer. Of course, a classical Boltzmann machine has a long history used in early work by Paul Lansky, and this was 87, and Hinton in 2006, and maybe before that. And they talk about how to use restricted Boltzmann machine, the classical machine learning in simulations. So why restricted Boltzmann machine? And I would like to mention here two properties of this machine. The first one, and you can find the argument in this perspective in Nature Physics from 2019. And I would read here the most important statement in this one, that the restricted Boltzmann machine is known to be universal approximator. So you can approximate any given function with n variables by the restricted Boltzmann machine. And they rely on an earlier mathematical theorem was put back in 2008 in neural computation. They took this theorem, and there is a mathematical proof for this theorem that the restricted Boltzmann machine can simulate any function by increasing the number of hidden layers. So we have a very powerful machine. I mean, you said, okay, I mean, it's not for a certain class of problem. This is for any function that you would like to approximate. This restricted Boltzmann machine can do the job, and there is this mathematical theorem. The second one about entanglement and efficiency. And this was back in 2017 Physical Review X by the group of Das Sarma, that they talk about entanglement and how do you bound the entanglement in the restricted Boltzmann machine. And they talk about two conclusions at the end of this paper, that they prove that the entanglement of all short-range restricted Boltzmann machine states satisfy the area law. And this is extremely important because we use this, that the entanglement is bounded by the area law in all the DMRG calculations in one-dimensional system, that if you break it into two, then the entanglement is bounded by the area law. And they show that this is also true for restricted Boltzmann machine. And they add one more thing, which is that the long-range restricted Boltzmann machine can be used to extract or construct states with a massive entanglement by bounding with the volume instead of the area law. So we have a very powerful machine that can take into account both the short range and the long range. And why we need the long range of entanglement? Because I think once we go for like a emerging phenomena, for example, in spin liquid, where entanglement or long range entanglement is extremely important, you need a machine that in principle can simulate such a system. And this is, they discuss these in this physical review X, and show that this is a very powerful machine when we come to scaling. So to summarize here, we have a restricted Boltzmann machine that can simulate any function, and it's efficient. So now let's go to the simulation. What simulation means? Like suppose I have a system, you have molecular system, your favorite molecular system, or materials, or spin system. What do? First, you choose a basis function. You take your basis function and you turn your Hamiltonian operator into a matrix of d dimension. This is what we do in quantum chemistry. Once you have a d-dimensional matrix, you ask, okay, what are the eigenvectors and eigenvalues of this matrix? I mean, this is very simple structure that we do in our calculations. You have a large matrix, and what are the eigenvalues and eigenvectors? So before continuing, I would like now just to mention that the results I'm going to mention, if you missed any of the details, all the results I'm going to mention based on our recent 3 papers. The first one, we put it back in 2018 in Nature Communication. We show how the restricted Boltzmann machine can do calculation for small molecular systems. And again, when I say we show that both the theory and implementation on the IBM devices. And then the second paper, which we published in the Journal of Chemical Information and Modeling, was how to take this restricted Boltzmann machine with periodic boundary condition to get the electronic structure of materials. And the focus of this paper was only on the ground state, the valence band. And then we developed the theory. And here is the main work by the postdoc Manus. And I'll mention his work later, that he was able to show that with the restricted Boltzmann machine, we are not only going to get the ground state, we can get also excited states. And this is important because we would like to get not only the valence band, we would like to get also the conduction band and talk about the gap and how do you engineer the gap for 2-dimensional materials. So I'll show how this one also can go for excited states, not only the ground states. So what to expect from this talk? Before I continue, just if we run out of time. So first of all, we construct a 3-layer restricted Boltzmann machine. The 2-layer visible and hidden, and we add another layer which will give us the phase of the wave function. Remember, the distribution from Boltzmann will give us the amplitude. You will ask, okay, the wave function has a phase. How do you get the phase? So we add another layer which we train the system to get the correct phase for the wave function. And then we implemented on a quantum device by designing a quantum circuit. So when I said designing a quantum circuit, we say, okay, what is the circuit width, depth, and the parameter count on this restricted Boltzmann machine? How do you optimize these parameters, and how do you implement it on a quantum device? And then you said, okay, I mean, this is a probabilistic machine. You have to add it many times. And then you can ask, what is the successful rate? And we all here show that there is a lower bound for this machine. And I will show like what is the lower bound for successful sampling. And then we apply it for 2-dimensional materials, getting the band structure for these materials. And again, we implemented all the results on a quantum simulator. In this case, the Qiskit was available for us, and the real IBM machine, and show the difference between the simulator and the real machine calculations. So let me go through this one and introduce what is the quantum circuit used to simulate this process. So first of all, here is the machine. You have N visible nodes, you have M hidden, And now when I said node, each node takes values 1 or -1. I'm going to replace these nodes with the qubit at the end of the process. And from this one, if you sample the distribution according to the energy which comes from the Ising Hamiltonian, you get the probability distribution over the visible. And then will give us the square root of this one will give us the amplitude. And then the phase, we introduce a function, which is a complex function, which allow us to obtain the phase of the wave function. And this is the function that will going to give us the phase. So at the end of this process, we have the distribution from Boltzmann, give us the amplitude, and S is the phase out of this complex function. And of course, we sampling over all possible configuration in the visible, all the sigmas from 1 to N, from 1 to N. So this is the idea. And now we said, okay, here is the algorithm. You start with, you initialize these parameters in the restricted Boltzmann machine at random. Then you build the quantum circuit, which we're going to sample the Boltzmann distribution. You get the phase, and then you get the wave function. Again, the focus is getting the wave function. So again, here, let me just emphasize what is the quantum part of this is the quantum circuit that sample the Boltzmann distribution. And here you can say we are sampling the Gibbs distribution of the system. So we have a quantum circuit that do Gibbs distribution for us. So we're going to map the nodes into qubits, in the visible, in the hidden, and then we're going to introduce and sell a qubit that's going to couple the visible and the hidden layer, because there is a coupling between the two, and get the distribution. So here's the quantum circuit, and I'm giving this example of two nodes on the visible. We have two nodes, and these are our qubits now, in the hidden, and then the ancilla qubit coupling those qubits. So you see, I start initializing the system in the 0 state. We do rotation, and now the angle theta in the rotation is related to the parameter in the Ising Hamiltonian in the restricted Boltzmann machine. So you see the A give us the parameters on the visible layer. The B are the parameters on the hidden. So you rotate your system, or your quantum circuit works with the parameters that you initialize from the Boltzmann distribution. And then you have the coupling, the matrix which couples the hidden and the visible, omega ij. And to get the coupling between the two layers, we use control rotation. Control rotation, and the rotation angles in this control rotation related to the matrix wij. So now in this quantum circuit, we know how to introduce our parameters, put it in the quantum circuit, run it in the quantum computer, and then start the process. So if I start here with A, what I did the first, like if I initialize the system and rotate, what we have done here is superposition of all possible configurations from the visible and the hidden is the first step, where you see here A. Now we start coupling the visible and the hidden through the rotational through the connection matrix omega ij by control rotation. Control rotation. I have 4: 0, 0, 0, 1, 1, 0, and 1, 1. We have 4 couplings. And you can see the first one will give superposition of all possible states, hidden and visible. And then if we can continue, we do control rotation. And now to implement control rotation, you have to decompose it into this sequence of X and rotational gate. So we have X, 6X rotation, and 6X rotation, and then 4 rotational state, depends on the parameter of the system. So after you're doing this control rotation, after the superposition, you end up with the distribution that you need, and you look at the ancilla, and we show that if the ancilla is 1, then you take this as a successful sampling, and you continue. So this is a restricted Boltzmann machine, and this is the quantum circuit that we design for this process. And just to summarize, we start with 2 layers. We add 1 single layer for the phase. And then once we have boundary condition, we need this complex layer, which allow us to put a periodic boundary condition to go to materials in 2 dimensions. Now, we'll not go through the details, but we show mathematically that the lower bound for successful sampling is restricted by this K, which is around 10 to the minus 4 as parameter. And again, all the details of this in the appendices in our papers, if you are interested to see the mathematical derivation of this lower bound. So let's talk about the requirement in the machine so we can implement it. So again, we have 2 qubits in the N, 2 qubits in the hidden, and we have 4 ancilla qubits. And again, the number of gates, we have 4 single quantum rotational gates, 4 in the control, and then once you break it into X and rotation, you have 24 gates. And the number of iterations, I mean, when the students run this calculation, you have in the thousands iteration, and in the real machine, they have 500 iteration in the IBM machine. So here, let's talk about the scaling. What is the advantage of this quantum circuit? It is known since this is the reference in 210, and they show that classically the scaling or how many sampling from this Boltzmann distribution is exponential with the number of layers, m to the n. In our calculations, we show that this is quadratic, because like m times n, which is the scaling from the ancilla qubit. So we reduce the scaling from exponential to polynomial, which is quadratic. But again, just not to confuse you, this is only for the quantum circuit that do the sampling, not end to end, because we have other hidden cost in this algorithm. So this is really the scaling from exponential to polynomial. Quadratic is only for the quantum circuit. So here at this point, you can ask, okay, what is the cost function at the end that we're trying to optimize? Is of course the expectation value of the Hamiltonian. Once we get the wave function with a coupling of parameters, then use variational calculations. Now you start optimizing the energy as you change these parameters. So the cost function in this machine is the expectation value of the Hamiltonian. After you get the wave function from the circuit and you start optimizing your parameters. How do we optimize them is the classical algorithm here. So you can think about it as a hybrid. The quantum part will do the sampling, and the classical algorithm will do the optimization. So as I mentioned back in 2018, we show how this machine works for getting very simple potential energy surfaces for small molecular system that people have run it with different algorithms, the phase estimation or VQE or other algorithms that also can we do it with the restricted Boltzmann machine, achieving chemical accuracy for these systems. And then with my student, Sri Hari and Manas, we succeed to go to 2-dimensional materials by allowing the phase to get into account the periodic boundary condition. And what he did, he showed how to do the calculation for this simple 2-dimensional system, where we took the calculation here. We used the tight bonding Hamiltonian for both graphene and hexagonal boron nitride, and for graphene, he also took the Hilbert Hamiltonian, and this Hamiltonian already in the literature parameterized using density functional theory. So we are taking simple Hamiltonians just to show the proof of concept that the system or this quantum circuit works, and you can get the band structure. So again, the Hamiltonian is tight binding, and Hilbert Hamiltonian for this simple system, and the unit cell is 2. Here we have 2 degrees of freedom here, or 2 different atoms. So it's a very simple quantum unit cell where the matrix will be 4 by 4. So when we run the calculations, first you see the classical simulation, the QASM, which is the simulator, and the real machine for the first one. Again, the solid is the exact calculations, and we're talking about only the ground state, the valence band. And you can see the calculation matches the and you have the accuracies within chemical accuracy of the calculation done with exact diagonalization. I mean, there is nothing here really new. This is very simple calculation, but a proof of concept that the machine is working to get the valence band for these simple systems. And you can see, okay, even for the real machine, you can ask why the real machine is not noisy. What we have done here is what we call the warm start. So warm start, you said, okay, I start at the K point, I get the convergence. I'm not going to start again with random initialization of the system. We're going to use it. Once we have successful sampling and we get the results, we'll use that results as a warm start for another point. And this is give us like a way to avoid the noise coming out of this machine by use warm start and error mitigation. So again, if you do error mitigation and warm start, you start seeing the experimental results matches the exact diagonalization. And now the question is, how do you go to excited states? Now, what we have done so far is the ground state. How do you go for excited state? It's very simple. We use it all the time in variational calculations. Once I found the ground state, I will introduce a penalty function which projects out the ground state, because the excited state is supposed to be orthogonal to the ground state. So if I have a trick to project out the ground state out of the calculations, then the next one will be ground state. This is what we have done in the calculation by introducing now a penalty function instead of just the cost function. The first one, you introduce the operator O, which is, here's the ground state. And what we're doing here, we project out the ground state from the calculation, and the second one will be the ground state. And then we can get the ground state for using restricted Boltzmann machine. So this is what we have done here. And Manas is he's a postdoc now in the group, and he's leading this project of getting electronic structure calculations and the band structure for materials. And we call this filtering any state. It's not, I mean, we have shown results later. It's not only the excited state. You can, first excited state, you can go for higher states. And again, he used the tight binding Hamiltonian, which is fitted to these materials by density functional theory. And we use this Hamiltonian from this paper back in 2013 with 3 orbitals on the metal, and they use up to the third neighbors in this tight binding Hamiltonian. And he took this Hamiltonian and ran the calculation on the restricted Boltzmann machine. And here are the results. Now we don't have only the valence band, we have also conduction band. And again, these simple calculations can be done easily by diagonalizing these matrices, but as a proof of concept, we see that one can get this gap correctly. And you can see the results, not only from exact, which is the solid line. You have the classical calculation, the simulator, and the real machine. And again, for all this calculation, we use the warm start. Once we have good results at one point, we use the same thing to propagate the system to a different point. And you can see the error in this calculation electron volt. I mean, it's an average is 10 to the minus 6 for both. And the fidelity, we are looking at the expectation value of how the overlap of the wave function with the exact wave function. And of course, 1 minus will be the fidelity. And you can see the wave function also matches the true wave function for the systems. And again, we use it for this material. So recently, Manas was also able to get not only the second one, we did this calculation for the water molecule, and he was able to get the ground state, which was singlet. Then the second one also, the green is a triplet state. And the third one is the singlet. And he can go up with this restricted Boltzmann machine for higher states. And it's extremely important when you do spectroscopy, you'd like to get the excited states. It's not, I mean, you do differences in energy, and not only the ground state is important in these calculations. So in principle, this restricted Boltzmann machine can obtain not only the ground state, we can filter any state by giving the symmetry of that state, if it's singlet, triplet, or you know what is the symmetry of that state. And here is like the warm start using, if you use mean field, for example, you can really avoid many problems of getting localized in a local minima. If you use mean field, like in our case, we use Hartree-Fock to initialize the system. So you ask, okay, now what is next? And here I listed a couple of topics for like an open problems for the future, but I would like just to mention how did we use this machine to talk about the quantum phase transition and mention a couple of projects that we are involved in the group and where we're going with this method. So now quantum phase transition. So when we talk about the quantum phase transition, what is the quantum phase transition first? So we're all familiar with the classical phase transition, like melting an ice cube. You go from solid to liquid to gas when you change the pressure as a function of temperature. So this is classical phase transition. Now quantum phase transition, this transition happens at the absolute zero, and you cool the system to lower temperature, zero temperature, or the KT, the heat is smaller than the gap, so the system does not jump to the excited states. You'd like to stay in the ground state. And what we do here, we look at how the system with the ground state energy, which is the equivalent now with the free energy at T equals zero, how the free energy changes as a function of parameter in the system. And this parameter could be the electron density. In this case, you go from Wigner crystal to liquid, or any parameter in the system. And what I would like to show, was a recent experiment that, and we did this calculation a long time ago, that even if you have a finite system, you still can talk about a quantum phase transition. And here we'll mention the results from the quantum Rabi model, where you have transition from normal phase to superradiance phase as a function of parameters in the system. So a long time ago, I mean, it's like I was back over 20 years, we were looking at chemical processes like dissociation, ionization. Can we think about these processes as a true critical phenomena? And what we analyzed then, and we show that in order to describe criticality or phase transition, you have to go to the thermodynamic limit. I mean, this is a known theorem. You cannot see the true criticality unless you go to the thermodynamic limit. But now we're doing calculation with variational calculation in Hilbert space. So what we have found that the number of basis functions in Hilbert space play the same role as the thermodynamic limit. Where if I take the number of functions to infinity, which means the size of Hilbert space infinite, you can capture all the criticality of the system. And amazingly, all the formalism of finite size scaling that works with number of particles can be mapped to the number of functions in Hilbert space. So we're using this trick to get criticality in a quantum phase transition. And we have example, and then I mentioned this one because recently there is interest both theoretically and experimentally on looking at phase transition of finite systems. And here is the two papers that we used in our calculations. The first one by Martin Pileno and his group. They look at the quantum phase transition in the Rabi model. And more exciting was the experimental results by this Chinese group, Cao and co-worker, where they observe a quantum phase transition in the quantum Rabi model with a single trapped ion. So what is this model? And here the graduate student that work on this problem, Bilal. So the model is simple system. You have two-level system interacting with bosonic field. So you have two-level system with the sigma z, and delta is the gap here for this. And then omega 0 is the frequency for the bosonic field, and the coupling is linear. And what they did in this paper, they show how the ground state changing as a function of this parameter, which is the coupling lambda and delta. And they show that the system exhibits a second order phase transition where the second derivative jumps at the critical point. So this is second order phase transition. And experimentally, they look at the same thing with the trapped ion. And now here the degrees of freedom that the hyperfine structure, the two states, and interacting with the vibration in this trap. And again, here is the analytical model that just show it's a second order phase transition. And you see in the red here is the second derivative jumps at the critical point. Anyway, we use restricted Boltzmann machine and this calculation done by Srihari here with, you can see the results 4 qubit in the visible, 4 in the hidden, and 12 ancilla qubit. We're able to simulate this quantum phase transition on a quantum computer. So this is show that a proof concept that also quantum phase transition can be used within the restricted Boltzmann machine, and you can get the criticality by looking at different sizes at here, different n, and see the crossing, and there is extrapolation algorithm as a function of the size of the system. We put together this paper in the archive in collaboration with Arnab, and I see Arnab is here. And this paper will appear soon in the Frontier in Physics. It will be out this month, but you can see, look at the version on the archive. We went through all the details. How do you simulate this quantum phase transition in a quantum computer? And how do you get the criticality using finite size scaling in Hilbert space? So again, this is very important. Now we can use, now when I said, okay, Hilbert space, now we know how to map functions into qubits. So we can use the qubit as the representing the size of Hilbert space, and we can get quantum phase transition as you change the number of qubits or number of basis functions. So why this is important, the whole criticality issue. And I like to mention this work from back in 2018 with my two graduate students. We were able to show that one can map the Schrödinger equation into an Ising type Hamiltonian. So you map it, it's an exact, so maybe big. I mean, it's still a variational mapping, but you can map it to Ising, but it's not efficient, which means the transformation is not polynomial. But we can see that for a small system, what is the Ising Hamiltonian representing the system? And you said, okay, what is so exciting about it? Because now I map the Schrödinger equation to Ising, and we know the rich phase diagram of Ising. The first question you ask, okay, this rich phase diagram of Ising Hamiltonian, what is the equivalent in electronic structural calculations? Because you have one-to-one mapping between the two problems. And this will take us back to the claim that we have it all the time, that quantum, in chemistry, when we talk about dissociation, ionization, electron affinity, all these processes in chemistry, there's a beautiful critical phenomena behind all these processes. And we argue in the past about this phenomena, but now we see that maybe there's one opportunity to do this experiment and get the true criticality of these systems. And now the question is, where are we taking with this flexible machine? One approach is really to go to long-range entanglement or quantum spin liquid. And this is an ongoing collaboration with Arnab. And this is really part of our research within the Quantum Center. And we have other projects with the group here, how to use quantum machine learning to classify states. And here you have metallic to insulating states. And we're trying to understand the process in the group. How do you relate this restricted Boltzmann machine to renormalization group? Because at the end, what we do in normalization group, you integrate unnecessary variables or the variables that you don't need, and you go from large scale to small scale by integrating out degrees of freedom, not contribute to the criticality, and would like to understand the flow of renormalization group in comparison with the flow in restricted Boltzmann machine when we talk about quantum criticality. And here we have the graduate student also looking at how do you go from the quantum machine learning to talk about tomography, and how do you construct the density matrix of the system from known observables. So this project in the group I would like to mention, because we have many students here, and these are the open problems that we're trying to tackle in the group. And yesterday, Vlad gave us a nice presentation of his work on machine learning. And he mentioned this work where Blackie is reading this one. He's a joint student with two groups. And the main idea, how do you go from continuous variable and map it to quadratic optimization problem? And we saw the excitement and the application with the talk by Vlad yesterday. And we'd like to continue this kind of inverse design and how you can map continuous problem into a cubic problem. We have other approaches, and maybe Alam will talk about it. How do you optimize the solar optimization? This is an old grant internally with also looking at quantum, at the material design, and this was also collaboration with Young. I would like just to mention for the last maybe I still have 10 minutes. Huh? I would like to mention the work on dynamics. So far we have electronic structure calculations, And the question is, how do you push it for dynamics? Because at the end, people said, okay, the advantage of quantum computing, you're going to do catalysis. Okay, what's catalysis? Electronic structure was not going to solve the problem. What is catalysis? Catalysis, you have a reactant and you have an output. This is chemical reaction. The barrier for this reaction is so high that you need a catalytic process to lower this activation energy. So the catalyst is not going to do anything except lowering the activation energy or give you another path. It's not going to change the thermodynamic of the system. It's lowering just the gap, which means it's going to find another path in this complex space that will allow you to do this chemical reaction. So it's both. I mean, you cannot solve this problem with electronic structure. You have to do the dynamics and look at the rate of this chemical reaction and how the process is. It's a very, very complex problem. And one has to be careful when we say, okay, catalysis and nitrogen fixation is the problem for quantum computer. I mean, it's a very, very complex process, and people work on this one for years and years. And one has really to rely not on electronic structure, also have to understand the dynamics and the rate of the reaction and how the catalyst finding another path. So if you think about it, how the catalyst is finding an optimal path is really exciting because you have many paths for this reaction. And somehow the catalyst knows, or the enzyme for our life, knows exactly what's the path to minimize the activation energy in order to do the chemical reaction. So we could think about it how, like, what exactly the path that this enzyme or this catalytic reaction finding in nature to lower the activation energy. It's really very exciting, and somehow nature knows how to do it and optimize these paths. So we have in the group, we couple of projects from how birds finding their magnetic north, how quantum coherence enhance the efficiency of solar cell, and in photosynthetic reactions, when people look at the exciton dynamics, why this process is so efficient in nature that from the antenna to the reaction center, almost the transfer of the exciton is 100%. Although you have an environment. So somehow the environment is assisting the transport, and how this environment assisting the transport will give us indication about the role of the environment in the transport. So we're trying to look also how the restricted Boltzmann machine can help us in the transport or quantum transport phenomena, and how do you obtain transport or IV curves from restricted Boltzmann machine. And we have done a lot of work in this direction, and now we're trying to see how to implement this one in quantum devices. And for me, when I look at this problem, all these problems have shared the same physics. It's really, when you analyze these problems, you see what happens in photosynthesis. You start with sunlight. Whatever the mechanism is this, you turn sunlight into chemical energy. When we talk about solar cell, what is solar cell? You start with the sunlight, you have all this transport in, and you turn sunlight into electrical energy. When we talk about the avian canvas here, you start with the sunlight, whatever the mechanism is, go for direction. So they share the same physics. You start with the sunlight, you excite electrons, you have your mechanism for transport, and then you turn sunlight into chemical energy, to electrical energy, or direction. So we're trying to come up with a unified way to analyze these three problems. So how do you do it? The way you do it, you have, I mean, now here is the problem if, so in 2 minutes, okay. So the problem is like here you have a system and interacting with the environment. And what we have to do is solving the quantum master equation, which allow us to look at the dynamics of the density matrix of the system with the environment. And we use the Krauss operator. And then let me just summarize here, because we have a few minutes for talk. So what I have shown you that the restricted Boltzmann machine can be used in principle and to do electronic structure calculations for simple molecular system. Also a proof of concept for materials, the valence and the conduction band. We show how the machine can be implemented by using quantum circuit on the IBM Quantum devices. We show results for two-dimensional materials. And we talked about how this can be used for quantum phase transition and open quantum dynamics, which is still a new problem in using this restricted machine. So for those here, I would like just to advertise everything I said and more. We put together, this was a project from the group, all the group participated and all are here in putting together a review article. I think we reviewed over 700 with the whole group, 700 papers, and we put together this review article, and it's on the archive and still going through a review. And I would like to end by thanking the students are here. They're doing all this hard work for many years. And I'm lucky to have students from not only chemistry, we have physics, computer science, electrical computer engineering. We work all together after we overcome the barrier, the language barrier. And now we are all focusing on different application, structure and dynamics for these problems. And I would like to thank all the agencies that supported us for years, and Bailey here talk about the Quantum Science Center for pushing this, the six boson machine into this emerging phenomena in quantum materials. And again, thank you for your attention. And this is my email if any students would like to get more details about our calculation. So thank you.
Thank you. Yeah, thank you, Professor Kais. I think we have time for one question from the audience. And if no one has any questions right now, I'll remind you that, oh, yes.
One of the questions I had about these variational algorithms is it's easy to get lost in the Hilbert space.
Yeah.
So you want to warm start using a technique like DFT or TMRG, so you kind of know where to start, and then you get a lot of.
You get so you start with warm starting with DFT or TMRG to get a good initial guess. You can use techniques such as symmetries to filter or purify your results at the end. Is there any kind of trick that you can use in optimizing for the variational step?
Yeah, I think this is a very important problem, especially when you go for large systems. And we know the discussion of the Parainian plateau, that if you go for large system with large number of gates, you start seeing the flattening of the surface, and even optimization because of the gradient will go to zero. So it's really very hard to overcome this problem. And for this small system, we don't see this problem, that the flattening of the surface in multidimensional space and the dimension of the gradient. But this is a very serious problem that people facing in this optimization. And the question is how to overcome this one for large system. I don't really have an answer for that.
Right. Anything that could be physically informed?
We'll let you know after the.
Okay, great. Thank you.
Thank you again, Professor Kais. Now it is my pleasure to introduce Dr. Alex Kiesling. So Alex earned his PhD at Harvard under the advisorship of Professor Misha Lukin, where he pioneered the work of programmable Rydberg atom arrays into a leading technology for quantum information processing. After his PhD, Alex took what he was working on at Harvard and founded QuEra Computing, a quantum information company developing programmable Rydberg atom arrays, along with several Harvard and MIT scientists and professors. Among his accomplishments are the creation and coherent control of systems with hundreds of neutral atom qubits, the demonstration of high fidelity entangling gates with neutral atoms, the discovery of quantum many-body scars, and the observation of new quantum phases of matter. So I'll turn it over to you whenever you're ready, Alex.
We'll give it a second for some technical work. But I can take the time to thank you all for being here. I know it's somewhat early. It's my first time at Purdue, and it's been lovely for the few hours that I've been here. I guess it also helps that the day outside is very nice. And so thank you very much to everyone for the invitation. It's a real pleasure to be here and to be talking about some very cool new science coming out of this platform of neutral atoms that we're now leveraging really hard. And the last 2 years, I think, are a great example of that for quantum simulation, but also for quantum optimization. And more generally, we're moving towards quantum information processing in a universal way. My name is Alex Kiesling. I'm the CEO of QuEra Computing. We are a company based in Boston, commercializing the technology that has been developed at Harvard and MIT over the past 7 or 8 years or so. And I'll give you a little bit of an introduction to the company. Since this is a summer school, I try to pick one topic and go through it slowly to give you a good overview of how the system works and what can be done with it. And at the end, I'll go back to telling you a little bit more about how you can engage with us. All right. QuEra Computing, as I mentioned, is a Boston-based startup. This was created because we all, after working at universities, came to the conclusion that we're a group of optimists, and we believe that technology can transform the world and improve society. And we were working on technology that has this potential to enable new applications of what we have been developing over the last 100 years with quantum physics. And our mission is to provide useful quantum advantage for customers starting today and moving into the future. We understand that there's a lot of work that needs to be done on developing quantum technologies, but given our experience, we believe that today, with the size and coherence that the neutral atom platform has, it is possible to get real value out of these systems. The company is formed by an outstanding group of very passionate individuals, all of us trying to make quantum computing real. As I said, we work with neutral atoms, which are particularly well suited for scaling to larger and larger system sizes. And there's some evidence from the past 2 years that at these sizes, you can already start seeing you can start using the hardware to learn something about other quantum systems and also about how to solve optimization problems. More generally, we're building not just hardware, but we're working on different layers of the stack, building software tools to allow customers to engage with the machine, to be able to program it. But we're also working on developing algorithms. And this is a core belief that we have at the company, that to get the most use out of these systems, it's important to take into account what the physical system is and develop algorithms that are efficiently implementable in this hardware, both in how the qubits are connected to one another, but also in the kinds of operations that can be implemented. So this is the system. And please stop me and ask questions at any point. I want this to be as informative and didactic as possible. Our system is composed of neutral atoms held in a vacuum using tightly focused laser beams. There's a few reasons why we chose to work with neutral atoms and that make them an appealing platform for us. The first one is that there's no manufacturing involved in any of this. We don't need to build chips. We just take atoms that are given to us by nature. They're all identical to one another. And it makes it easy to learn how, by controlling one atom, we can extend this to controlling many of them. Atoms are quite well isolated from their environment, which extends coherence properties. When you think about some of the most precise measurements that we have that require this isolation from the environment, they come from atomic transitions. So this is another reason why neutral atoms have a lot of appeal to us. And the last one is that neutral atoms, they're isolated from their environment, and this includes one another. So they don't naturally interact with one another unless they undergo a collision, or unless we set the circumstances for them to interact. Particularly in this case, what we do is to control a single electron within these atoms. And by exciting this electron, we can create effectively a very large dipole that allows the atoms to interact with one another. There's a few other advantages that come with the system. One is that because the isolation comes from working in a vacuum, the system operates at room temperature. The connectivity is also something that we have a lot of control over. There is a local form of interaction which allows us to create gates only between pairs of atoms that are close together or between clusters that are within a given distance of one another. So this is something that we have control over and that we can use as part of the programming model. There we go. And as part of the programming model, we have the fact that we can, for every task that we try to solve, we can reconfigure the connectivity and the positioning of the atoms, encoding problems efficiently into them. So from a fraction of a second to the next, we can go from a problem that looks like an ordered system to something that looks like a random distribution, or something that has nearest neighbor connectivity to something that has effectively a longer range connectivity. And this allows us to reduce the necessary overhead to take problems and implement them directly on the hardware. And last, because of the fact that these interactions are local and that we have the ability to define the position of the qubits at every single shot, this allows us to parallelize the system. And once again, because the atoms are non-interacting with each other and with their environment, it makes it easier to pack more of them together. So these images that you're seeing at the bottom, these are real pictures of individual atoms, where each one of these bright little purple spots is fluorescence emitted by an atom that we're capturing on an electron multiplied CCD camera. Now, getting a little bit more into the weeds, the way that this works, we start with a single laser beam that goes into a spatial light modulator. This is a liquid crystal and silicon spatial light modulator. This is not too different from what is used in conventional projectors. And we pre-calculate a hologram to display on the spatial light modulator, which imprints a phase profile on the laser beam, which allows us to then effectively take the Fourier transform of that using a lens and create a distribution of very tightly focused light spots. By bringing these light spots inside a vacuum chamber where there is nothing but the few rubidium atoms that we inject, we are able to take these atoms, which we cool using lasers and magnetic fields, and pull them into the focus of these lasers. This is how we go from just light, like what you see at the top of the screen, to then an image of atoms. And again, here, this is an image taken over about 10 milliseconds, where each one of those spots is a single atom. As you notice, there's a lot of randomness in where the atoms are and are not relative to the picture on the left. And this is just part of the procedure. Every time that we want to initialize the system, we have a random distribution of atoms, but because we can image them quickly enough, we can then introduce another set of optical tweezers, which are being generated with acousto-optic devices that allow us to create a different movable set of tweezers that can pick up atoms at one position, move them, and drop them into another one. And at the end of the day, this looks something like this. And this is about the rate of repetition of the experiment. We can initialize very large system sizes at a few hertz. Of course, there's some finite error in this procedure, but we can periodically initialize systems with hundreds of atoms, which is the starting point for everything else that I will talk about. The geometries, as I said, are completely flexible. We're not tied to having a particular grid. As you see here, there's quite a variety of things that we can do. And we can also just initially define a random set of positions where we want atoms to be, put that into the computer, and get that exactly out of the experiment. Now, atoms are very nicely non-interacting. But now the effort is for us to make the atoms interact with one another and to do something useful with them, to generate this entanglement that produces the kinds of effects that we're looking for. So I'll walk through the Hamiltonian that describes the system step by step. First of all, I will define two levels for the atom. And as we know, there's no such thing as a two-level system in nature. Atoms are in two-level systems, but we can isolate levels within the atom very nicely. In this case, we use the outermost electron of this rubidium atom, and we can use laser beams to excite it to a very high principal quantum number, effectively a large orbit. So these will be the two states, the electronic ground state and this highly excited state, which we call the Rydberg state. By coupling these two, we have a sigma X term. This is exactly what you would expect. There's just some resonant driving between two states. We can see Rabi oscillations. The coherence is can go on for multiple cycles. So this is a starting point for a single atom. And here I'm denoting the Rydberg state by that large circle. Now, the reason why we use these states is because now we can have an interaction between them. And this is an van der Waals interaction, but it only is present when two atoms are both simultaneously in this Rydberg state. So this N represents the population for a particular atom in the Rydberg state. So the way this looks like is if we have two atoms and they are far away from one another, so on the right of this plot, we can create an excitation on the left atom or the right atom, and for the same amount of energy, because there's no interaction effectively, we can excite the second one. However, when they're close, because there's an energy penalty for this interaction, we can only create a single excitation, meaning either the left or the right atom will be in the excited state. This, in principle, creates an entangled state already. If we take two atoms in the situation that you see on the screen, and we just pulse a laser, we'll actually create a superposition of having the left atom excited or the right atom excited, but not both and not neither. And again, when they're far apart, none of this happens. They just both get excited. Now there's another term in this Hamiltonian, which is relevant for this picture, which is that, well, I'll get to it in a second. But first, the way that we can think about this interaction is that if we take an atom, any particular atom, we can define the maximum distance over which it will, if excited, it will prevent a nearby atom to also get excited. And we call this the blockade radius. So any atom within this circle will not be able to get excited. And for that, we can just draw a connection between the two and say, these atoms cannot simultaneously be excited. This is a constraint. That can be done for every single site, and we can recover some kind of connectivity. And this is leading towards a graph problem. Now, there's another term in this Hamiltonian, which is the detuning. Basically, are we resonant in this transition or not? And the important thing here is that for the many-body state, when we look at this entire system, if we take this delta term and make it less than 0, then we're creating a situation in which all the atoms to lower the global energy will go to the electronic ground state. However, when we increase this detuning, we're making it more favorable for them to be in the Rydberg state. But remember, there is this hard constraint. So the many-body ground state for this large detuning is that in which we have the highest number of atoms that have now flipped their state to the Rydberg state, such that they still obey this constraint. There are other ways of thinking about the system, but this is a particularly good one for the results that I will describe today. Now, using just that concept, there's been a few recent results, and yes? There's a large beam that is moving in that direction, and it's addressing the entire system globally. You don't. This is addressing everything globally, and we will actually make use of the connectivity of where the atoms are placed and the fact that we can initialize ground states like the one on the left to do everything that I'll show you today. All right. So in the past 2 years, we've had a few exciting developments. This is particularly, I will show you things that have been published, driven primarily by the work at Harvard. One is on quantum optimization. Another one, which I believe you'll hear about tomorrow, is on simulating other quantum systems, and particularly here, observing signatures of quantum spin liquids. And very recently also, reimagining the architecture to implement motion as part of the computation so that we can, with very few controls, still have a universal gate-based quantum computing system. And the way that this looks like is a little bit like this. So you can actually move atoms and you can implement gates between them and separate them then to perform also local rotations. Again, I will not talk about everything, but I will mention that at QuEra, the machine that we have sitting in our space will get connected to the cloud later this year through the AWS Bracket service. So these two types of results you'll be able to replicate soon. And for these two on the right, to the best of my knowledge, you'll hear more about tomorrow once Misha Lukin is here. Today, I will focus on this, on using these systems for quantum optimization for a few reasons. One is that recency. These results just came out last week, so we're very excited about them. Another one is that it allows me to take to show you a little bit of the tools that are necessary to make something, to make sense of the complex large systems that we work with. And the last one is that it will allow me to move back and forth between the language of computing and many-body physics and simulation. So while I will talk about this as an optimization problem, you can also think about it as observing phase transitions in disordered systems. Now, I do want to talk about it in the context of optimization, though. And the reason for this is that we have all of these ideas about what will quantum computing do for all of us. And there's a lot that we can learn by studying these systems mathematically. But we are at the point where we can play with hardware and use that to learn more about what quantum systems are capable of. So a reasonable question to ask is, in the near term, can we expect to see any kind of quantum advantage for the kinds of problems that we already have mathematical descriptions for? And so far, there's been several attempts. They're all building together a very nice cohesive story. Some of them have been done on small systems with shallow depths, very good results matching theory with experiment, but at the point where you can still completely simulate this on a laptop or a larger computer. Then there are other implementations where the effect of quantum coherence is limited. So while they are great optimizers, it's much harder to gain any insight into the role of quantum physics here. Our approach is to combine large circuit depths by using a hardware efficient implementation of this problem with large slices to gather some more information about what we can do in terms of optimization. The optimization that we're working on is for a particular kind of problem called the maximum independent set. This is an NP-complete problem, meaning that, yes, it's hard, But I think that the more useful way of thinking about this is that it's a language. It's a language to take problems that we generally try to use computers for and then reframe into this particular formulation. There's several NP complete problems like traveling salesman, but the important thing is that they have real world applications today, and we do try to solve them even if we don't have great solutions for them. Exactly, for at least for the hardest instances, we don't have good solutions. And something that is very deep about working with NP complete problems is that because it is a language, if we are able to solve any NP complete problem efficiently, or at least better than we can otherwise, we have a way to extend that to every other problem that falls within this complexity class of NP, even if it looks nothing like the formulation that I'm going to give. And the formulation is the following. Given a graph of nodes connected by edges, the task is to find the largest number of nodes so that no two of them are connected by an edge. So an independent set is nodes that are not connected. The maximum independent set is the largest such set of nodes. And this, it's easy to explain. Trust me, it's very hard to solve. There are known instances with about 400 nodes where we still cannot solve to this day. Now, why am I so focused on the maximum independent set? Well, it turns out that what I told you a few slides ago was exactly this with different words. I said that if we place atoms, it's exactly this for a particular type of graph, which is known as a unit disk graph, in which the connectivity of the graph is given by some distance between the nodes. So if two nodes are within a particular distance, they will be connected. And as I was saying, this is exactly what I was telling you about a moment ago. If we put two atoms at a particular distance, we are setting a constraint that they cannot both be excited to the Rydberg state. So by just trying to excite as many atoms into the Rydberg state and placing them in a configuration that is exactly like what you see on screen, we are effectively trying to solve the maximum independent set. Was that clear? Because that's kind of the basis of this. Great. I'll start moving then a little bit more quickly, but that's exactly the idea. If we have a large system like this one, where the blockade radius encompasses the nearest neighbor, but also the next nearest neighbor, we can create a graph like this one, which for the experts in the audience is non-planar. There are many crossings. By using the same controls that I was describing with the driving and the tuning, we can then implement this blockade constraint. The blockade constraint enforces this MIS constraint. It's the same one, and we can encode directly this kind of graph in the system. So the full Hamiltonian here, this is just giving us the same mathematical description that the MIS problem is, but it also has this other term that is the transverse field, the Rabi driving. And thinking about this in the context of a many-body system, of a quantum system in the condensed matter sense, which we heard a little bit about at the end of the last talk. This is a transverse field Ising model with a large longitudinal field as well. So this also has connections to other material systems, for example. So what are we going to do? The recipe is very simple. We initialize the state in something that's easy for us to prepare. Then we implement a quantum circuit. In this case, we have two options. We either do things slowly by tuning parameters continuously, or we pulse the controls more along the lines of what QAOA was described as. And then at the end, the state that we're preparing, we're trying to get to be the MIS, but even if not, we'll try to approximate it. And the way that our control parameters look like is like what you see on the left. Again, we have Rabi driving that we can turn on slowly to really initialize this ground state at large negative delta. And then we can move delta continuously to a positive value so that we try to take a simple to prepare ground state into a very complicated to prepare ground state adiabatically, or as adiabatically as possible. This is how we'll do most of it, although we did test this pulsed approach, and I'll show you some results about that as well. The way that we are approaching the problem now is, we can take a simple function like a linear function to go from this easy to prepare ground state to the hard to prepare ground state, but to increase the fidelity with which we are preparing this effective ground state, we can also parameterize the evolution of this delta parameter as a sequence of piecewise linear segments that we then smoothen out. So we have a few different control parameters, the initial detuning, the final detuning, all the intermediate ones, and the times at which they turn over. So we start with an ansatz for what would be a good way to sweep these parameters. We start with a problem that is how we put the atoms relative to one another. And then we implement this quantum evolution. At the end, we project the system, we take a measurement, and we effectively just count how many atoms went from being in the ground state to being in the Rydberg state. And this is our cost function. How many nodes are in this system? By repeating this procedure over and over and over again, we can create a histogram, like you see on the bottom right, that tells us how often are we preparing a set of a particular size. And ideally here, we will prepare the largest possible set, which is the right line. And as you see, we do, but we don't do it always. From this, we can extract many different metrics, including how often we prepare the correct ground state, but also what is the mean number of nodes in the set. And we can now use that as a cost function to tweak how we are implementing the control sweep. And by putting this into a classical optimizer that is now changing the parameters of the sweep automatically, we can start getting better and better approximations. And what you're seeing there is what this sweep looks like. So at this point, the machine is working basically without human intervention. We defined a problem. There's an easy to measure cost function, and it is running in a closed loop where it's analyzing the results as they come out. It's updating its belief about what a good sweep would be. And then it's just cross-checking and continuously approximating a better and better solution. This, by the way, was all done using the experimental device sitting at Harvard, but much of it was informed by the work that we're doing at QuEra, including this optimizer loop. And it was also, funny enough, we started really pushing on this right at the beginning of the pandemic. So for us, it was, while I was still at Harvard, this was a little bit like a test run of how would we have to operate one of these machines if it were only available on the cloud. So basically all of the results that you're seeing here, they came after adapting the university lab within a week to be able to control it remotely, to operate it, to debug and so on. And that's how it was all taken. And that is now also informing how we are setting things up with the QuEra devices so that it has the same level of reliability and without needing intervention. Okay, so now we can compare how do different algorithms perform and be more quantitative about it. As I said, we can look at the mean number of nodes that we have in the set after a given number of repetitions of the experimental sequence. And In these cases where we know the size of the solution, because we can still compute it with classical computers, we can define this approximation ratio. We can do it two different ways. First, using something that is very much inspired by the QAOA algorithm, the quantum approximate optimization algorithm, where we pulse the control parameters, and we see that the more layers that we add, the better it gets, up to about 4 or 5. After that, it starts getting hard to continue optimizing the parameters for deeper and deeper circuits. And we see that the approximation ratio is, we get about 75% of the way there. If instead we use the kind of approach that I was showing you about, then defining depth now becomes a little bit different. It's not just the number of parameters that we're optimizing over, but also how long we allow the system to evolve. And in this case, what we're defining as a depth is what is the total evolution time relative to the time that it would have taken to flip all of the qubits. And this gives us an effective depth that, as you see, can go to much, much higher to what you have on the left. And for reference, the total time evolution for this pulsed approach is also consistent with being on the order of 2 on this right plot. Importantly, the approximation ratio at the optimum gets a lot better. We're talking about starting from getting about 75% of the way there to getting 91% of the way there. So one of the big lessons for us was that to get the most power out of these devices, out of the NISQ devices where we're still not correcting for errors, where decoherence plays a significant role, is to look at two things: how to efficiently implement a problem onto the hardware, in our case, by doing the mapping to this graph problem. And the second one, to use the hardware to its advantage. And in this case, the advantage is in being able to prepare ground states and to keep low energy states. So these two things put together are what is driving the very good performance of the system. Decoherence is still something that we need to consider, and that's why we believe that the curves turn around after longer and longer times. But we can find a sweet spot where we are really seeing depths that are consistent with having information spread throughout the entire system. And this is actually very important. I'll get back to it in a few slides. This is basically recapping what I just said. One of the reasons why we think that this picture on the left doesn't get better that easily is because the assumption that I made, that I just stated, was that this blockade is strong enough to not allow for mutual excitations. But that's not true. There's an energy penalty. But here, by using this pulsed approach, we believe we're creating many more of these excitations, which are then harder to control as the depth of the circuit starts increasing. Good. Now, we can do this not just on that one graph that you saw, but on multiple graphs. And we can take the same pulse, rescale it in time, and see how the system performs. And you can see that different graphs have different performance. They all have similar behavior in the early times, but the slopes of how the approximation ratio gets better are different. And we tried to do an exploration by changing the size of the system, the particular random distribution, and try to find a correlation. It turns out that the correlation doesn't really seem to come from the system size. And this took us a while to figure out what was really going on. And after a little playing around with ideas, we came up with this. What we're looking at is, on the left, rather than arranging things by how many nodes we have in the graph, what we're asking is, we know that there's a particular size for the maximum independent set, but how many different configurations are there for this maximum independent set, namely, what is the degeneracy? And this degeneracy can change wildly for a particular system size, and it also changes across system sizes. But what we see is that there's a very strong correlation between the kinds of approximation ratios that we get and the number of possible solutions that there are. And maybe this is something to be expected. This is true across many different system sizes. You can say maybe this is something to be expected because the more solutions you have, the more likely you are to find one. However, the slope here is interesting, and it's not clear that that can really explain the full behavior of the system. As a matter of fact, it looks like the slope is about a third, which is not something that you might expect. So we had to come back and think, what is causing this massive difference in total number of solutions and how easy it is to approximate these solutions. And we had to go back to thinking not in terms of complexity and optimization, but more along the lines of condensed matter and quantum many-body systems. And what we realized is that just like any other quantum phase transition, the way that this process happens is that correlations start forming throughout the system at a given rate, and we form correlated systems of a particular size. There's actually a very precise prediction of what this process looks like, and it is the Kibble-Zurich prediction that tells us that the size of these correlated domains scales as a power law with the rate at which we are crossing the minimum gap, which in the infinite size limit turns into a phase transition. Now, thinking about this picture, we can see that if there's a system that has multiple solutions, it's possible to create correlated domains that even though they're inconsistent roughly with one another at the interface, they can effectively slide and give us a better approximation ratio. So the higher the degeneracy, the higher the likelihood that these smaller correlated domains are still going to represent very good solutions. Basically, the problem looks more local. And going back to this prediction, we can actually put in some time, effort, and thinking and get what is the expected power law that one would have for these disordered systems. And this is what you see here, experimental data compared to our prediction. So it seems like this picture is giving us a very good representation of the system. Now, we want to benchmark this. We don't want to just make claims about the quantum system, but what if we weren't using a quantum system? And for this, we're using a very generic classical algorithm, namely simulated annealing. Simulated annealing basically takes a spin model and allows single spins to flip one at a time and accepts it with some probability, depending on whether the energy was lowered or not. So this is quite a powerful way of trying to solve these kinds of problems. For our case, we used even correlated flips to try to get more power out of the classical algorithm. And what we know about this is that after enough iterations, the system will coalesce into something that looks like a thermal distribution. So there's a potential that it gets stuck in local minima. To get to the true minimum, there's an exponential amount of resources that are necessary. So as I mentioned, we use collective updates to get more power out of it. And now we can take a look at the data for the comparison between what we're doing with the experiment and what the simulated annealing gives us. And as you see, there's a few different things here. There's the experiment seems to be doing better even in the early times. And one thing that we noticed is that there's different graphs, some of which show a feature of slowing down, some of which just continue to get better over time. But the slopes are not too different seemingly here. So here, again, at low depths, the performance is quite similar and better with a experimental device. And at low energies, we see this feature of slowing down and getting trapped in what we believe from how simulated annealing works to be local minima. After further inspection, we actually found that this approximation ratio is consistent with being 1 away from the optimal solution. So we get most of the way there, but then the system slows down. And we came up with a way of thinking about what's really happening. If we map out all of the possible solutions, not just the correct solution, the MIS, but all the ones that are just one size smaller, there's a few of them that connect by a single spin flip, but most of them are actually not connected. So with simulated annealing, what we believe is happening is that the system gets to some distribution of all of these possible solutions, and then there's a random walk. And this random walk is what's slowing us down. So to characterize how hard it is to find these true minima, we defined a new hardness parameter, which is how many solutions are there that have one node less than the correct solution divided by the number of edges that lead from this subspace into the correct solution. And yes, it turns out that there's an exponential runtime in system size, and we have numerical evidence for this. So everything seems to check out. Now, if we focus on the instances that seem to be hard, and that they have effectively this hardness parameter be high, we can still find differences. And we can see that some graphs are hard for both quantum and simulated annealing, but some of them just get easier for the experiment to approximate good solutions. And when we look at the probability of finding the correct solution, the MIS probability, this can be a difference in at least 1, if not 2 orders of magnitude. So trying to understand this, again, kind of going one step deeper and deeper, we come back to very fundamental questions in quantum physics, and particularly in phase transitions, namely Landau-Zinner. And here, what you're seeing here is the solutions for the hardest graphs. With these blue data show the simulated annealing, so the classical version, and the red data is the experiment. So if we take all the data, the hardness, there's an exponential dependence on the hardness parameter, and it seems to be very similar across the quantum and classical data. However, we do see much more variability in the quantum data than in the classical one, particularly at around depth 20 or 30. And this, again, kind of one level deeper, we try to understand by thinking about how does the gap close between the two sides of this effective phase transition, and how adiabatic can the process really be if it's limited by a single gap closing. So for some of these graphs, for the smaller ones, of course, we cannot simulate large systems with hundreds of interacting atoms. But for the smaller ones, we can calculate these gaps, and we can also identify them experimentally. If we do a protocol where we go fast, then slow, and then fast, and move where that slow region is, we can see that there's a particular point where the performance just gets a lot better. So we can experimentally identify where the gap is, and we can corroborate from numerics that it is in the correct place. Now, if we calculate the gap and we look at the corresponding time that we evolved the system over, we can see that for some of these systems, we are in the regime where we are going slow enough that we expect there to be for everything to be effectively still adiabatic. But there's some other ones where the gap is very, very small, where adiabaticity will just break down. So this needs better performance of the system. But But for the ones where we do see, where we are going slowly enough, we can now separate and analyze that data. And we can see that there's a, if we rule out the data for the ones that we were too fast for, and we focus only on the ones that we were slow enough, we see that the scaling is actually different. So we're starting to identify, kind of using an experimental device hardware, we're really starting to see all of the signatures that you would expect from a quantum system, where now for the instances where we are adiabatic, we're starting to see a better scaling in the performance of the device relative to classical solutions. So this is super linear speed up in circuit depth for approximating solutions of these hard optimization problems. This is what is expected to be the case in a generic case. And right now we're working very hard on identifying what are features that we can identify ahead of time that tell us whether the quantum device will be able to perform better than the classical device. And also, how can we take other features of graphs and change the way that we're implementing this adiabatic evolution to get an even enhanced speed up over this. I'll move on to something else, but I wanted to take a moment to recognize that this was the result of the work of a lot of people across multiple institutions, and particularly Separate Body, who is a graduate student at Harvard, and Maddie Kane, also a graduate student, were instrumental in getting these results, both on the experimental side and the theoretical side. But as you see, the list is quite large. That's what I have for the optimization. I'm going to move on to something else, but I want to take a moment to take any questions if there are any. All right. So now that you know what can be done, how can you take advantage of this technology? What you're seeing here is the first device that we have at QuEra. This is built with a Harvard instrument as a blueprint. And this will be available to customers through two different ways. The first one is through direct partnerships, where you can engage with a company. If there's a particular project that you're interested in running, we can devote time and resources to develop algorithms together, to work on mapping problems to the hardware and to run it. But also later this year, as I mentioned earlier, the device will be connected to the bracket service on AWS, so you can access it directly and corroborate everything I've said so far. This device is what's sitting at the center of everything, and those are pictures of, of atoms that reminded us of constellations. So we have decided to call this machine Aquila, the Eagle constellation. It's also nice that it has a Q. Now, talking about direct partnerships, we're already starting some partnerships with people here at the QSC. Particularly, I see Sasha, Vlad, and Arnab here in the audience. And of course, Blake has been working hard with us on pushing through the project definition and how we will implement two different problems. One is also Vahan, who I don't see here. But we're looking both along the lines of quantum simulation for the kinds of problems that were mentioned in the previous talk, looking at material systems. In this case, this is particularly as the Shastri-Sutherland model. What can we learn about these systems and how can we build towards non-abelian quantum statistics? And similarly, we're looking at extending these quantum optimization tools and taking other generic problems that, again, look nothing like the maximum independent set problem and mapping them to something that is able to be solved by the hardware and implemented efficiently. So here we're looking, again, some questions in inverse design, for example, where computational resources are quite expensive. Lastly, I want to draw your attention before taking any questions to something that we just made publicly available. We have a suite called Blockade, which allows you to play with these concepts with an emulator. It runs on Julia, and it has a lot of very nice properties. We've benchmarked it against some of the other solutions out there that would allow you to explore the type of analog evolution for systems like ours, particularly with Q-tip and Pulsar, and it is outperforming both of them. It already has support for GPUs. It's compatible with Yao, one of the programming languages whose creators are affiliated with QuEra. So if you go to look for Blockade from QuEra, you'll be able to download this and start playing with devices. Well, start playing with these concepts in exactly the same way that you will with a device once it's online. This is the QuEra team as of a few months ago. We're growing, so if we're looking always for bright, motivated people. So if you want to talk about that, come find me afterwards, and that's my email. All right, that's all I had. Thank you.
All right, thank you so much for that fantastic talk, Dr. Singh. So we have time to take a few questions from the audience. I think he'll come up with the mic.
Hello. So you have this simulated annealing algorithm, the classical algorithm that you're comparing to, and it's clear that this is not always reaching the optimum solution, right? Because you have this approximation ratio business going on. So I'm wondering, what how much time you give the simulated annealing algorithm, to evolve, because obviously if you give this exponential time, you should always get the optimum solution, right? But and it seems like that's what the scaling is indicating anyway. But you get like some, exponential factor improvements, which is obviously very nice. It's just, there's many dimensions in which these algorithms can be compared, and that makes it kind of difficult to understand what is really happening, right?
Right. So I was focusing on scaling to try to disambiguate what I meant. So here, what we're doing with the simulated annealing is it's not that much about computation time, like how long you let it run for 2 days straight and then you find a better solution. It's really about the depth of the algorithm. So in simulated annealing, what you'll do is to start with some random configuration, and then you define the depth of it as one instance in which you effectively go through every single spin and you try to flip it. And the rate at which you accept the flip or reject it is given by an effective temperature. So that probability of e to the negative beta delta e. So by what you have to do then is to change the procedure for the simulated annealing, because you're redefining this effective temperature every time that you go one layer deeper. And you can do this in a linear way, you can do it in an exponential way, there's many different approaches. So what we do is that we cap the number of layers for the simulated annealing at what we found to be an optimal annealing schedule. So that's the comparison that we're making. You can go to deeper simulated annealing layers, and you'll continue to get better, but there's this exponential process. I will say though, however, that here we're using this as a benchmark for us to understand the generic performance of generic algorithms, both on the quantum side and on the classical side. There are other classical algorithms that you can use that use heuristics rather than the simulated annealing, and they perform it's very hard to say anything about scaling for those algorithms, but in terms of the absolute performance for a particular system size, they do better. And that's how we find the size of the maximum independent set. Does that address your question? I'm not sure.
Can I just ask also about how does this depth compare to the quantum algorithm?
We're comparing the depth 1-to-1 here. We're using the same definition of depth. So the time that it takes for the quantum algorithm to attempt to flip all the spins is the time of a pi pulse. So we take the time for a pi pulse and we say this is 1 unit of depth for the quantum evolution. For the classical, we say it's 1 instance of going through every single spin and trying to flip it. So that's how we can put both data on the same plot.
I believe you had a question.
Alex,
Oh,
thanks for a
Hannes
nice
here.
talk. Yeah. So I wanted to ask if you tried to study the size dependent in the stimulated annealing, how many spins you are flipping and how this depends, how the speed of optimization depends on this. Because this will give you the idea how deep is this local minimum energetically.
Right. So this data contains several system sizes. And going back to an earlier point, what we found is that it is the size of it's the degeneracy of the solution what sets to first order how hard it gets. It's not the size of it. To higher orders, it's the size of the gap.
I mean more the stimulated annealing part when you flip the spins. Like, so in that case, you told that you were doing correlated sweeps, right? How many spins you were flipping in that correlated sweep?
Oh, the correlated sweeps are, you basically look at a single spin plus the ones that it's connected to, so that it's easier to flip local regions, which is again somewhat more consistent with what the quantum system is doing, right? Because there is this connectivity that is embedded in the interaction. But the layers, to what I was saying earlier, the layers are redefined by so the depth in the quantum circuit is always just given by the pi pulse. The depth in the classical circuit is given by the attempt to flip every single spin once. So the computational requirements for a single layer in the classical circuit does increase with system size, whereas in the quantum, for our definition, it does not.
Thank you again, Dr. Kiesling. So I believe now we have a 30-minute break. So we'll meet back here at 11:10 for, I believe it's Professor Weiner from Purdue University who's up next. A quick reminder that I forgot to mention this morning, if you are presenting at the poster session tonight and you forgot your poster at the hotel, please talk to David Stewart and he can help arrange for you to go get that. I think that's all we have for now.
Thank you. Good morning, everyone. My name is Ethan Dickey. I currently am researching quantum state complexity theory, quantum Turing machines, and generally quantum complexity theory, and under the advisement of Dr. Price. This morning, it's my pleasure to introduce Professor Andy Weiner. Professor Andy Weiner is the Seifert Family Distinguished Professor of Electrical and Computer Engineering here at Purdue University. And Professor Weiner's research focuses on ultra-fast optics, focusing in processing of extremely high-speed light wave signals and ultra-broadband radio frequency signals. He is especially well known for his pioneering work on the programmable generation of arbitrary ultra-short pulse wave forms, which has found application both in fiber optics and in ultra-fast science laboratories around the world. Most recently, he's been focusing in quantum optics and frequency cones. Everyone give it up for Professor Weiner.
Good, thank you. Microphone working okay? Yeah, so pleasure to have a chance to give a talk here this morning. As you can see, I'll be talking about frequency domain quantum photonics. And so unlike the previous talks, ours is not so much about quantum computing, but really the idea is how to really aimed at sort of quantum networking or transmitting entanglement, sending quantum information over fiber optic communication infrastructure, and perhaps someday, I don't think right away, but perhaps someday to assist in quantum networking or helping to distribute entanglement between shared quantum resources at remote locations. So that's kind of the long-term aim of what we're interested in. So what I'll talk about today is, I'll start with some introduction, then something called biphoton frequency combs, but we're really interested in encoding and manipulating quantum information that exist as coherent superpositions of different optical frequencies. So that's why we call it frequency domain quantum photonics. We'll talk both about the frequency correlations and the entanglement in these combs, which can not just be qubits, but also can be qudits. There's a very high potential for high dimensional quantum information carrying and manipulation. We'll talk about encoding those states. And then as one example, we do a lot of work pushing towards higher dimensionality, but as one example, I'll talk about some new work where we can use these photonic states to measure delay changes sort of at the single picosecond level, much faster than sort of the typical 100 picosecond response times of single photon detectors. Okay, so some acknowledgements. A lot of people have been involved. We've got involved in sort of quantum optics in my group first about 10 years ago. Previously, I had worked and still work in sort of manipulation applications of very broadband light, mostly short optical pulses. But so I show some of the graduated students. On the current students, the top three, Suparna, Alex, and Kartik, are the students currently doing quantum photonics in my lab. Some collaborations with some Purdue faculty. We've had a very fruitful collaboration with some of the people shown at Oak Ridge National Labs, particularly Joe Lukens on something called quantum frequency processing. Our work is actually not part of the Quantum Science Center, but we're happy to be partnering with on a quantum networking project under DOE that Oak Ridge won over the last year. To use some of these technologies, some collaboration, some devices from EPFL as well. Okay, so the introduction, maybe some of this will be too simple, but perhaps will be useful for someone here. But in terms of, just introducing bits and qubits, and in classical information, I have the analogy with a coin. If you flip it, you get heads or you get tails. It's definitely one or the other. We don't talk about superposition states of heads and tails, but in quantum information with qubits, we certainly do. So superpositions, in fact, coherent superpositions where phase matters between the two states. And I make the point that we have phase matters and interference phenomena. This talk will be full of interference phenomena involving different optical frequencies. Okay, and there at the bottom, I talk about higher level encoding. I already mentioned higher dimensionality. So we could then consider dice as opposed to coins as our classical analogy. They have 6 sides, so that's more than 1 bit worth of information per dice flip. And sort of already in both wireless and optical communications, sort of encoding information in higher levels is common. And so advanced fiber optic communications for quite some years now have gone with various advanced symbols that encode many bits per symbol of light. So potentially we might be interested in something like that in the quantum regime as well. So going beyond sort of qubits or qudits, we're very interested in entanglement. Entanglement is viewed as a primary resource for most quantum tasks. Okay, and so if we look at the coin analogy, we can have a case, for example, classically, Alice and Bob both have a coin, they flip it, the results are independent and uncorrelated. But in quantum mechanics, we can have entanglement where when Alice or Bob flip their coins, the result is still random or unknown. But what is known that if Alice, for example, with the state shown here, gets a head, then Bob gets a head. If Alice gets a tail, Bob gets a tail. That's the state written there would be one of the 4 Bell states. So there are other possibilities. But we have these very strong non-classical correlations. They're non-local in the sense that they can persist even at a large distance. Okay, again, phase is going to matter when we write these states. So it allows, here we'll hear 2-photon quantum interference experiments. Okay, where you manipulate phase, you change coincidence probabilities. And I would point out as also, it's not limited to qubits, but higher level dimensionality entanglement is possible, which we'll explore. So just a little bit of introduction to sort of photons. There are many interesting and useful degrees of freedom with photons, many of which have been very heavily explored. Polarization has been explored as to represent qubits for at least 30 years. This is limited to sort of 2-level quantum information, but one can have time bin encoding with 2 or more bits where the quantum state is a current superposition of many different locations in time. We can have path encoding. That's particularly interesting and has been explored in sort of large-scale silicon photonics, where you can make different integrated waveguides as parallel paths, and the light will exist as a superposition of existing and different waveguides at once. And orbital angular momentum has been very interesting, and is really, people have explored high-dimensional quantum information. Until recently, with some of the work over the last few years of our groups and a few others, optical frequency had been sort of, I'd say, underexplored in the quantum sense. One reason for that is if you think of frequencies existing as, in our case, tens of gigahertz apart or farther, it's hard to make interference experiments to measure what happens. So I'll show you some of the techniques that lets us go over that obstacle. And so we'll be really exploring quantum photonics and now this optical frequency dimension. Okay, so a little bit about why we're interested in frequency, other than it hadn't really been done before. And I'd say the main inspiration is really the remarkable technologies that have been developed in classical fiber optic communications, exploiting wavelength division multiplexing. Okay, and so it's well known from that work that frequency has a good degree of freedom. It's extremely stable when you transmit it over fiber. And one can explore many frequencies in parallel to achieve many terabit per second classical communications. And so the thought is it wouldn't be exactly the same, but we somehow exploit this vast bandwidth that can be supported by fiber optics in the terahertz regime to better transport quantum information over fibers and to establish technologies that could be useful for quantum networking. Okay. Some of the other reasons are the potential, as I mentioned, for high dimensionality. It really comes very naturally, as you'll see with frequency. There's interesting technologies allow us to perform routing or do frequency-based separation of frequencies to different spatial paths. You'll see a little bit of some examples of doing parallel manipulation of quantum states, parallel processing in the frequency domain. There'll be, this actually can work fairly well in integrated photonics. You'll see some integrated photonics here, much discrete photonics, but I think there's interesting paths to more fully integrated systems and other things. Okay. A point I want to make is classically, the multiple frequencies of light and wavelength division multiplexing are principally used to delineate different data channels. They tend to be independent. phase between them doesn't matter, and so forth. And we'll be showing a little bit of work kind of along those lines. But for the most part, we're interested in then going beyond that and encoding quantum information coherently across different optical frequency slices, if you will. Okay. So a little bit on just sort of some of the classical tools that you'll use. The one on the top, the pulse shapers, are one of the things I'm well known for in my early classical ultra-fast optics days. That was a long time ago. But so we have the top left something called a pulse shaper. The motivation in those days is femtosecond pulse technology was relatively new. You know, we had these incredibly short pulses, but no way to electrically control them or to sort of carve them into new waveforms because the time scales were much too fast. And so the scheme shown in the top left is a frequency domain approach. The pulses get shorter and shorter as more and more bandwidth. Here we're talking 100 femtoseconds and up to 10 terahertz of bandwidth. And so by sending the short pulses at a spectrally dispersive element like a grating that separates different frequencies of light, focusing them with a lens, you could sort of spread out or disperse your frequencies. That's the front end of a spectrometer. That's been known for a long time. But the innovation was to put in a spatially patterned object, which soon became programmable modulator arrays or spatial light modulators, to impart different amplitude on phase on the different frequencies that were spatially dispersed. After using more optics to put the frequencies back together, one could transform these short pulses to new waveforms, a few of which are shown here, by a Fourier transform process. The spatial amplitude and phase that was placed onto the spectrum, once the frequencies are recombined, now becomes a new time waveform. So that's sort of Fourier synthesis. What we're interested in here is essentially an arbitrary amplitude and phase filter that we can program and change these coherent frequency superpositions. And sort of an example in top right is, for some years now, there have been nice commercial implementations. These are closely related, and this was a commercial driver to something called wavelength selective switches, which are used in WDM to programmably switch different frequencies of light or wavelengths onto from different input fibers to different output fibers. And so those don't manipulate phase. The pulse shapers as shown here do, but you can also configure these with multiple output fibers, so you can do both frequency-dependent phase and amplitude filtering and routing of different wavelengths to different fibers, and we'll see a little bit of that. The other tool is the phase modulator. So we're going to need ways to mix frequencies, much as the way one uses beam splitters to mix different optical paths. And so if you drive a phase modulator with a sinusoidal signal, these are telecom phase modulators. They can be driven at tens of gigahertz. You generate frequency sidebands. For example, in the bottom right, as you increase the phase modulation depth, you can make these sidebands that essentially will you mix different frequencies. So this will be our tool for mixing frequencies. Okay, a little bit more about the pulse shapers. We're going to be doing a lot of phase control here, spectral phase control. This idea is we can put in approximately arbitrary phase onto the spectrum. If you want to add, there's a relationship with frequency-dependent delay or dispersion. So the derivative of the spectral phase gives you temporal delay. And so some classical examples shown here. On the left is a case where we have femtosecond pulses. By reprogramming a pulse shaper with different linear phases, the derivative of the linear phase is delay. You can move the pulse back or forward in time, no moving parts. If you put on a quadratic phase as shown on the right, that gives a linear frequency-dependent delay. You can spread the pulses out, or if you have a chirped or frequency modulated pulse coming in, recompress it. So we'll do some analogies with that in the quantum regime. One more example on sort of dispersion control, again, classically. Here is a case where we're sending short pulses into fiber optics, about half a picosecond long. The pulses spread very rapidly. So in this experiment with a couple kilometers of fiber, we spread 100 times, a few hundred times. And then using special fibers that the industry sort of created back in the late 1990s to support more fiber optic bandwidths, you have fibers that have the opposite sign of dispersion. The slow frequencies in one fiber are the fast frequency in the other. They can be compressed, but usually not exactly. And so we were interested in using pulse shapers as programmable spectral phase equalizers to dial in some spectral phase that fixed whatever distortion was remaining. And so this shows an example with a half a picosecond input pulse. It spreads a few hundred times, not shown. goes through the special fiber. We get the top right 770 femtoseconds with the tail. It turns out there's a cubic phase effect. So we can program that in and the pulse gets restored. So again, there'll be some notions of doing similar operations on broadband entangled photons. Okay, let's go on to really talk about the biphoton frequency combs and the frequency correlations and entanglement. Okay, so how do we generate these? Nonlinear processes, either parametric down conversion, which is, again, been well known for about 30 years, or spontaneous four-wave mixing, which is appropriate for on-chip microresonators, and also has been increasingly well explored for probably 10-ish type of years. Okay, so on the parametric down conversion, one goes into a second order nonlinear crystal with a high frequency photon. I call that 2 omega naught. And most of the pump photons just go right through, but occasionally there's an interaction, and those photons essentially split into 2 daughter photons, a signal and idler. The individual frequencies are randomly distributed, in our case, over sort of the full light wave band, about 5 terahertz wide, but there's strong frequency anti-correlation, so the photon energies are preserved. Okay, and so you get curves shown over on the right where if you measure the signal frequency, idler frequency, they're widely distributed, but they have this tight sort of anti-correlation. And it turns out that's a coherent superposition of different frequencies. There's a Fourier transform relationship that allows you to predict what's the time correlation function. The photons come out, these events happen at random times, so you can say the signal photons happen at random times, but the idler photons then happen with tight timing correlation that goes as 1 over the total bandwidth. So in some of the experiments here, that could be 100 femtosecond type of timing correlations. That's kind of a broadband process. If we go to a continuous frequency process, if we go to the microring resonators, now it's a chi-3 nonlinearity. But if you think of a pair of photons coming in and sharing their energy, at that point, they divide the energy into signal and idler photons and the same sort of anti-correlations. With a difference here in a resonator, and this really happens efficiently only at an evenly spaced set of longitudinal modes, which in our case will be tens of gigahertz to a few hundred gigahertz separation. Okay, so it's kind of generating this discrete frequency entanglement. And the parametric down conversion we'll use also with periodic spectral filters to carve it into discrete bins. A few examples, we're looking at frequency correlations right now, not entanglement. For entanglement, we're going to have to talk about phase. But for example, some of our early results with 2 different micro rings, a sort of relatively small one shown on the left, about 380 gigahertz spacing between longitudinal modes. But if you look at the spectrum that's generated, there's a strong pump even after attenuation. And sort of, you can see sidebands on either side. Those are the signals and the idlers. If you now use a pulse shaper to programmably say, grab 1 low frequency photon, 1 high frequency photon, change which one, send them to single photon detectors and look at coincidences, you can make what's called a joint spectral intensity blot. And then you'll see it's a diagonal or really anti-diagonal distribution. So that's the frequency correlations. On the bottom just shows some of the examples of the sort of nanosecond scale coincidence peaks between the signal and the idler. 2 of them are the matched signal and idler. One over sort of towards the right are the wrong mismatched pairs. You get essentially nothing. And then over on the right, there was a sort of a larger resonator, which has closer frequency modes. These are about 50 gigahertz. And there with some dispersion engineering, we're able to get a broad bandwidth. We can generate up to about 40 frequency correlated signal and idlers. So that suggests really nice potential for high dimensional quantum information. Okay, another thing you can do, again, this is related to frequency correlations, none of the entanglement or the phase yet. We can use dispersion as a tool now. So if you take your light from these microring resonators, here we're taking 4 signals and 4 idlers, okay? Send it through some dispersive media. These are chirp fiber Bragg gratings that have quite a bit of dispersion or frequency dependent delay. You can impart different delays to the signal and idler. They're all randomly tied, but they have correlations with respect to each other. And so if you put these dispersive elements in only one arm or the other, signal or the idler, you separate these peaks out in different delays that you can actually measure, sort of mimics the actual spectrum. But the interesting thing, if you put the dispersion in both of them, it turns out with opposite signs, the signals are all delayed in various ways, but you put them back up so they all arrive relatively at the same time. So over on the right, you get a single peak again. This is called non-local dispersion compensation. It's really a foundational idea dating back from the early 90s and time frequency entanglement, but shown here kind of in discrete, sort of over a broader bandwidth than normal, I would say, with kind of discrete bins. Okay, so we're going to talk a little bit now, all right, a little more about our state. So look about on our top left, this is my picture of what I call a biphoton frequency comb. It has these signal and idler photons at high and low frequencies respectively. I draw these solid lines here that are illustrating the tight frequency correlations. And then there's going to be a notion of these dashed lines are going to be a phase coherence between photon pairs. We'll get back to that in 4 or 5 slides. We're going to need that for entanglement. But I want to talk a little bit about the polarization state here. So for most of this talk, but not the next 4 or 5 slides, we'll be looking at polarization sort of like in the top right. We'll just be generating linear polarization. There's no information there. All the photons have the same polarization. And we'll be working on manipulating frequency degrees of freedom. However, for the next few slides, we're going to use hyperentanglement. And so, generating a polarization entangled light, again, has existed, something people have known about for a long, long time. Okay, and so you can generate these photons, for example, in superpositions of 2 vertical photons or 2 horizontal photons, or 1 vertical photon, 1 horizontal, but you have quantum state which is which, okay? And so that's a way of generating light with polarization information that you might send over your fiber network. Okay, so let's use that for a little bit together with frequency correlations. So some work we've done sort of was following on this nice work from the Austrian group of Rupert Urson, who was talking about entanglement-based wavelength multiplex quantum communication network. And the idea is that under the right circumstance, you can generate very broadband photon pairs. This is in parametric down conversion, filling much of the C band. And if it's got polarization entanglement, you can look at different frequency slices, and they'll each carry polarization entanglement. So you can use different frequency slices as a resource for other purposes, and in particular for routing entanglement. And so what they did, there's this fairly complicated setup in the top right, but they generate these broadband photons. They use a series of WDM filters, essentially filters at fixed wavelengths that are an available technology. And they use them to grab different frequency slices and to route them in their original experiments to 4 different users. And you can sort of see at the bottom left some frequency assignments. There's 12 frequencies or wavelength bins that are used in these experiments. So you need kind of a lot of filters, okay? But what the idea is that physically what you're doing is this hub and spoke thing. You think of a central generator with entangled photons, but then you can, by sending different wavelength slices out, physical fiber to different users, you can distribute entanglement sort of in parallel among all user pairs. Logically, what you get is the sort of mesh network where everyone is going to share entanglement with everyone else. And so that seems to be quite attractive. So they did some very nice work there. Again, frequency is used as a resource to sort of do routing. Your polarization carries the entanglement. What we got interested in using these pulse shapers, these wavelength selective switches. So instead of having a bunch of fixed filters that gets very complex to deploy as you go to more and more users, to do something programmably. And so the idea is these wavelength selective switches in the same device, one can essentially programmably grab different frequency slices and send to different output fibers. Okay, and so in the top right, we did some experiments. You can't really see the spectra, but the different color codings say different ways we could program to grab different frequencies and to send them to different fibers. And we could use that to start to play with what you might call quality of service, or try to equalize that. Here we had some good detectors, some superconducting detectors, some bad detectors, some APDs, and to try to account for that. For example, to try to give everyone the same coincidence rates, or to maximize in some way. Another interesting thing is loss here is very important. They're all kind of our quantum technologies, and these wavelength selective switches have typically 5 or 6 dB of loss, so that's not so good. Okay, but these DWM filters have some loss. It kind of varies depending reflection, transmission, and so forth. But as you start to put more and more of them in the network, the loss adds up. And so we did some loss estimates. And basically with the programmable wavelength selective switches, you have a fixed loss that doesn't change until you have the maximum number of output fiber ports, which can be up around 20 in commercial devices. So that's kind of a solid 6 dB. You look at the estimated loss with the DWM filters and cascade more and more to get more users. If you go up to like 16 users, you can have a large variability in loss, but you can get up to many, many tens of dB. So there's an interesting feature of sort of a loss which over a certain range is independent of user scaling, which is kind of novel. So we published our first laboratory-based work on this about a year ago. There's been some rapid follow-up, some experiments in France that stayed in the laboratory but added sort of 25 kilometers of fiber and had broader band sources than we do, so it can scale up to a few more users. Actually, with our collaborators at Oak Ridge have actually taken this idea and done a first implementation in sort of using installed fiber to connect different buildings over about a 2 kilometer scale. And so that's something we're very interested in. They're very interested in kind of further using to test out these techniques. So a little bit about scaling, I think is kind of interesting here. And so how many users can you have? And so let's assume we can use the full light wave C-band. That's about 5 terahertz or 40 nanometers. Let's assume we can have 12.5 gigahertz spectral slices, which is about twice the minimum resolution of these wavelength selective switches. If you do that, you can get about 400 spectral slices. Now, the number of slices you need, I put that up at the top, you basically need n-1 spectral slices, right? And it's the number of users. And so this would get you up to about 20 users, which, as I said, is kind of the number of output ports available. And so, I think it's got some, interesting potential, at least over the near term, to push the state of the art. Let me come back now to entanglement. And so this is a similar slide as I had before on the left, but I'm asking, okay, how would we look at phase coherence between different photon pairs? And one way is I said, well, if we ask what's the time correlation function between these photons, you do a Fourier transform on the entangled photon wave function, you get something along the right. You expect to have these sort of periodic peaks in the timing between signals and idlers. So you could look for that. Problem is, we're going to look at time scale, frequency scales of tens of gigahertz between frequencies. These peaks will be tens of picoseconds for most single photon detectors, and certainly the superconducting detectors we have, which are 100 picosecond scale. It's too fast and you can't measure it. So I'm going to need some other techniques. And it turns out if you ask what happens if I don't have phase coherence, these beats kind of wash out. You'll get sort of the solid envelope shown here. And so if you can't measure fast delays, you can't distinguish between mixed states, and pure states where you have entanglement. Okay, so what do you do? Well, what we did, and it turns out a group with Roberto Marandati up at Canada developed essentially in parallel independently, is to use these phase modulators. So we're going to come in with our biphoton frequency combs on the left. We're going to use pulse shapers to choose different frequencies, impart frequency-dependent phases as we need to do quantum interference. And with a phase modulator, we're going to mix frequencies. Okay, we're going to use another pulse shaper as sort of a way to just sort of select one signal, one output frequency, and look at coincidences. And then on the bottom, it's sort of, the pictorial, we have the blue lines are the starting frequency bins that have, we presume, some entanglement. After phase modulation, we create, and here we're RF modulation at half of the spacing. It could be at the same spacing, but here we do in half. So we generate these green sidebands that didn't exist before, and all of those can have contributions for two or more parent frequencies. And so on a single basis, photon basis, it turns out there's no interference. On a 2-photon basis, there is, and we can control that by playing with the phases in the first pulse shaper. And so we'll grab a single new sideband on the signal idler side, send those to detectors, and we'll see quantum interference. That's the test of entanglement. Okay, so here's our first experiments using parametric down conversion with a periodic filter. So we generate these frequency bins, 36 gigahertz apart, about 12 gigahertz wide. And in this slide, we're going to pick 2 signals and 2 idlers, go through the procedure I talk about, and look at coincidence counts as we play with sort of the phase on the input spectrum. And the bottom line is we can get these deep interference in the coincidence counts. This shows examples for 2 different pairs, the first and second, or the second and third. And it's deep enough that it verifies entanglement. And these were with our kind of bad detectors or APDs we had at the time with better superconducting detectors, you can start to get much higher quality data. You can also go on to higher dimensionality. This shows an example with 3 signals and 3 idler bins, which is the farthest we've taken in this particular experiment. And the phase we put on are these, as illustrated here, are these linear ramps, okay? That's sort of an idea that came out of Nicola and Jason's group with time domain entanglement from the early 2000s. Turns out those ideas translate. And we can generate over in the bottom right now these sort of sharpened up 2-photon interference curves. We can prove entanglement. It's kind of like if you're doing classical mode locked lasers, you add more and more Greenwich frequencies, you get shorter and shorter pulses. Mathematically here it's similar, but now they're tighter and tighter traces, in these quantum interference. One thing that wasn't understood, certainly by us, I think, or any of the other groups in the beginning, is when putting on these linear spectral phases here, I explained before, linear spectral phases delay. What we're actually doing is we're kind of varying the relative delay between signal and idler. And I'll come back to that at the end of the talk, showing how we use that for measuring physical delays with very high precision. We can also do this with the microring resonators. So here, these are lines that are 50 gigahertz apart. They're much narrower now, about 100 megahertz wide. And here we're showing a 2-dimensional entanglement, so the same sort of traces that I showed before. And we can also do fancier stuff. Here's some more optimized microring resonators from a collaboration with a group in Switzerland. You can see some of their nice chips on the top. Here we're making frequency correlations out to about 50 bins, where we stop measuring. It takes a while. Okay, so there's potentially very high dimensionality. And we're actually going to resolve the temporal beats now. And here the trick is, instead of phase modulating exactly at a matched frequency, we offset a little bit. We call that a Vernier effect. We offset the phase modulation from 1 gigahertz compared to the frequency bin spacing. And in that way, we can actually sort of down convert the beating that was too fast to a slower beating that we can resolve with single photon detectors. I won't go into details, but here's some example, again, of sort of characterizing and showing entanglement at the 3-dimensional level. Okay. One other thing I wanted to talk to here is, again, to dispersion. So we can look at the effect of dispersion, taking these frequency entangled states and send them over to fibers. They're giving us frequency dependent delays. That's somehow going to change the quantum state. And we can actually measure dispersion. And so what's showing here is a series of measurements where we take 2 signals and 2 idlers. We measure coincidence counts, either for a fixed frequency bin pair as a function of the phase that's applied, or for a fixed phase, we can look at different frequency bins, first and second and third and fourth, compile the results. And without going into the details, we can pull out the fiber dispersion from this and hit the specified value to within about 1%. So it's kind of interesting. We measure dispersion using this 2-photon interference. I don't think this is going to replace any of the well-developed classical tools that do this, but it's kind of interesting to note. But maybe the more important thing is we can understand very well what the effect of these frequency bin and phase effects are on these states that they're going to see when they go through optical fibers. Okay, I'm going to go on to another topic here, just checking how I am on my time plan here. Not as bad as expected. Okay. So we've talked a little bit about sort of the entanglement in these photons. What about gates? How can we manipulate the quantum states? So I'll talk about here is really sort of single photon gates. How do we manipulate, single photon frequency qubits? We'll also see some on Q-trits, 3 dimensions. Okay, and so this is following a proposal that came out of our colleagues at Oak Ridge, Lukens and Lugovsky, and something they call the quantum frequency processor. So it's going to consist of a phase modulator, pulse shaper to do spectral phase, and a phase modulator. Same elements we use for entanglement measurement, but exactly flipped in all the orders. So it's kind of a complementary set of ideas. And what's happening is shown in the second line. Suppose we come in with a frequency qubit. So frequencies represented A0, A1. This looks like space here, but really think of this as sort of a frequency axis going horizontal, vertically. Okay, it's going to go through a phase modulator. It's going to make a series of sidebands on both frequency bins. It's going to spread out of the computational space. Phase modulators don't give you sort of contained shifts. They give you sidebands that spread. Okay, so that would be kind of a problem for only interested in 2 frequencies. But really the innovative idea there is that, well, if you play with the spectral phases and go through another phase modulator and choose all the phase modulation waveforms correctly, the phases correctly, you can make controlled operations where almost exclusively the frequencies come back to the desired computational space. Here the frequencies A0, A1, but you can have a transform in the amplitudes and the phases. So you can change your quantum state. Okay. Now the contrast is that if you look at say in integrated photonics where people have looked at path entanglement, there's this algorithmic approach, from Rex Zeilinger. There's been some updates on this, but basically the idea is that you can construct in a determinate, in kind of an algorithmic way, transformations in higher dimensions, and they're based on a series of 2x2 interferometers cascaded together with controllable phase shifts. And so this is used in some of this state-of-the-art, or probably at least a couple of years ago, close to state-of-the-art work on sort of a 15-dimensional waveguides and doing manipulating spatial superpositions done from a group in Bristol. So this is algorithmic, the quantum frequency process shown here again. There aren't algorithmic approaches that are known at this point, so it's all done on basically computational optimization of waveforms. But it's interesting because it allows you to accomplish, some transformations in a sort of set number of components. You can add phase modulators, you can add depth and pulse shapers, but you can do a lot more than a single interferometer and phase shifter. So here's some examples. This is frequency qubits. This was now joint work that our group and the Oak Ridge group did to do the experimental demonstrations. So what's happening here, this is going to be a Hadamard or 2D discrete Fourier transform or a frequency beam splitter. And we're interested in doing a 50-50 split. So if one frequency comes in, you'd like two. If two frequencies come in, you'd like with the right phases to recombine them into one. So on the left is top left, single frequency input. You come in with the blue, you get two equal reds. If your eyes are good, you can see a little blip outside of there. And so that's here we have about 98% or something probability of keeping the frequencies where we want them, okay, which is pretty good. And if you come in with a superposition at the bottom left, there's two blue inputs. With the right proper phase applied, they can be recombined into either of the two outputs, okay? So that's a frequency beam splitter with a single photon. What's interesting here in these setup, it can support multiple photon frequency qubits that are separated at different places in the frequency axis. So on the right, we're coming in with one of our entangled pairs. The entanglement is now, it's all the same polarization, but we have two frequencies over here for the signal, two frequencies here for the idler. We're going to work on them essentially independently. They go through the same phase modulator and pulse shaper. Pulse shaper can be programmed with different phases though. And so over on the right, we can look at their coincidence counts, either starting from the top left with the identity. So we arrange it so nothing happens. The frequency anti-correlation. On the two ones that are spread out, we do a Hadamard in one arm, not in the other. So we're using essentially different bases. We mix the correlations. Okay, and then on the bottom right, if we do a Hadamard on both, we can actually flip the correlation. So that's expected and can be used also to estimate something about the quality of the gates. Okay, how does this work a little bit more? So what's showing here is just what the spectra look like on a single photon basis. On the left is if we have either the first frequency mode 0 or 1, but they go through the first phase modulator, you see they get spread, okay, just as described before. But if you just put two phase modulators back to back with opposite phasing, which is, you can recombine the frequency just how it started very effectively. Okay. The difference is now by putting a pulse shaper in between and controlling spectral phase, you can engineer what manipulation you get. This one is just the identity. That's just a little bit how it works. So we can also do 3 dimensions. And so this is showing some of the phase modulation drives in the top left, and after what spectral phase we use. We're driving with 2 RF harmonics now, so that's a new degree of freedom. As you add RF harmonics, you can build complexity into your transformations with the same hardware. And so there we're doing the frequency beams tritter, we call it, or 3-dimensional splitter, or 3D discrete Fourier transform. So bottom left, we can come in with any of the 3 different input frequency modes, split them into 3 approximately equally, or we can come in with superpositions with proper phasing. We can get any of the kind of parent frequencies back out. So that's working. That's single photon. Again, we can do entangled photons, similar sort of thing. There's more possibilities now, but we can transform these correlations between the photon frequency in ways that are expected. The one other thing I'll talk about in this topic, a little bit about how it might tie in to optical networking. So as shown here is kind of the notion of using entanglement swapping and belt state analysis as a way to sort of try to distribute entanglement over increasing distances and try to overcome loss. Okay, so again, this is a well-known concept. It's still kind of hard to implement, and it's not one we invented, but maybe we can contribute towards implementation. And so let's focus sort of on the left where it says entanglement swapping. The idea is, suppose we come in with our photon pair generators. Here it's going to be frequency qubits, from two different sources. And let's say we send a signal to the left, the idler to the right, and we're going to do a bell state analyzer. So we have some hardware that will click when those photons happen to match a particular bell state. They're uncorrelated to start with, but once we do a measurement, we essentially do induce correlations. And if one can do this, get the bell state analyzer click, that now, at that point, we now have correlations and entanglement that didn't exist before between the signal all the way on the left and the intermediate idler. So that would be an entanglement swap. And then the idea is you can kind of cascade this or have a chain, and in the end, sort of create entanglement all the way on the left and all the way on the right, even though you didn't have initial entanglement. Okay, now to really do that effectively and get gains here, you need some kind of multiplex. You should actually have multiple streams of qubits going on each link. So the idea here is perhaps we can use all these frequencies available to somehow do that. But then if you do that, you have the problem you've got spectrally distinguishable photons. Usually bell state analyzers work on indistinguishable photons. So what I'll tell you about next is some recent work showing how you can maybe start to be able to handle distinguishable photons here in frequency and still make this work. Okay, so the idea is the left shows, again, an approach that's been known for quite a number of years of how you would make a bell state analyzer. In this case, for two photons with have polar quantum information coded in polarization coming on different spatial degrees of freedom. So you go to a conventional spatial beam splitter, it's 50-50, you mix them, and then you polarization resolve the output and look for clicks. And there's 4 possible bell states. You can't get them all, but with this sort of configuration, you can know whenever 2 out of the 4 came in. Okay, and if that happens, you can use that, for your quantum networking, entanglement swapping, for example. So it turns out there's an analog of this in the frequency domain, which I attempt to show on the top right. So imagine that instead of 2 spatial modes, we have these 2 red photons in one part of the spectrum, the 2 blue ones in another part of the spectrum. Each of those is a doublet, so it's a frequency qubit. And it turns out instead of having a spatial beam splitter, we like a frequency beam splitter. Here, the way the frequency beam splitter should go is it should mix A0 and B0 and A1, H1 and B1. So it's going to be 2 interleaved atomars now. So we can, with a small change in what I showed before, it turns out we can implement this. We're going to look for coincidences, and when we get the right coincidence pattern, we can distinguish 2 of the 4 frequency bell states. I won't go into details, but it turns out there's some data there that shows it works pretty well, about 98%. So there's certainly a lot more to do to sort of extend this to many, many frequencies if you really want to take use of the fiber optic bandwidth. But it's a start and points to some of the ways you might be able to use frequency as a resource for these type of networking applications. Okay, so last topic I'm going to speak to here. We're okay. Is just one example of what we're doing to sort of push towards higher dimensionality. So go beyond, try to start to go well beyond the 3 dimensions that I showed you. And what we're going to get out of this is we call quantum delay metrology at the single picosecond level, or essentially being able to measure changes in signal and idler arrival times, time scale that could be 30 or even approaching 100 times faster than the single photon detectors, okay? It's not limited by the single photon detector response, which is kind of an idea, kind of a classical ultra-fast optics, or, been much development in how to measure ultra-short pulse signals and ultra-short pulse measurements, despite always being limited by detectors that were, by definition, slow compared to the time scale of your experiments. So we're going to go back to this sort of same picture that we used for kind of entanglement measurement, coming with a biphoton frequency comb. The first pulse shaper will select different signals and idlers. Here's going to be numbers like 9 signals and 9 idlers. So we're going to go up to 9-dimensional kind of systems. Apply appropriate spectral phases. As I mentioned before, the applied spectral phase, if it's linear, is the same as actually physical delay. So we're going to move and bring in physical delays now. It will have the same sort of effect. And that was sort of a new insight that kind of inspired this work. Okay, we're going to mix frequencies with our phase modulators. We'll select a particular signal frequency and idler frequency after doing all this and route them to single photon detectors. Look at coincidences and show that's a very sharp function of delay. What are some other points? How can this work? Well, one of the point is the RF phase modulator, by definition, is a clock. It imparts a time dependence and somehow creates a condition that allows you to make, time-related measurements. Okay. The other thing I'll point to is this can be non-local, so your photons don't have to interact with each other at the end. So they could be, to Alice and Bob that are separated by a fiber for networking applications. It's unlike techniques like Hongo-Mandel that gives you very good delay sensitivity, but absolutely requires the photons come back together. So it's inherently a local type of measurement. So sort of the non-locality is new here. Okay, let me try to explain how it works. Top left. So I'm showing pictures for 9-dimensional signals and idlers that we presume to be entangled. Top left. Now we're going to mix those with a strongly driven, sinusoidally driven phase modulator, which can certainly mix, a single phase modulator can probably mix about 20 frequencies, if you really push it to sort of the limits. But so we're going to kind of mix these all in some pattern. Then we're going to pick out a single signal and a single idler, in our case, the central one, and look at their coincidences. Okay, on top right shows what you would get with equal mixing coefficients. So if you somehow equalize it, this won't happen in real experiments, so that all the sort of lines connecting the different frequencies have equal amplitude, then you get the top right. And it basically shows as you increase the dimensions with different colors from 3 dimensions, 3 signal bins, 3 idler bins, up to 11, what happens, this is showing delay over one period of the RF phase modulation. Okay, it gets narrower and narrower. Okay, and that's the idea to exploit that. As it gets narrower and narrower, it's giving you timing or really delay resolution. Okay. Bottom left is showing what happens if we don't have equal mixing coefficients. So phase modulation does not give us equal mixing coefficients. They're Bessel distributed. And but so what happens if we kind of look at those sort of coincidence curves versus delay for increasing modulation depth, they get narrower and narrower. At some point they saturate and you lose counts. And that's when you're phase modulating so hard that you're generating frequencies outside of your 9 signals and idlers. So there's some optimum that tries to keep most of the light within the frequencies that you're using, but otherwise you want as much bandwidth as possible, okay? And so on the right sort of shows the mixing coefficients for what we felt was the optimum in our particular experiment. So it's not particularly equal, but it still does a very nice job in generating these narrow peaks. Let's move on to some experiments. So the first one is doesn't have to be local detection. We're going to look at non-local, but the first one happened to be a local geometry setup. So we come on, we're doing parametric down conversion sources here that we use a pulse shaper to carve into bins. We can also play with phase there if we want. And we're going to separate the signal and idler, high frequency bins versus low frequency bins. And one of them we're going to put through a physical delay line. We're going to bring them back together, go to a phase modulator, and then look at the coincidence after separating frequencies. So another cartoon, sort of similar cartoon on the left, but with a physical delay line, at least for some of the experiments. Here's what we get. So here, let's see, we had 25 picosecond frequency bins, a 40 picosecond RF period. We get a delay peak, a little under 4 picoseconds long. And if you look at the signal to noise in some sense, you should be able to look at timing delays. Again, these are real physical timing delays down to the few hundred femtosecond level. So, 30 or more times better than our single photon detectors. We also compare there an experiment where we do a real physical delay with a delay line versus fix the delay line and play with different linear spectral phases. Results are essentially identical, and that's sort of another reinforcement of the idea that a spectral phase, even with no moving parts, is a delay. On the right, we're just sort of expanding the time scale over which we measure this, and we see that this is periodic with the period of the RF clock in some sense. And so this is both going good and bad. The good part is, unlike what most white light interferometry classical techniques, if you want to measure delay or some other property, you have to bring the two paths into matching delay, otherwise they never interfere. Here you can make the path lengths microseconds different. Well, I'll show that. Yet they still interfere because it's got this periodicity. The downside is that if you can get fine delay, but if you want kind of global delay, you need to disambiguate in some way. And there are some ways to do that. We've done some of that. I won't go into that. But this is the way how the thing works. So now we do a non-local experiment. Looks kind of similar up at the top, but the difference is we separate signal and idler. We send one of those into a fiber spool. I forget how long that is, what it was, but the delay must have been about a kilometer because it's about a 5 microsecond delay, if I recall correctly. Okay, and then we go send signal and idler to separate phase modulators, separate single photon detectors. So they could be, physically a kilometer apart. Okay. Otherwise, we change the RF frequency and the frequency and spacing a little bit for this experiment, a little bit higher. But otherwise, it's the same sort of idea, now done non-locally. And we see similar things. So the top left is showing what happens without any fiber. Okay, under 3 picoseconds here, we got a little bit better. We go through, 310 meters fiber. That corresponds to a microsecond and a half. Those are the correct numbers. So we get some sharp features for distortion. That's dispersion in the signal and not in the idler. Okay, so we can understand that. It matches the theory. But we can also, as shown before, we can compensate that. So if we dial in some extra spectral phase, we can do the non-local dispersion compensation. We end up with a trace that's sort of the same as without the fiber, and we can get sort of single picosecond level delay resolution. And so with this non-local detection, one of the things we're interested in going back to quantum networking is sort of the synchronism is a big problem that people are trying to chase down for doing quantum networking. So sort of the time resolution that people think of in many cases as being required to manipulate these quantum states is much faster than classical Ethernet type of things. Okay, and so this I'm sure there'll be classical solutions that contribute, but it also suggests that the entangled photons themselves can be used not as only as information carriers, but as diagnostics for very fine scale synchronism. So that's an idea we're pursuing as well. So I'm going to finish up quickly here. One summary and discussion. So hopefully it's been clear. I've been talking a lot about manipulating and entangling quantum information as coherent frequency superpositions, both as two-dimensional systems, but higher dimensional systems. We're interested particularly in applications of quantum networking. We think that's probably the best place on a short time scale where we, not so short, but we may be able to contribute to sort of quantum technologies. One other point I wanted to make is what we've done here is a little bit of integrated photonics, but a lot of discrete photonics. And I think there's really opportunities to really advance these type of ideas using integrated platforms. So on the left are sort of the micro-ring resonators that for pair generation that I've talked about. In the middle is some work from Marco Lonkar's group at Harvard, which is making these coupled rings they call photonic molecules in electro-optic thin film lithium niobate, and can use those sort of as on chip as two-dimensional frequency splitters and swappers, making Hadamard and other gates. To my knowledge, this has been demonstrated at the classical level and not yet at the quantum, but one expects it to work, at the quantum level. So some specialized functionalities might have completely on-chip implementations. On the right is some work we're involved in with a number of collaborators, Oak Ridge, Air Force Research Labs, RIT, and really trying to use AIM photonics, using silicon photonic foundries to really put on, multiple phase modulators, integrated photonic versions of pulse shapers, and really to look at the quantum frequency processors, entanglement measurement schemes that I talked about, and see if we can implement it all in integrated photonics. So we've worked a lot on that. Hopefully within the next year, we'll start to have some interesting results to put out there, but we'll see. But I think ultimately that should work as well. And so finally finishing up, again, a lot of people involved. This is a picture of my current group, but a lot of students have been involved, a lot of collaborators, and we've enjoyed at different times support from a number of different funding organizations. And so thank you for your attention. Happy to take questions if there are. I think that's someone there, maybe there.
Thanks for the great talk. I have to ask if you have any thoughts on microwave to optical transduction and if maybe some of the techniques you mentioned towards the end might help in debugging building quantum networks, even of superconducting qubits.
Yeah, and so again, if people could hear, but really, does any of this apply to microwave to optical transduction, for the superconducting technologies? Some of it may, but I think the biggest part that we're not addressing is really the quality of or the sensitivity of the electro-optic or other transduction. You do it with very low driving voltages in a cold environment with very little heat dissipation. And so there's a number of groups, and from your question, you're probably much more familiar with it than I am, perhaps, but are working hard on pushing devices, electro-optic techniques. Colleague here at Purdue, Sunil Bhave, is working on stress optic or piezoelectric type mediation of some of the ring resonator type cavities, and so forth. So I think the work we're doing doesn't address those are really a modulator type of issues. But if one can do that, and in superconducting circuits, my understanding is you really have different frequencies, usually 2, but in some cases maybe modestly more. And if those were to be transduced directly in the optical regime, there's some hopes that maybe there'd be some interesting manipulations one might do along the way while in the fiber stage.
Thanks.
Yeah.
Great. One question in the back.
Professor Chu back there. No.
Thank you for a very thank you for a very interesting talk. I'm not in this field, but throughout your talk, you keep emphasizing that phase matters. So I just wondered how many of these systems are naturally phase locked, and what systems are those, or where you have to introduce things like phase lock loop to get the phase to be locked?
Yeah. Okay. So Professor Chu's question is really generally about phase matters, and as I interpret it, what kind of systems produce coherent phase. And so rather than enumerate the things, I would say if you're talking about entanglement or interest in entanglement, if you don't have kind of coherent phase or a stable phase, you don't have entanglement. Okay. So if I have I have my frequency correlations. Okay, I could have a system where I only have idler 1 and signal 1 at one time. And then sometimes they're not there, but I have signal 2 and idler 2. Okay, so I have strong frequency correlations, but in that case, I never have both frequencies at once. I wouldn't have a coherent superposition. It would be kind of a mixed state. But in general, whether it's frequency, polarization, whatever, when you have 2 or more states with 2 or more particles and you want to have entanglement, you have to be able to describe the wave functions in a way that there's a stable phase relationship, between the different levels, okay? And then bridging, not only the one particle, but however many particles are involved in entanglement. So, in the quantum world, I put it that way. If you're talking about entanglement, you're talking, you have a system with stable phase, and the extent that the phase isn't stable, that's a loss of full entanglement or degradation in the infidelity of your entangled state. Okay, so I'd say in the quantum world, it's particularly ubiquitous. To the extent you don't have it, it's a problem where you're fighting, to solve the decoherence, et cetera.
Great. I think that's all the time we have for today. It is lunchtime now. We'll see you back here at 1:30.
Good.
Hey guys, hello. Can you hear me? Guys, I have a question. I lost somewhere my cool sunglasses. If anybody saw sunglasses, please let me know. They're cool. I like them. Thank you.
we go. Hello, 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 hello. We're going to be starting in 5 minutes. Alrighty. Okay, we're going to go ahead and get started in a minute. Can all the panelists please join me at the front real quick? Until 2:15. Alrighty, welcome everyone. This is the second panel discussion of the QSC Summer School. Our topic for this panel discussion, as you can see up here, is quantum simulators and quantum computing. What is next? So, hello, my name is Blake Wilson. I'm the team lead for the postdoctoral and graduate student association at the Quantum Science Center and a PhD student at Purdue University, studying quantum machine learning applications in engineering under the guidance of Sasha Boltaseva, Vlad Shalive, Sabri Kais, and Alex Kildashev. And like I mentioned, topic for today, quantum simulators and quantum computing, what is next? Specifically, we'll have a discussion on the key applications for quantum computing, such as quantum simulation, quantum chemistry, engineering design, and machine learning. With me today are 4 highly regarded scientists on the ground developing near-term hardware and algorithms within our field. So first, to my left, Sabre Kais. Sabre is a distinguished professor of chemistry with a full professor courtesy appointments in physics, computer science, and electrical and computer engineering at Purdue University. Even further to my left, Alex Kiesling. Alex is the CEO of QuEra and an expert on Rydberg atom arrays. And then further to my left, Andy Weiner, the Cypress Family Distinguished Professor of Electrical and Computer Engineering at Purdue University. And then finally, last but not least on the end, Nick Braun, who will be giving a lecture later today, is a research staff member in the Experimental Quantum Computing Group at IBM TJ Watson Research. So for the next 45 minutes or so, the panelists, myself, and all of you will engage in a chat on physical platforms for quantum computing, quantum simulators, quantum computing, what's next, what are the algorithms we're going to be running, all that kind of stuff. For the first 30 minutes or so, the conversation will be amongst all of us on the panel, and then in the last 15 minutes, we open it up for all of you to ask any questions you want to the panelists. So I guess I'll begin with a fun question for all of you. What is the hardest problem you've ever solved? Just to get things going. It doesn't have to be quantum related at all. What's that, Vlad? Yeah, still ahead, still ahead.
Thank you. This is the fun part. I touched on this problem on my talk, and the problem is how to map symmetry breaking of electronic structure into critical phenomena. And this started back when I was postdoc with the Hirschbach doing dimensional scaling, which the main idea is to generalize the Schrödinger equation to high dimensional space and solve the problem at d goes to infinity. And what happens at this limit, electrons are localized, and we start seeing like the symmetry breaking looks very similar to critical phenomena. We could not figure out how to do it. And then when I joined Purdue back here in '94, we spent like 2 years until we figure out how this phenomena can be mapped into true critical phenomena. We calculate the critical point and critical exponent. But what was frustrating about this problem after we did the solution, it looks nobody cares. And how do I know nobody cares? Because like later I start looking at the citation, and it looks like only our group was citing our papers. So nobody cited. So this is, but now what is exciting, because I mentioned this in my talk, now we start seeing experimental work on finite system, and we're getting back to the idea that we developed back 20 years ago, that processing chemistry, dissociation, ionization, all these processing chemistry, they have behind these processes a true critical phenomena and true critical exponents. I just want to mention one last point. I mean, why this is important, because when you go to physics of critical phenomena and people calculate the critical exponents, they start seeing a classification and of the universality classes. Well, somehow in chemistry, what we do in chemistry, each one take a chemical reaction and beat it to death. So we don't have universality classes in chemistry. And I thought this is maybe will open up a new door for classification of chemical reactions according to the criticality. Thank you.
Seems a little self-referential. This may be the hardest problem. It's hard to tell from a scientific standpoint, probably actually related topics on quantum phase transitions and making sense of what the experiment was telling us, that we didn't necessarily know how to interpret. Looking at universality classes that have unexpected critical exponents, particularly field theories that describe them that are non-conformally invariant. So that took a little bit of figuring out. I think that this question is hard because we must highlight one thing, but I think that to me that what's more important is more than the one biggest thing. It's the series of small problems that we've had to solve as a team over many years and as a community that seem like small things, but they all keep adding up. And thinking through what it's taken to get the platform to where it is right now, starting with very simple problems like how to generate multiple deflections of an acousto-optic deflector. It sounds very obvious that it shouldn't be a problem, but there are some subtleties there. And it wasn't necessarily the hardest problem. It was a problem that required insight and thinking a little bit through it. But what's particularly important about that one is that it allowed us to make very, very fast progress and also enable the progress of other groups. And similarly, this is the way that this is something that we contributed. Another small, seemingly small problem that we got our insight from others was to make better lasers by filtering phase noise. And these small things really turned into huge differences over time.
Yeah, I like that. It's the hen that keeps laying golden eggs along the way, right? Pursuing a hard problem helps you solve a bunch of smaller problems. Andy?
Son? Yeah. So I go back a long way. And so what really comes to mind are things that are non-quantum. I will finish with one that's quantum. What also comes to mind are problems that I didn't solve. Sort of most of the ones we've solved, I probably didn't feel that way at the time, but in retrospect, weren't that hard and so forth. So what really comes to mind is back when I was a graduate student, this was 79 through 84 at MIT. And I was, my thesis advisor, Eric Ippen, had just come from Bell Labs. I was one of the pioneers of ultrafast optics. And one of his equally sort of famous colleagues still at Bell Labs, his group had first demonstrated the first femtosecond laser, 100 femtosecond timescale. And so I was told as a, his first, one of his first, actually his first as graduate student actually, that I should build one of those and replicate it at MIT. And so maybe half a dozen years later to 8 years later, there's a lot of theory and there was some understanding of how it worked. But frankly, at the time we're doing it was almost completely black magic. And aside from learning how to light lasers and stuff, which I'd never done before, when I got it going, it was very hard to get short pulses or full of instabilities. And so I spent about a year, mostly in the dark, though it was dye laser, it shined, nice yellow light, but otherwise, largely, in the dark, fiddling with mirrors, making some observations. This mirror works sometimes and had this different spectral thing, and more from observation without my understanding. About a year later, it kind of got it working most of the time. Sometimes it stopped working. It might take a few months to recover. But it turned out it was either the first or one of the two first of such things working at a university. And it was kind of a great time because the field was kind of completely open. So at the time, it took a tremendous amount of persistence. I think that's something I'm blessed with having and still have. It took some, clever things, but it was really both literally, because it was dark in a laser lab, working in the dark, but also from the understanding point of view. And, so that's what actually comes to mind. And that brings up an example of one of the problems I didn't solve. And so in these lasers, the pulses get very short. Dispersion is very important. I talked a little bit about dispersion in the context of quantum optics today. I'm essentially wrestling with dispersion, enjoying wrestling with dispersion for 35 years now, or no, 40 years. Okay, so the fact that different frequencies may have different delays in going through fibers or even bouncing off mirrors in sort of the extreme case of a femtosecond laser. And originally we didn't appreciate that dispersion was important. That understanding came a few years later. In my case, I was lucky with my laser that one of my mirrors that seemed to work well actually gave me accidental dispersion control. But this idea that it was known that pairs of diffraction gratings could be used for dispersion control, but they're too lossy to go in a laser. So I thought, well, why not prisms? Prisms like gratings disperse light, and maybe we could put these in a laser, they're high transmission. And I spent quite a bit of time in my office and several stacks of paper trying to work out the algebra of how different frequency light went through prisms and what the delay was. And finally, I gave it up and threw it in the trash, or it's in a notebook somewhere. But I spent a long time on that. And turns out, probably about 2 years later, there was a paper from colleagues at Bell Labs, a theorist with some experimentalists, who had found an elegant way to sort of work this out without my, inch of algebra, and could show in a few lines that the prisms had the right properties and built a laser with prisms for dispersion control. And then this whole art became a lot easier. The other lesson is, I didn't know it at the time. I was kind of too ignorant to know that the reasons you should expect that prisms wouldn't work, and it's because they diffract light where the angular change with wavelength is opposite to gratings, and there's reason to think that was bad. The Bell Labs guys figured out actually this sign didn't matter and it would work. I have a detailed write-up in my textbook at this point in ultrafast optics. But at the time, one, I couldn't find an elegant solution. The algebra stopped me. But I had somehow the right intuition. But I was also not smart enough to realize there's reasons you shouldn't even consider this. So anyway, that's one. Coming to the sort of the quantum era, one of the things I talked about how to characterize the entanglement of these frequency superpositions, I think was hard at the time. And in fact, I remember when we started working with these micro rings around 2016, we fairly quickly saw frequency correlations. And there were some other groups doing that. The group of Morandati at INRS, been doing it for a few years. And as I mentioned, had sort of independently around the same time, they published a little earlier, came up with these phase modulation ideas for measuring it. But my students, we saw frequency correlations, wanted to publish a paper on entanglement in these micro rings. And they told me that they had talked to the students in the group and said, why aren't you guys claiming that? He says, because we haven't shown it yet. And they came back to me, and I remember sitting at a Clio pondering why we hadn't had entanglement. And that's when it occurred to me that there was some notion of phase that I didn't understand at the time that must be important. And pretty quickly after that, I kind of understood things about entanglement I hadn't appreciated, which I'm glad, because we could have really embarrassed ourselves if I went with what the students wanted to do at that time. And so now it was throughout my talk, sort of the phase matters. But it's partly an understanding, but partly it was actually, there were several approaches we looked at involving phase modulators, and it was quite technically demanding and just barely doable with the equipment and the parameters we had at the time. So I think that's enough out of me. But please remember, sometimes the hardest problems are the ones that, unfortunately, your brilliant colleagues solve and you don't.
Yeah. Yep. Nick.
Okay, so well, this was going to be something I touched on during my talk, but let's just say it here. I said the hardest problem I ever worked on was the one I'm going to show to you about 4 p.m. today. And you're going to look at it, you're going to be like, well, what's so hard about it? You're just using Qiskit nature to do, map your fermions to Pauli operators. You're just using, other Qiskit tools to do trautorization and map. It's so super easy. But the thing that I want you to appreciate is that this work I'm going to show you is follow on from my first quantum simulation work. I've only been in this field for 2 years, so I have one piece of work I did with the postdoc mainly, and we were essentially like hand compiling microwave pulses in order to do that work. It was very, very difficult. We didn't have all these tools in Qiskit at that point. This did not exist. I mean, I could have gone like Sabre said. There were tools at the time that we could have automated some of this work, but it was really, it was essentially like pulse compilation and optimization by postdoc. Which brings me to the point that because these tools exist now, they allow us to tackle much harder problems that we couldn't have thought of even being feasible, which is why I say that this is the hardest thing, because if I had to do it like we did it before, I would have never done it. And like Alex said, it's like all these kind of little steps towards the hand that lays the golden egg. I forgot what you referred to it as.
Yeah.
But yeah, all these steps forward just make more and more possible. And I have this philosophy that you always have to push, the technology forward. And as you go forward, you have more tools that you can do more things with. So you can keep going further. That's my motto.
Yeah. Thanks, Nick. Yeah, just so people know. So Nick, you are now the Qiskit guy, right? We were talking about that earlier. You didn't start it, but you are the Qiskit guy.
Right. I'm the Qiskit guy now. So,
Yeah.
I was working on the hardware like a lot of like Alex and a lot of other people. So I got to see a lot of parts and how the hardware was developed over the years. I mean, I spent like at least 6 years on hardware, and I've been in a lot of groups, so I kind of see how things work, and I see the differences in how things kind of flow together, and have a lot of experience around IBM.
Right. So if any of you have Qiskit questions, he's your guy, and so is Olivia up front. Anyway, okay. So speaking of moving forward and thinking about what's next, what sorts of problems in chemistry and physics do you think quantum simulators will be able to tackle for us in the next 5 years or so? Alex, you've made some great progress with QuEra on specifically simulating physical systems. But more broadly, what are the next steps of that? What are the next simulations that haven't been done that you really want to see in the next 5 years, or those kind of applications?
There's a lot. And I think that part of it is that we haven't even realized how much there is. I think to me, this is the most exciting thing about the field, that we're getting to the point where we're learning which questions to ask thanks to the hardware. In terms of, even just looking at what's been happening in the past few years, I think that there's been a lot of very exciting developments with quantum simulators in general, and I think that they're opening up more and more possible directions. I mentioned briefly earlier today that some results about seeing signatures of spin liquids, and suddenly now we can start thinking about non-abelian anions, or we can take a different approach and look at what happens when we deform the system slightly. Can we learn something about material systems that can support these types of phases? What are the right conditions? Hearing what was said earlier today about chemistry was very exciting, and how phase transitions might be able to tell us something about chemical processes and molecules in general in these symmetry breaking. I think that there is more to be done than I can even start to comprehend, and that is very exciting to me.
Well, I think maybe before answering this question, I would like to take you back like 10 years ago, because we have a center here for quantum information and quantum computing for chemistry. And I remember at that time, the discussion was how to build a quantum computer. And look, just for the last 6 or 7 years, we shifted the discussion from how to build a quantum computer to what to do. And this is the NISQ era. We have 50 to 100 noisy qubit. And people shift the discussion to what to do with this quantum computer. And as I mentioned in the talk, like electronic structure will keep, I think, advancing once we have a better hardware. But the problem that I would like to, discuss, and I see in the near future will have a big advantage, is in the dynamics, not in electronic structure. So what I'm saying dynamics, because if you look at the machine that we have today, these are noisy machines. So what does it mean, noisy machine? What we do in open quantum dynamics, we have a system interacting with environment. So if somehow we can control the noise in this machine to our advantage, what I'm saying, like engineering the noise to our advantage, we really be able with these noisy qubits, we can do dynamics and might be able really to see advantage over classical computing. And just a couple of months ago, we put together a paper with my colleague from University of Chicago, David Mazzotti. So what we did in this paper, we took an excited state with a simple Hamiltonian, and we put it in a quantum computer and see what happens. What are the signature of the noise? Can we learn something about the noise? And it seems there is a really unique signature of this noise on the machine. So I believe if we have a control of the noise and we know how to engineer the noise in these qubits, now we should be able to do dynamics for a large number of qubits. And I see the future of dynamics, I mean, getting advantage over classical computing will reach it faster than electronic structure calculations.
I guess that just brings up one of the recent things I've been thinking about. I've been mostly doing Hamiltonian and evolution of simple systems. But the more I learn about the many body systems like Sabra is talking about, one of the questions seems to be how much entanglement do you actually need to describe the system to an accurate degree to get like an answer that's better than what you could do in other ways. And I think that will be one of the biggest questions that will be with us in the next 5 years as these systems get larger. And I think there's like very deep connections to machine learning, tensor networks, and error correction that will come out as a result of this. Because I have this feeling, I haven't wrapped my head around it, but I think there's like a very deep connection between the three of those.
Yeah, so as I hope I made clear in the talk, I'm actually not working on computing or simulation, but you know, some basic photonics when I toward networking. But you know, 2 comments that might be marginally relevant. You know, one from the networking point of view. So, you know, this is an area that's at least as much and probably more in its nascent stages than the quantum computing. But hope to see it get someday to the point that we can play a useful job in connecting quantum simulators, sensors, or computers at a distance, and where something advantageous happens from connecting these resources in a quantum way. I don't have a great view of that what might be, and I would love to learn more about that, but it's sort of the hope that that might be a useful thing.
Okay.
And I have one more thing I can mention from the simulation point of view. This is not so well formed, but again, with our frequency states, you know, there's problems with photons. You know, certainly systems we work at have probabilistic generation of the entangled pairs and so forth. That's a, you know, if that were deterministic, that would be very helpful. And interactions between photons by themselves are, you know, very still a big challenge in the field. That all said, the number of dimensions that you can connect in sort of frequency platform in a compact space may be fairly unique. So one can envision sort of loops with electro-optic phase modulators on chip or resonators on chip. And in the classical world already, there are demonstrations, not in my laboratory, but demonstrations of electro-optic on-chip modulators that a single frequency can end up generating sort of a class of 1,000 or above frequency sidebands. And so there's capability, if you had photons with those number of frequency dimensions, you can envision what I think are truly massive interconnects between the different frequencies or different dimensions. My intuition is there may be some way to use that together, you know, with other tools to do some novel things in simulations. Again, I have really no well-formed idea of what that might be, but I would like to observe it's a you know, hardware potential capability that may not be available in other approaches.
Yeah, Andy, you're touching on a point that I really wanted to get to next, actually, was yesterday, Vlad and Chris and Yang had talked briefly about modular quantum computing and how exactly that would work, because a lot of our classical systems are essentially modular. You have a bunch of cores communicating in a GPU, for example, right? As we start to develop, you know, more advanced quantum hardware, eventually we need some sort of platform to mediate communication between these different quantum computers, right? And that's probably going to be photonics. Photonics is going to have to play a role in that. I guess, you know, how far away are we from using photonics as that mediator between modular quantum computers? And what challenges still need to be solved to be able to do something like that? Andy, you were starting to touch on it a little bit there.
I can continue maybe for a little bit.
Yeah.
You know, so, you know, in addition, just sort of the challenges that my group and our collaborators, struggle with from day to day, there's lots of other pieces. For example, that, the transduction bit. And so, Nick and I were talking a little bit earlier, he had asked about transduction from superconducting to optics. I confessed, I think publicly, that I didn't have any good solutions, but that's important. But likewise, if we're doing neutral atoms or ions or so forth, those are almost exclusively, in the sort of the visible or near visible ranges. And so if you're interested in going over any distance, at least over fiber, those are undesirable wavelengths. And there's a whole, efficient, high fidelity quantum frequency conversion technology. A lot of people working on that, but they're, I would say, not yet to the point where they're ready for, where they, by any chance, any point need to be. So that's one of the actions. I think the whole bit about long distance, short distance is one thing, but long distance, I talked a little bit about repeaters and so forth. I know about enough just to get myself in trouble, but it's clearly, there's a tremendous challenge to sort of actually be able to relay quantum information at a distance, overcoming loss, particularly in fibers, which scales exponentially. So, satellites scale in a polynomial fashion, but still it's very lossy. So, I have to believe that to really be useful, you need a certain rate, and over any distance, that's still a tremendous challenge. How you're ever going to get there. The last thing I'll say is, I participated in some proposals. I didn't lead them, but for some of the NSF Quantum Institutes, they were all about quantum networking and bringing in some computer scientists and algorithms. But I have to say, I felt one of the questions our team didn't have a good handle on is, suppose you started distributing some entanglement between, separated quantum platforms. What were some clear examples you'd give of how you would really win? And so I think that part of it too, maybe some of the people here or elsewhere know, but, clear idea of when we get those quantum networks going, what algorithms we're really going to make happen that weren't going to happen otherwise, and so forth. It's not clear to me how well that's answered.
To add one point, I think though, this might be really helpful in securing data. I mean, the question is how to use entanglement to protect data and connect them with the entanglement. So if somebody threw the one aspect of the data, you will know it through the entanglement. So we don't really have a clear algorithm for that, but we are working in the group to see how one can secure data by using the same idea of distributed entanglement between different data sets.
I mean, I can just tell you what we've been doing. We know eventually you want to take the data outside of the dilution refrigerator, which is sitting at 10 millikelvin in your lab. And a microwave photon has no meaning in the thermal bath that we're all sitting in right now. So you have to upconvert to fiber optic. And that's relatively easy to take a fiber optic outside. So that is definitely a long-term goal of us as well. We also do, the field has the work of Andreas Walraff at ETH, where he's actually taken two dilution refrigerators and attached them together using all kinds of cryogenic support, which seems like a rather pain. So we probably need to solve this optically.
I will echo what I've been hearing, which is it's a hard problem, and that's for sure. We've been thinking about it for the neutral atom platform specifically, and there are exactly the issues about the wavelength, the absorption in fiber for visible. It's clear that we need to be able to do some conversion to go to very long distances. But even at a smaller scale, I think that part of the benefit of modularization is to be able to have smaller problems to solve. So even in the absence of a worldwide quantum network, I think it's still something that we need to address. We're working on it. We're working also on related technologies to really push the boundaries of what can be done in the visible range of the optical spectrum with
very fast modulators for individual control of atoms. And this very nicely, they're coupled problems, right? If we can bring the light in and we have that degree of control, we've gone half of that way to get the light back out and to connect. It's free space, so there are still questions to be answered there. Do we need to start putting things into cavities? I think those are complicated topics that we'll still need to answer. But what makes me hopeful that this problem will not be a limiting factor is the very fast progress that we've seen in the past few years, particularly in developing new visible range optic solutions or photonic solutions. And for what I'm projecting for our platform, today I described results with hundreds of atoms. I'm pretty convinced that without having to reinvent basically any part of the system, we can go to something in the ballpark of 10,000, and with a few engineering developments that we're starting to work on, this number may get pushed to 1 million. So it's a problem that we need to start addressing right now, but I think that everything will converge in a few years so that we still have enough time to solve it.
Okay, sure. So we have about 12 minutes left. I'm going to open it up for the audience now. If anybody has any particular questions, we can run a microphone to you and you can ask the panelists. So yeah, does anybody have any questions? Okay, great. All right, then I can just keep asking. Okay, this is a directed question at Nick and Alex. You both kind of, well, Alex, you've touched on it a little bit. Nick, I assume you probably will. You and I have had conversations about it a little bit. How does a company like QuEra or IBM create a useful product for their customers when quantum computers are still a ways out? What is the near term like? It is the question to be answered at the moment, but I'm curious what your answers are.
Sure. I think that it's important to think about where you find value, right? I would claim that even what I was showing today, this is something that is valuable to a lot of people. I mean, as a scientific tool, the devices and everywhere, be it at IBM, QuEra, anywhere, I think that they're already providing a significant amount of value. I mean, we've heard from multiple people in this room that they are using the IBM machines. And back to my first answer to your question about simulation, the fact that these things exist allows us to move at an ever increasing rate. And the discoveries that are coming out of the quantum devices today are advancing the types of questions that we can even ask and that we can answer now with data. I think that the underlying assumption in this question that one needs to be able to outperform every classical alternative for a particular task, design or whatever, I think that's not the only way to provide value. And I think that we're not that far from that, to be honest. But even today, what we're doing is already enabling scientists, researchers, and it's also allowing people that want to know what quantum computing will be able to do in the next few years to understand, to prepare, and to guide their own efforts for what are the areas that require the most attention, both in industry, in academia, and also in government.
I like Alex, I would agree. I'd see, in the cases where people get interested in quantum computing and they're gotten along to the point where they can do a project that's scientifically interesting is probably about a couple years. And so right now, I don't want to ruin my colleague Olivia's talk next, but there's way more job openings in quantum than there are people available to fill them right now. So besides that, just tooling up and to the point where we hope, which we think will be hopefully closer, where we have advantage in certain kinds of algorithms over their classical counterparts. We think that will be soonish. And we think that there will be a huge demand for people to fill the needs for companies to use those for their solutions, which is why they are paying IBM, for example, to learn how to do this right now, even when they're not getting a direct benefit in solutions right now. They're equipping themselves with that possibility. In addition to training the quantum workforce so that all the colleagues of the engineering and physics departments and chemistry departments can get their students jobs when they graduate.
This is not an answer, this is a question. So I'm curious on both of your views on how many years we have, the community has, before actually demonstrating some improved solutions that can be used to business or government advantage before this checks stop coming.
Answer that I was going to mention, and this is, it's not necessarily okay, I'm going to take that back. I'm going to say this is a very interesting problem because you talked about mapping all kinds of problems onto icing models, and I'm going to say, well, that is actually a pretty easy thing to put onto a superconducting quantum processor. And one of the results my colleagues Youngsuk Kim and Abhinav Kamdala had recently is that they can do some quench dynamics, and then they can't do anything that you can't do computationally, but they're approaching the asymptotic limit at which they will go beyond what is capable by currently the best approximation using projected entangled pairs and matrix product states, for example. So there is a point at which you can kind of see the quantum nature or the quantum computers overtake in performance, at least versus these systems, not overall, like you can still classically compute all this, but you kind of see these asymptotes go and you can see that limit, or you can see where quantum would overtake, and you could say, well, that's a practical enough problem that everyone's been talking about it today. Sure, it's gonna happen.
I just wanted to say that the difficult part about that question is not the science and the engineering, but the economics of it. And in terms of the science and the engineering, I am sure that we are on the path to getting quantum devices that can outperform classical devices, even if in niche applications that have commercial relevance in the next 5 to 7 years, something in that ballpark. You're asking about when will the money stop flowing. That is very hard. I mean, even if you look at the markets today, right? Like, I'm not sure that you would have been able to predict where we would be 8 months ago. So that part to me is just very hard to give you any kind of precision. But what I can say is that there's an understanding, I think, from the government and from very large corporations that this is a key technology that is going to enable completely radically new things. And even if things start going more slowly in the next few years, it looks like there's been enough set aside to get us through to where I predict we will have real useful applications that are integrated into workflows.
I just like to add one point, which I'm really more optimistic about this. If we look back at the two experiments that were done by Google, which is the supremacy experiment with 53 qubits, and the Chinese experiment with 64 qubits. Again, I mean, the circuit was random, so the results are everybody saying they are not useful, and this is just to have a random quantum circuit. But recently we're analyzing these the results of this experiment. And I think these experimental results can be used, and we think in two different fields. One, in cryptography, which you have a random, you generate random numbers out of this experiment. And the second is you can use it in stochastic, like if you are running quantum Monte Carlo, what are you using? Using random numbers. So you can use these random numbers from this experiment to do real stochastic optimization or simulations. So we are really pushing hard to see what will be the useful problem that come out of this experiment. And I don't think these are just useless experiments just to show supremacy for quantum computer that cannot be run on a classical computer. I see more useful application of this experiment, and hopefully in the coming years, we'll see more and more application into solving these real problems with these experimental results.
Very nice. Okay, so we have about 3 minutes left. Yes, Mino. Let's run a microphone here. It's mainly for YouTube. There you go. Thank you, Alex. Okay, go for it.
Is this on?
Green light? Green light? Okay, go for it.
So just in line with what you all have been talking about. So if you're wanting to start a startup in quantum, whether it's for hardware, and there are some companies out there that are focusing on building just a software stack, even if it's a full stack, there still seems to be a lot more hype about where quantum computing is at and where it will be in the next few years than what I or people I have discussed and people who are using this hardware understand it to be at. So when you're asking for funding, how do you keep the expectations real for venture capitalists or anybody who's funding your startup?
Yeah. So the question specifically is about quantum hype, right? How do we manage it when we also need to, convince people that these startups are worthwhile?
That's right.
Okay. Yeah.
I mean, I think this is true about quantum startups as much as it is about startups in general. The best policy is openness and honesty. Look, I think that investors do their work, right? Like they understand that that the technology is not implemented in daily life in the processes going on in large corporations. They know what kind of they know how much people are paying for accessing these resources and so on. I think our job is to be honest, to be accountable, and also to be optimistic. Because what this technology has the potential to do is absolutely mind-blowing. And if we are not the biggest cheerleaders for it, then we're going to miss out on something huge. But being optimistic and being deceitful are two very different things. I think that we can be optimistic and we can show with results what has been done in the past few years and where the arrow is pointing, while still being completely honest and showing what is available today and what is the roadmap look like. How are we thinking about generating new applications? How are we going to be developing algorithms? How are we going to build a community around using these devices? And how do we see the progression of the capabilities of these devices? All of these are things that we just need to be as honest as we can.
I agree with you as a scientist. At the end, we have to be honest. I mean, this is our job. Once we do research, we have to publish it, go through over the review. But if you think about this hype in the field, it's just a function of time. I mean, it doesn't bother me at all. I mean, people write about it. I mean, we know this is going to, you cannot fool people all the time. So if there is a hype with the function of time, will decay to zero. And I think It's not, I don't see it a problem whatsoever. I mean, I know people, famous people writing about it, but it's not going to affect us. If people write about it and will help get funding for other projects, that's fine. But at the end of the day, science will bash, all this hype will go away as a function of time. And I'm sure this happens all the time when you have a new technology. But now we have it more because of the communication that we enjoy these days. But I'm sure when people start with AI or other machine learning or they have the same problem. But look at this as a function of time. It really doesn't affect us as a scientist.
Thank you all so much for answering these questions. I think that's all that we have time for this panel discussion. Please join me in thanking our panelists. Next up, we have Olivia Lanez. Olivia, I'm going to do a quick introduction for you, and then you're good to go.
Yeah, is this on?
Sure I get. Testing. Like when you. We ready to go? Ready to go? Ready to go? Okay, cool. All right, everyone. Next up, we have Olivia Lanez. Olivia completed her PhD in physics focused on quantum measurement in 2020 from the University of Pittsburgh. She joined IBM shortly after, where she works as the North American lead for Qiskit research and education. In this capacity, she works to help put Qiskit into the hands of researchers and to make sure the people who are using our systems have access to the best tools and devices. She's also passionate about education and works on IBM Quantum's challenges in summer schools with the aim of democratizing quantum education. She also sits on the National Q12 Education Council to focus on workforce development at a national level. Without further ado, Olivia.
Okay, thanks. Is the mic on? Can you hear me? All right, cool. Hi, everybody. My name is Olivia. Thanks so much for the introduction. Really happy to be here today. So I think this talk is going to be pretty different than everybody else's talk so far today. It's not very technical, although I do have some graphs, so you can still be excited about that. I don't think it's going to take the full amount of time, so hopefully there'll be plenty of times for questions at the end. This talk is sort of divided into two parts. I'm going to use the first part to talk about myself a little bit, because the second half is kind of an opinion piece. And so I wanted to sort of establish some credibility here with you guys and let you know why maybe my opinion could carry some weight. And then you can choose to take that or not. All right, so part 0, because that's how we index things in science, is my story and how I ended up being the lead for North America at IBM and Qiskit. So this is just a little bit about my life. So I was born in Boston, Massachusetts, and then nothing that was really important to anybody who would care about anything in the audience today. I took high school physics. I ended up being pretty good at it. I originally decided that I wanted to be a science communicator, and I grew up watching Cosmos DVDs with Carl Sagan, not the new one with Neil deGrasse Tyson. It's very important you know that. And I really loved Carl Sagan. I wanted to be a science communicator. I thought the best way to do that would be to go on to study astrophysics. So I went to Dickinson College, which is a really small liberal arts college in Pennsylvania, because it had an observatory on campus. Again, this was all part of my plan to basically be an astrophysicist. And I studied all sorts of different types of physics while I was there, but I really wanted to do astrophysics in the end. So I went on an observing run at the end of my junior, beginning of my senior year in astronomy, and I really did not like it. So this was sort of an existential crisis moment for me in my life, where everything I had done up until that point to get to that research experience sort of was for naught, in my opinion, because I just really did not have a good time. And that's no knock on astronomers. But some of them are my best friends. They're great. It just was not for me. I did not enjoy it. So I started applying to graduate schools. I prepared myself to settle, and I was just going to keep studying astrophysics anyways, even though I knew that I just didn't like it at that point. But luckily, my senior year, my advisor sort of pointed out that I could work in his laser lab instead of focusing on my senior thesis in astronomy. And I ended up doing that instead. I thought maybe this is something that I should actually pursue in graduate school instead. And so I decided to do that. And so at the last minute, I literally took all of my graduate school applications, which were geared towards astronomy and astrophysics, threw them away, and then reapplied to some condensed matter and quantum information graduate schools. So I got accepted to the University of Pittsburgh, and I decided to go there to build a lab from scratch. My advisor, Michael Howridge, was hired just a few months actually before I got there. So when I got there, my lab looked like this. And it was just this big empty white room. And you can see we had some chairs and a vacuum, but there's no scientific equipment to be seen. So I had to help, along with me and two other graduate students, basically build up this lab from scratch. And I thought this would be a really fun and interesting and unique learning experience. And indeed it was, but it was also incredibly difficult. So we finally got some equipment. These are two of my friends and fellow graduate students. This is a dilution refrigerator panel you can see here. Finally got some equipment, didn't know how to use it. So this is us looking there, being confused. There was no one really to teach us how to use this equipment except my advisor. So that's what it looked like at the very beginning in the early days. This is an experiment that did not work. So if you're building a lab, if you've ever had this experience in your life, you may or may not know that plumbing is hard. It's like way harder than you would think it is. I see some people nodding. Thank you. So these are all the parts that I built for plumbing for my first experiment that didn't end up fitting with any other plumbing parts that were actually already installed in the lab, and you couldn't return them. So this is what my graduate school lovingly referred to as Olivia's plumbing drawer of shame. But eventually we got the right parts and we were able to put those together, and I wired up my first dilution refrigerator. So all those cables, I made those by hand, not to brag, but yes, this was my first completed project in graduate school. And then right before the pandemic, because I graduated during the pandemic, this is what the lab looked like the last time I saw it. So we were able to build up this quantum computing lab. It has 2 dilution refrigerators in it now. A third is arriving shortly, I think my advisor had told me. And you can see we filled it with tons of microwave equipment and electronics and generators. And it was a fully fledged lab that I worked in for the next 6 years. All right, so I will resume my timeline. So went to Pitt to build a lab. I did research for 6 years, went to a bunch of March meetings, and then I started to apply to jobs after that, X amount of time, when your advisor sees that you have that pained sort of desperate look in your eyes, and which means it's time to graduate. And then I did, and I started applying, didn't get every single job I applied to. Oh my gosh, everything is terrible. The world is falling apart. Then I finally did get some jobs, but then you have to sort of pick, what career you're going to follow. And that was also a little anxiety provoking. Also, there was a pandemic, so that was fun. I wrote my entire thesis during quarantine and accepted my IBM offer. And then I joined IBM shortly after I graduated. And last year, sorry, the formatting is got a little messed up, but I got promoted last year to the North American lead. And now I get to do events like this and work on Qiskit. And with my colleague, Nick Braun, we get to work on a bunch of educational initiatives as well. So it's been super fun and rewarding. All right, so if you are interested in doing sort of anything in the quantum space, the first question I always get is, what background do I need to do this? And of course, the answer is it's complicated, right? It really depends on what you want to do. So there is a bunch of text on this slide, please forgive me, but I sort of broke it into 4 distinct areas. So there's theory, hardware, experiments, software, and then applications. For all sorts of these different fields that you might want to go into in your future, I think different backgrounds can sort of help a little bit. This is not like a strict rule. Again, please don't think that this is, concrete and this is the way it has to be 100% of the time. But in general, these are some of the trends that I have noticed. And I've done quite a bit of hiring over the past year and a half. So in general, quantum information science and theory, physics is a good, strong background to have. If you want to work in a lab, if you want to do experiment, most of the people, again, physics or engineering, work with a lot of good engineers. Software, again, it depends what you want to do in software. Computer science, of course, makes a lot of sense, but also there are some graphic designers that I work with as well. So if you want to work on like the user experience and the interface, you might want to study graphic design. Could be cool. Applications, this is sort of a very large conglomerate of different skills, I think. So physics, chemistry, computer science, math, sort of all pools together in the applications framework. And I think you have to sort of be strong in all sorts of these good things to become a good algorithms developer. This is really quite challenging. But I put a little asterisk next to the software one here because a lot of my software friends tell me, you don't necessarily need to have a PhD or a high-level degree to go on and work in computer science and software. Often equivalent levels of experience are also good. So this may or may not be relevant to most of you in the audience today. I'm told most of you are already graduate students or postdocs, so you've already, sort of formed your decision here. It's too late for most of you, I guess, but that's fine. Still interesting data, and you might be advising undergrads or, the such in the future. So the other question I always get is, do I need a PhD? And this is a graph from a really cool archive paper that you can check out later if you're interested. But this graph at the top here, the pie graph, is all of the different degrees from all people working in the field and industry, so not academia right now. And then it breaks it apart into North America and Europe. So you can see here that there are about 50% of all of the people working in industry in the United States right now in quantum information science have a PhD, and it's a little bit more in Europe. That's not actually super surprising because in Europe, it generally takes about 3 years to get a PhD, so it's not as much of a huge time commitment at the beginning. But so you can make of that what you will. This other cool graph here kind of shows, not graph, a flow chart, I guess, actually, different paths to get into the quantum information science industry. Obviously, getting a PhD, doing a postdoc, getting industrial experience, or you can go right into the job market. It's a very common path. Getting a bachelor's, going straight into the job market, not as common. And then something that has sort of popped up more recently are these quantum information science master's degrees. I don't know if you've seen these, but they are sort of exploding. And we've done some consulting, IBM and a lot of these different universities and colleges who are exploring these master's degree programs. It's a little bit too early, I think, to say, how successful they're going to be. And, this might not necessarily be the flow chart that applies to them. I think these master's degrees are more for physics and engineering and computer science, but we'll see how that sort of plays into things as well. All right, this is also some interesting data that I just wanted to share with you all. So from that same archive paper, these are the distributions of degrees depending on what you might actually want to do in the field. So at the beginning here, it starts off a little bit less technical. So you have some product sales, marketing, technical design, and then all the way down at the bottom where you will see the vast majority of people working on it on error correction and computational chemistry. Those are sort of the PhDs. And then there's all sorts of different people in the middle. But you can see, unsurprisingly, the more technical, the more specialized it is, the higher the level of an education that is generally required. All right. Other interesting data that I thought might be interesting to share is This is a different archive paper that sampled 57 quantum computing companies sort of across the board, hardware, software, everything. And they asked them what if they had somebody on staff who had one of these degrees, what's the question? So if you were the CEO of, a startup or IBM or whatever, and they said, hey, do you have anybody on staff with a PhD in physics, they would mark you as yes. So 95% of companies had somebody on staff with a PhD in physics. And then it sort of goes in descending order here. And you'll see that actually the next most common degree was a bachelor's degree in engineering and a PhD in engineering. And then it sort of goes down to a PhD in math. Probably just there are not as many folks that exist with that degree. All right, so I thought that that was another interesting sort of problem statement. All right, so indeed, what is the answer? It depends because everything is complicated. So if you're giving advice, if you are an undergrad or you work with an undergrad and they ask you these questions, I generally like to say, well, do you want to work in a lab? Because it's really hard, I think, to get quantum information science, tangible hardware experience without working in a lab. And the best way to do that is to go to graduate school, I think, for some number of years. Do you want to be a team lead? Do you want to be a technical leader? It's hard to do that without a PhD. Often you will have somebody who's a little bit more senior, if you don't have a PhD, sort of developing the ideas and the strategy and then passing those on to the group and telling them what to do. If you're eager to dive deeper into ideas and understand the theory, if you want to be really close to the cutting edge research, then yes, maybe a PhD is for you. What are some options for different career paths that you might be interested in after graduation? So this is a fun question because there are so many different possible options. And this is not all of them either. This is just a subset of what might be available to you. So you know that there is tons of industry research. There's IBM, Google, AWS, all sorts of big companies. And then there are also plenty of startups as well. As I'm sure you know, this is not a complete list by any means. So these are just some startups that I was able to find in a handy dandy picture and copy and paste onto the slide. So these are, again, if you want to work in research, lots of options available to you. Maybe you're actually more interested in consulting. I think that people don't always think about this, but actually when I was applying to jobs, I applied to some quantum information consulting positions. So some examples of that are the MITRE company, who's Alan Hamilton in DC. They work on government contracts and they inform decisions made by government officials in this technology space. So it's actually, from what I understand, I don't do it, but a very interesting and rewarding career, and you get to work with a lot of people in government and high-ranking officials. Could be cool. I think a lot of other jobs that people aren't maybe acutely aware of at this point in their career is product and project management. It's different. So this is actually a really cool job, I think. You don't need a technical background to do it, but I do think it's beneficial. And I think a lot of companies these days are looking for people with a technical background to be product managers, especially in the quantum computing space, because I think people who have been working in it, like we have for some amount of years, have a particular insight that's a little bit not tangible to people who haven't been working in that industrial or academic space. And so they have more insight into the user's experience and what the user might want. Very helpful for project and product development. And then there are lots of other companies who hire these people as well. These are just a few of them. Or you can go on, of course, and work in academia, right? You don't have to go on to industry, but I think that people usually focus on academia. So I was sort of doing the opposite and focusing on industry. But if you're interested in academic positions, that's great. I actually also applied to professorship and academic positions when I was graduating too. I applied literally all over the board. I applied to consulting firms, professorships, big companies. I applied everywhere. So there are sort of two different categories you can think of course, R1, big research schools, small liberal arts colleges, become a teacher. I think that that's great. All sorts of different options are available to you. It's really an exciting space. And I think one thing that we mentioned earlier is that there are way more jobs that are online and available to you right now than there are people who are maybe qualified or perfect candidates to take these jobs. And this was sort of a paradox that you and I were talking about, Blake, earlier, is that I think a lot of people who are interested in quantum information science right now think it's really, really easy to get jobs because there are so many jobs. But it's actually not necessarily the case because some of these jobs are so specialized, they're such niche jobs that you either have to have perfect qualifications or you have to almost be a star in one particular field, right? And I think some of the things that people don't come out and say blatantly are that all of these jobs are looking for skill sets that they might not explicitly list under their job description, right? So they might say, oh, we need you to be, an expert in quantum error correction. But what they might not say, and something that's very important to note, is that you also have to be an excellent communicator. You also have to be a team player. You have to be a great writer. You have to be able to give good talks. You have to be able to communicate with people who aren't in your field and be able to express complex scientific ideas to people who don't work in that space. It's a really, really difficult skill, I think, but anybody can do it. It just takes practice like every other skill. One other intangible skill that I always like to talk about whenever I give these sort of talks is like something I call big picture thinking. I think in graduate school, it's really easy and in postdocs to get really bogged down in like the details of your research, right? I knew I was like that in graduate school. I was really focused on like one tiny parameter, adjusting that parameter and seeing how that would affect my experiment on like a really macroscopic scale. But I think when you're going into industry, they want you to be able to connect what you're doing to like a big picture idea. Like, how does this affect the experiment as a whole? And how will that experiment affect the company? And how would that company and that experiment affect the industry? So I think, again, this is a skill that anybody can learn. You just have to sort of practice it. And one of the best ways to do that is to talk to people. So practice your elevator pitch, so to speak. Other data while we're talking about this subject is more intangibles, right? So if you look at different jobs and sort of the requirements that people want in those jobs, it's not as much quantum as you would expect, actually. So again, this is sort of a list going from jobs that don't actually require quantum technical expertise, although it couldn't hurt, right? To jobs that do require a lot of quantum technical expertise. And again, we have here at the bottom is quantum error correction. People really want you to know a lot about quantum information for some reason for error correction. But you have to have all sorts of other non-quantum skills as well. And those probably would include some of the ones that I talked about on the previous slide. Again, be a good communicator. You have to learn how to write. You got to be a team player. All sorts of different things that have nothing to do with quantum information and quantum mechanics. All right. This is one of the later parts of my talk. So how do I get started? So I think, obviously you have already all gotten started. The slide almost doesn't apply to you. But if you're interested in a particular job, say, I came from a hardware background, but I actually mostly work on software now. You can teach yourself. There's plenty of information that's available to you online. It's free. It's open access. We've already talked about this a lot today. And I think Nick's going to give you a glimpse into how you can really start to do cutting edge research for open, free anywhere in the world right now. So you can often teach yourself, and dev teams will make note of people that are contributing to their open source projects. It's really easy to see on the back end who those people are, who's asking questions, who's doing pull requests, all sorts of stuff like that. Internships, great idea. I think they can be key to getting, a great job in the field. Probably no surprise here. There are internships at almost all of the quantum computing companies that I mentioned, not just IBM, not just Google, but all sorts of ones as well. I'm just more familiar with these ones because I obviously work at IBM. Doing an internship can greatly increase your chances of getting a great job. I think that they're also very competitive. So again, referrals are very helpful. Networking is great. Just keep in mind, a lot of it is, making connections, not just for the sake of making a connection, but like for the sake of sharing information and sharing knowledge, right? Not just to, job hunt. This is just a sampler that I stole from one of the IBM talks on internships, but we hire around 125 interns every single year. We hire some undergrads, but a lot are at the PhD level. So you can get started this way as well. And I think it's always a great idea to get your name out there before you apply. So making a name for yourself in the field is great before you even turn in that job application. LinkedIn, Twitter, I actually think social networks are a great way to get your name out there and interact with professionals in the field. They're way more accessible than you might think they are. I like Twitter more than I like LinkedIn, but that's just a personal preference. I think a lot of people think that when they talk about networking, you have to be really extroverted and like really brave to go out and do that. That is not the case. Again, it's a skill just like anything else that you can learn. You don't have to be like the most extroverted person in the room in order to build a good network. This goes without saying, you need to publish, right? You actually have to, build up your scientific framework before you can start to get the most benefit out of doing that sort of networking process. And if you're interested in software, if you're a computer science person, then obviously you should keep your GitHub up to date as well. All right. This is the last part of my talk, and then I will conclude. But what else should I consider when I am looking for a quantum job? So this is not a comprehensive list. These are just a couple things that came to my mind as stuff that I wish that I knew when I was looking at jobs. But one is leadership. Who is leading the organization or the institution, and not just necessarily like the name that they list as like, the CEO or the board members necessarily, but like who is the leadership composed of? What are their experiences? Are they business professionals? Are they scientists? I'm not saying like one is wrong and one is right, but these are all sorts of things that I think it's good to understand and keep in mind. And what are the general opinions of the leadership team? You can sort of get a glimpse into that just by interacting with employees at the company themselves. What is the work-life balance of the company that you are interested in? When do people arrive? When do they go home at night? Do they have to work, all hours of the day if they are working with people in different time zones? Again, sometimes that happens, not saying it's bad, but it's just stuff that you might want to keep in mind. It depends on the type of life that you are trying to lead. Yeah. Culture. Are people happy? I think happiness is important. I don't think that's a super controversial take. So you can sort of understand the culture of the company that you're interviewing at by talking to people one-on-one or in a group setting in interviews. Really good idea to do. What do you like about the company? What do you dislike about it? Is it a collaborative environment or is it a competitive environment? And does your company have a rec softball league? I'm just kidding, but I recently joined an IBM Rec softball league and I think it's fun. Benefits, salary. Is the salary competitive for the industry? Are these benefits substantial? Again, these are things that are not even necessarily specific to quantum information. These are just things that I wish that I had even thought about when I was a graduate student and I was looking at jobs, and nobody told me this. So I thought I would sort of pass on this knowledge now that hindsight is 20/20 to you guys. It's really hard and confusing to know, I think, what your worth is, especially in an industry that's really competitive and is changing all the time. Don't be pressured to know exactly, how much you want to ask for salary-wise or benefits-wise. Take your time, do some research, talk to your friends, talk to people in the field. You can get a really good sense just by doing that. All right. And that's the end of my talk. So if there are any questions, I'm happy to take them. Sorry, that was sort of a whirlwind of everything, but if you have any questions, you can also find me at any of these places as well. Thank you.
Thank you very much. All the graduates that Boltzmann with the whole semester coming up,
might be worth your time.
Yeah, that's a great idea.
All of the stuff that you reviewed is incredibly powerful, and most graduate students think they can graduate and then a month before they start assembling their resume, which is just really, really a bad idea. So So anybody who's on campus, join, have fun. Also, the lectures are on NanoHub on professional development. So there's a bunch of lectures on that topic on NanoHub. If you Google NanoHub professional development. So it's incredibly important and I feel cool. So we have this one and we can add it on NanoHub too.
Awesome. Yeah, I think that's a great resource. I wish my school had something like that.
Olivia, thanks so much for the talk. So my question is, can you talk a little bit about the interview day at IBM Quantum? What kind of people do you meet? What do they generally ask? How does the decision get made? Just just in overall sense.
So it's been a little bit different during COVID times. So I'll just talk about pre-COVID and post-COVID times. So generally, you might get invited to come in for a day or two. You generally give a presentation on your research and what you've been working on for about an hour or so. Actually, Nick hosted my seminar when I interviewed at IBM. So that was a lot of fun. And then you will get set up on small interviews with one-on-one with people that you might be working with, or on group interviews with a few people, maybe like a 3-on-1 type interview. And it's honestly a very exhausting process. You're there from like 8 a.m. until like 6 at night, and then they take you out for dinner and you just try to stay awake and like try to keep it together for another hour or two. But they feed you good free food. So that's a plus. And then you do it again the next day. And then you fly home and you're exhausted at the end of it. But that's sort of the experience for the interviewee. For the interviewers, what happens is we generally, what is advised is we get together sort of beforehand and we figure out who is going to gauge what aspect of the candidate's talents. So we might have some person who's going to ask them about program experience. We might have someone who's going to ask them about like their, culture fit with the company. And then we get together afterwards and we rate certain skills and we compare notes. And if the hiring manager is on board, the hiring manager, of course, should listen to the advice and recommendations of the people on his team and from other stakeholders as well. And then they will make a decision and reach out to you. Does that answer your question?
Thank you.
Okay,
Yes.
cool.
Okay. Thank you very much, Olivia. That's all the time we have for questions right now. We're going to transition into a panel discussion. So everybody join me again in thanking Olivia for this wonderful presentation. And we'll go ahead and get started soon.
Thanks. Email that to you.
Oh, no. We should
What do you say?
I said we should talk. I have some questions about
sure.
later on, but probably more in-depth questions we can discuss later.
Are you going to go to the dinner and stuff later?
Yeah.
All right, cool. I'll be around.
Yeah.
I'm glad it was fun. I was like, this is very different cost than everybody else.
Yes. Okay. Are we good to go? Okay. Give it 1 second. Okay, welcome to the third panel discussion for the QSC Summer School. This one is about quantum workforce development. We have several people here who have been working tirelessly on workforce development for the past few years. And I'd like to apologize profusely because we added Moti Segev to this panel discussion last second. We didn't have time to put his picture up there, but for everybody in the audience, Moti is at the end. He would have a picture up there, but we decided to add him last second. So, okay, to start off, we're going to be talking about workforce development. I had prepared a bunch of questions, and then Olivia did such a great job during her talk that I no longer have any questions. So I'm going to let everybody introduce themselves while I come up with questions. So starting with Olivia.
I'm sorry. I'm Olivia. I just spoke. So, yeah, so I am the North American lead again for Qiskit development and education. And I work on the community side technically at IBM Quantum, but my background is as a physicist, and I also am allowed to go into the labs and do some hardware stuff in my copious free time.
So I'm Sasha Boltzmann. I already introduced myself yesterday. I'm professor at Purdue, and I'm also workforce lead for Quantum Science Center. And to start with, I would never imagine that I would be leading workforce efforts because I thought I was not able to convince my own kids to go into engineering or quantum. But well, my older is a freshman at Purdue Engineering. So after all, I guess I have something to do with workforce development.
Hi, my name is Erica Carlson. I'm a professor in the physics and astronomy department here. I work on quantum materials, and I'm a theorist, so which means I do math and I do computer simulations, trying to figure out what electrons do inside of those interesting materials. We're always on the lookout for new phases of matter and phase transitions happening in them. And specifically, we're looking for ways that we can draw out some of the quantum properties into the macroscopic level where we can control them. My reason for being on this panel, the contributions to workforce development would be that I love to communicate science to the public. That maybe resonates with Dr. Lanez here. So I've put out some video series on quantum mechanics, introducing the public to quantum mechanics. And there's a YouTube channel that you're linking to for this summer school where I put some resources up there that kind of give people really very bite-sized introductions. Most of that stuff is targeted towards the general public. And I also work a little bit on developing middle school and high school curricula with Dr. Hosseini here, who I'll pass it over to.
Thank you, Erika. Hello, everyone. My name is Mahdi Hosseini. I'm an assistant professor in electrical computer engineering. My background is a physicist in physics. I'm doing experiment in quantum optics and studying light-atom interaction. I'm leading some effort in quantum education funded by DoD, where we are developing courses, educational material for undergrad, grad students, and also collaborating with Erika on doing some outreach activities in quantum and curriculum for K-12 students.
Good afternoon. Yeah, my name is Moti Segev. I am a professor of physics and electrical engineering at Technion Israel. And I'm here also in, what do you call that? Neil Armstrong visiting extinguished professor at Purdue, the first one in electrical engineering here. And yeah, I do a lot of things in photonics and also in quantum. And I've graduated about 50 students and postdocs. 23 of them are professors. I think all are doing quantum, some kind of aspect of quantum technologies, and all others are in the industry. What do you know? What they do is exactly this. I think maybe two went to some strange places like McKinsey, but all others are doing quantum-related technologies.
Thank you very much, all of you. I guess I want to start off with like, what is the main motivation for doing quantum workforce development? Why is it important to all of you? I guess. We'll start with Olivia.
Well, I can give my perspective on why it's important to me personally, and I can also talk about why it's important to IBM. It's important to IBM because we want to be able to find the best talent out there. We have an incredibly hard, challenging, not just engineering, but software, hardware problem in front of us, and we want to be able to find people who can solve these incredibly hard challenges, no matter what they do now or where they may be. I think it's important to me personally because I think this is a technological revolution that's happening now. And if you look at the first computing revolution, it was a lot of people who looked pretty much the same and came from very similar walks of life. And I think we have an opportunity here to democratize this type of education. And I would like to see people who look like all sorts of different type of people and come from all sorts of different places able to rise and meet these challenges. I think the breadth of talent will come from everywhere.
Yeah, I would second what Olivia just said, and we are witnessing this quantum technology revolution. But what's different, I think, with the previous technology revolution that happened with transistors and semiconductor industry, is that this revolution is happening at the same time in academia and industry. So it's very much industry driven right now. And whereas before we had time to train scientists and engineers in academia after fundamental discoveries and breakthroughs, and then send them off to industry that was on the rise. Right now, we are witnessing development in R&D and fundamental science, both at university level and industries. And both of them need workforce now, and there is a huge gap that we have to fill.
I echo your excitement. It's good to hear that perspective. So as someone who works on quantum materials, I do see something very exciting about this developing quantum revolution, which is the following. So typically when we are looking at the frontiers of human knowledge, which is what scientists do, right? We go out to the frontier of human knowledge and we work there. We are typically discovering what's already there. We are typically discovering things that nature has given us. We're going out, we find them, and then we find how they work, and then we use them. Now, we're at a very unique place, I think, right now with quantum materials in particular, because we can design them now. So we are no longer stuck with just the materials that nature gives us. We can design them atom by atom, okay? So this is an incredible new era, where not only are we out exploring a new frontier, we are designing and creating the landscape that we are then exploring. And so that I think is something I'm very passionate about communicating to the general public, to get them excited and aware of what's coming, and to inspire young people such as yourselves to go into quantum related technologies.
So I won't repeat what you heard already. Yes, this is very exciting. I mean, we are all here because we are excited about quantum technology. It's exciting to communicate that to others, to general public, but also continuing to what Sasha said earlier. When you look at the history of digital technology, digital revolution back in 1960s, 1970s, where the first transistors were invented, you look at that and then you ask, back then people were asking similar kind of questions that was asked in the previous panel, that what is next? What do we do with this technology, with this central classical computing technology? And now I think we're asking similar type of questions. And then back then, when you think about it, there were this community of hobbyists and gamers and engineers who were interested in the digital technology. And they helped creating a culture around the digital technology that kind of motivated an industry to go after building and personalizing digital technology. And now we are thinking maybe we should be asking, maybe we are at the same stage that we can ask similar questions, that what is next? And by communicating this knowledge, this interest, this technology to others, we are hoping, and by kind of abstracting some of these ideas, we are hoping to engage broader communities to contribute to quantum technology, create a culture around quantum technology, and hopefully help us find what is next. Thank you.
So if I may, I would like to say a few things that are quite provocative. First of all, quantum technology is not only quantum computing. And I have major arguments with some of the directions that quantum computing is taken, especially with IBM and Google, and especially because I'm familiar with the technology and I talk to some of the IBM people that are in Israel, so I know what's going on. And when you are able to reach 10 to the 4 qubits, tell me about it. I'm not even dreaming about it. It's a major challenge to get to 1,000. I have some arguments with some of the others, but I want this for another time, another discussion, and I can tell you exactly the pros and cons of every one of the technologies and which one has the chance. And, maybe none. And, but putting that aside, quantum technology is not only computing. There's a lot to say about that. A lot of that is already in the working. Yeah. For example, atomic clocks are quantum technology, and atomic clocks are extremely important for quite a few years now, I'd say at least a couple of decades, for many things. And there are many others. So I think I'm a great believer in the quantum revolution, but not necessarily in the quantum computing. Never mind that in terms of education and in research, and university research, that is actually very important. So that I have no doubts. I want to say, in addition to that, also about the computing, that you may want to listen to Ilya Ablonovich when you get a chance, or maybe invite him here. He talks about quantum-inspired computing. And the reason is very simple. If you put aside all these nice directions that we would like to do, if we have a quantum computer, for example, to design drugs and for personalized medicine or everything of that, at the end of the day, most of the applications of quantum computing, when we have a real one, not 100 qubits and also not 1,000, because these are good for nothing. They are good for shows in the cover of Nature and Science, but nothing more. They can't solve a real problem. But when we have one, it will be mostly optimization problems, solving optimization problems. And there is a direction that was inspired indeed by quantum computing, but it's not quantum. It's, I would say, pseudo-quantum. D-waves, I saw there, I think Olivia put there D-wave. D-wave doesn't do quantum computing. They do pseudo-quantum computing or quantum-inspired. But there are several other companies of that sort, and they are able to, one of them was founded, by the way, by my former student, Marin Soljacic, and another one by Ilya Ablonovich. And what they do is actually, they do solve optimization problems for real, like the traveling agent and all these kind of things that the classical computer cannot do. And they do it using some, this is an analog computer that is based on nonlinear devices that self-synchronize, or they actually do like self-annealing and things of that sort, only smarter, okay? So that's another side one. Another thing, another remark that I want to make is that quantum technology, in my opinion, or education towards quantum technology, after the bubble will explode, and it could explode, what is happening today, okay, at least the computing bubble could explode, and like it was in 2001 when the photonics bubble exploded, and there's still a lot of industry there and a lot of R&D in photonics, despite the fact that the field received a kick in the ass for several years. So in my opinion, at the end of the day, if quantum technology will be built mostly by engineers and less by physicists. I'm telling you that as a physicist. So I'm bothered by the figure that you've shown, that most of them are physicists, and I wish them good luck in making something really working, because the engineers will do it, electrical engineers and mechanical engineers and things of that sort, because eventually you need to put the pieces together, and physicists are not very good at that. Actually, this is really work for the engineers. So in the Technion, what we are doing is actually we are trying to teach quantum at the different disciplines. For example, in computer science and mathematics, we want to teach them, they don't need to know quantum at all. We give them a class, just like in electrical engineering today, you teach at the beginning some algebra, you know, all these AND and OR and NAND and XOR and all this, okay, exclusive OR. So this is how we start. by giving them some axiomas of quantum information. And from there, we teach them actually Adamant gate and also, for example, a guy that took these classes is sitting right here, my student, Ziv. So he knows with this class. So we have a elementary class and more advanced class that is intended for people that don't need to know quantum at all. They just need to know what are the arguments or what are the axiomas from which you can develop them. I highly recommend that here too will be a class or two classes of that sort, because you need to prepare the computer engineers one day to do also to write, to be able to actually write something and think about it the way that computer engineers are thinking. Same goes for electrical engineering. There are already quite a few quantum-related technologies. For example, there's one by the name of Quantum Machines. It's a company based in Tel Aviv in Israel. What they do is a compiler and a controller. So practically speaking, the control system of a quantum computer, today, I think all the quantum computing companies, including IBM and Google, including Chris Monroe's company and Rainer Blatt's company, and all the others are talking to them. Some of them already bought their box. So they have a box that looks like this. And what the box does is all the control system in the quantum computer. If it has 30 ion traps or whatever it has, it organizes them and also works as a compiler. So the user is sitting there. All of that was designed by people that know electromagnetism very well, and they do not need to know quantum at all. They need to know what is the input-output for the quantum. Those need to be educated as well. And it goes like this, and the mechanical engineers and so forth. So in my opinion, and this is the way that the route that we've taken the Technion, is to try to teach, not to bring the people in computer science to become experts in quantum mechanics, but actually to teach them the necessary part so they can actually do something important in their own discipline and contribute to the quantum technology. There is more, but it's good enough for now.
Are you sure? Okay, actually, this is starting to get into a topic that Erica had brought up earlier with me through email. So quantum is obviously a deep and challenging topic with many non-intuitive twists and turns. I'll start with Olivia again. What is your philosophy about how to build the on-ramp so people can begin working on quantum technologies without oversimplifying the quantum concepts?
Yeah, that's a really good question. So I guess it depends on like what age you're really talking about, but I guess when we talk about like K through 12 initiatives, like the government NSF workforce panel that I serve on, I always say that when you're talking to, elementary school kids, middle school age kids, maybe even some high school, I don't really care if they understand quantum mechanics. Like I'm not trying to teach them quantum mechanics. I'm not trying to teach them quantum computing. I kind of just want to blow their minds a little bit. And if they walk away just thinking like, oh, that was cool, like job well done. That's it. That's all I'm trying to accomplish at that level. I don't think we need to like work to teach them, the exact precise nuances of what's going on. I think when I first learned that quantum mechanics like existed and was a thing, somebody just showed me like a double slit experiment and video of like single electrons going through a double slit and like didn't explain it. Like they just showed me what happened. And, the result is obviously very counterintuitive. And so I just walked away and I thought like, wow, I don't understand this at all. And I think if you can just sort of convey that like nature is a little bit more complicated, and a little bit cooler than you think, that's it. That's good.
I don't think that there is a danger of oversimplifying it. And I agree. We just have to, as you said, excite the kids and society. And we have not oversimplified other technologies. I mean, if you think really clearly, then you can communicate it to a lay audience in such terms that they would understand it. But this would not be oversimplifying it. It would just be making it accessible to everyone. And as you mentioned earlier, our goal is to make quantum accessible at different levels everywhere. And there has been a lot of discussions about starting teaching quantum really, really early to kids. And I'm sure Mari could talk about this more, teaching quantum without any math. But there is an opinion that all the education, especially for young kids and K-12 is deterministic. If we would, for example, teach them the probability That would be much, much better start into quantum world and quantum revolution. So again, I think there are a lot of things we can do, but we shouldn't be worrying too much about making it too simple.
So I struggle with this a lot, actually, trying to communicate quantum concepts to the general public, because really there are, at least when talking to the general public, there are two audiences, right? The primary audience is the general public, but the secondary audience is experts in the field, okay? And they're very, very different. They have very, very different concerns about what gets communicated, right? For the general public, I want to inspire them. I want to get them excited about that. I want them to understand enough to see how interesting it is. And, I don't want to teach them anything they're going to have to unlearn later if they go deeper, right? But then, the experts in the field want it all taught absolutely correctly. And as one of the experts in the field, I'm very much on board with that, right? I refuse to communicate stuff to the public that's actually wrong. So my role model for this is Richard Feynman. Anybody out there read some Richard Feynman book? Okay, all right, yeah. Well, if you haven't yet, you got to read his stuff on quantum. So go to the Feynman lectures and read his quantum stuff. It's absolutely beautiful, right? So without telling any lies or oversimplifying anything, he just takes you right to the depth of the whole subject. And I think it's very, very beautiful. So anyway, Feynman's my inspiration for this. But when, say, communicating, for example, a recent discovery that's got some deep subtleties in it, right, to the public, I rely on people who are, experts in that particular area to check it, right? So, so right now I'm working with a particular lab developing a video about what their discovery is. Obviously, I work on the content and then I let them check it before it goes out the door. So I have to post a retraction later or something, something along those lines. But, so I like the challenge very, very much. I like the challenge of what's the minimal, especially this goes along very much with what theoretical physicists do, right? We want minimal models. I want to know what's the minimum amount of information I need in order to get a chain of logic going, and then what's the least number of steps along that chain of logic to get from point A to point B. And so I apply that to this communication idea. So for example, I think it's important to make a distinction that just because something happened in the historical development doesn't mean we have to teach it to people trying to on-ramp into quantum. Okay, I'm going to give you an example of that, the Bohr model of an atom. We don't use it, so we don't need to go through that, right? The real thing that's going on there when you have an electron hanging out around an atom is that you have a three-dimensional standing wave. So we should just go straight to that concept, just build it up. So that's the way that we're working on, for example, introducing these things, say, into high school chemistry classes, right? To understand the chemistry of the electronic orbitals as arriving just based out of standing waves. And any kid knows standing waves because they've all played with slinkies and jump ropes, right? So we start there with the slinkies and jump ropes, take it into the two-dimensional realm of drumheads, and then do actual computer visualizations of real calculations that show people the real deal. So anyway, I'm constantly thinking along those lines of what's the minimal amount, what's the minimal argument we need to make to get somebody from where they are to where we want them to be without making any unnecessary detours. Why should we trouble with them with that? And without, of course, leading them down a wrong path.
Yes, so I think oversimplification is good, and I agree with that to some extent, but I think misconception is not. And I think this discussion that we have had with Erika and Professor Melekşe in engineering education, almost every day, every week, we're trying to think what kind of analogies to use to avoid misconception for K-12 students. And this is what kind of examples you come up with to avoid misconception is very important. So one way that we try to approach this, at least for K-12 students, is that we try to develop hands-on activities, something that a student can do, can play with, and try to experiment with those. For example, whether it's QKD or other things. That's what I think the hands-on part is helping your students to get interested, to learn better, and also go after and kind of learn about that more. And at the university level, we also have MicroMaster degrees here at Purdue, and these are specifically developed for engineers. And every year we have approximately about 50 students, and these are professionals who are working in the companies for more than 5-10 years, and now they want to learn about quantum, so they can use that in their work. And that is what we call a MicroMaster degree, which is a 1-year degree. They take 7 credits, and we have developed 3 to 4 courses specifically designed for those students who do not have any background in quantum. Now, that doesn't mean that we don't use any math, we don't go in depth, but we try to carefully choose the topics that they need to learn. And we ask companies, what is it that the students or your workers need to learn, so we can help them in that as well. So we are careful in designing the courses. We're careful in working with companies as well to, for example, we work with Microsoft, and we try to use the computational power they have, such that we ask our students to log into a quantum hardware and not necessarily learn how to program a quantum computer, but do experiment with quantum computer. And we also have support from INQ as well, that they gave us free access to quantum hardware to develop some kind of examples where a student go connect to the hardware, run a program, perform experiments, explain their results, and provide explanations about their observation. And I think that kind of hands-on part, hands-on activity would help us to kind of bridge that gap a little bit and have a little bit of depth as well as breadth.
So generally, I agree with the speakers, actually, most of them, including you. And I want to say several things. First of all, we like to talk about the quantum revolution, but actually there have been 2 quantum revolutions. The first quantum revolution is the old one, where we can probably think about it as de Broglie. In other words, that every particle is a wave. That's the first quantum revolution, and this you can explain intuitively also to high school students through wave mechanics. The second quantum revolution, which I would call it John Bell and maybe Alena Spee, is entanglement. That I find that you can formulate it in terms of the math, but it's extremely difficult to explain because the intuition is not there. Certainly not for graduate students, and I would say also not for professors. So most of us do is we put aside the paradoxes, and there are plenty. I'm not sure how much of you guys know. I would suggest read a book by Akira Aronov that talks about quantum paradoxes. There are plenty of them, not only the APR, Einstein-Podolsky-Rosen, but there are many others. These are difficult to visualize and to understand, to grasp the intuition. But what we do in that, what I think should be done, is to look at the result of the measurement. This is really the way to convey it, and it's difficult to train the students to get them the intuition. So the first quantum revolution is easy to teach. The second one, very difficult. Now regarding Feynman, it is interesting. I was a young postdoc when I came to Caltech about 1.5 years after he passed away, and the ghost was still there.
We're contemporary. I got there a couple years after he passed away as a freshman.
Yeah.
We must have seen each other.
So I probably took a class. So Kip Thorne was teaching his class, and I gave every year 2 lectures in that class. So let me tell you about Feynman lectures on physics. You can read about it there. Feynman did not write a single word in that book, in the 3 volumes, not even one. So the idea was that the story goes actually before that. And maybe it's good that the audience hears it. So America felt a great country, built the first nuclear bomb, the first nuclear reactor, wonderful. And then one day they woke up and there was a Sputnik in the sky. So what's going on? They had a committee with Richard Feynman heading it of what did we do wrong? What should we change? The outcome of that was, which was really in Feynman's spirit, he said, look, the way we were teaching physics to the young people is we taught it the way that we learned it. It was discovered. So we need to give them the flavor of modern, truly modern physics. We cannot really teach it the way that things have developed, including fluid dynamics and everything that was known, all the mechanics and so forth, and then reach quantum and the interesting questions only at the end of the PhD. We have to reverse it in some way. And this is why, since then, we teach according to the Berkeley series of physics, where we teach special relativity in the first semester. This is Feynman's inspiration. Now, Feynman said, okay, and I will show you how to do it. And let me teach a class. And this is the class that he used to teach at Caltech. So at the beginning, the class was full of undergraduate students like you were, and they came there and nobody understood a thing. And then, so they sat there because this is the famous Feynman Nobel laureate. And after a month or so, the class, all the undergraduates fled away. PhD students came and some of the professors. And in the end, when he was teaching the third volume, only professors remained. If you notice, the book was written by one of the students who himself became professor at Caltech, not by Feynman. Now, instead, so after Feynman realized that this is an issue, so he had set aside a separate class that he called it like modern physics, or lectures in modern physics, where we would bring topics, just different distinct topics. And this is the class that you took, Erika, I'm sure. And the person in charge after he passed away was Kip Thorne. Later on, 2019, he won the Nobel, 2020, he won the Nobel Prize also. And Kip Thorne brought famous people to teach sections. I was a postdoc with Amnon Yariv. So Amnon Yariv was teaching the section on lasers and nonlinear optics, whatever. But then he wasn't on sabbatical, and he asked me to replace him. The students loved it, so I taught it 2 years in a row, but 1 week at a time, just 1 week. All the rest, they brought famous people to teach the class. That is the class, and Feynman envisioned it, but in the end, the Feynman lectures on physics, if you read it, it's for the experts. It's true that he doesn't use the math, but if you don't know, if you come without knowledge, the chances that you understand that the deep concepts there are slim. Okay, so I also use some of the examples in my graduate classes or in the senior, or I would say maybe not the freshman year, because I'll scare them away. Now, regarding what you said about educating, it's important to separate the experts from the public, because the experts will drive you crazy if you want to teach to the public. And I think the way to teach it is really through intuition. And with respect to entanglement and all the concepts that came out of that, which is really the current quantum revolution, I think to do it is through experiments. If you do a Hongo-Mandel experiment, this is more educational than 100 movies and presentations. Just to do the experiment and see the dip, you start to understand what does it mean to have entanglement. I think this is really the key. There are about 4 or 5 experiments that are crucial. This is one of them. There are several others. There are key experiments, and from that, they maybe can develop some intuition, at least believe you that entanglement is real. It's not some balloons in the equations.
Thank you, Maldi. Okay, we have about 10, 15 minutes left. We can open it up to the audience if anybody has any questions. Yeah, multiple. Ethan, do you want to grab some of those? Yeah, perfect.
Thank you. I asked this question from the perspective of a grad student. I understand that a robust quantum workforce is going to be teamwork between teams of theorists and experimentalists, software experts. To what extent do you think individuals in a quantum workforce should branch out or specialize in any of their fields or any of their areas? And if they should branch out, for example, if an experimentalist should also know a little about how to write algorithms or how to compile circuits, what are good ways to learn to do that in school?
So that's a great question. Obviously, I mean, if you have time to learn about other topics, other areas, that's helpful. So one of the things that we do here at Purdue here, we have created this, what we call Quantum Game Club, where we have students from undergraduate students and graduate students coming to this kind of club, weekly meetings. And we don't ask them to do anything outside the club. So we have access to quantum hardware, free access to quantum hardware, including IonQ and Rigetti and others. And we are teaching our students how to access a computer, how to program a computer and things like that. And our motivation is to teach a student about quantum algorithm a little bit, but not really asking them to take a course on that, and just give them a little bit about what is out there, what are the opportunities. So I think it depends you don't want to spend too much time basically branching out, but I think a little bit of, going outside your comfort zone is helpful.
Oh, sorry.
you want to?
One thing I was going to add is I think, if you're an engineer or a physicist, an experimentalist, probably what might be more important than learning how to compile circuits is just, working on your programming skills. I think the better programmer you are, the more successful you're going to be in any tech career. So I think that is probably the most important skill to sort of add to your skill portfolio.
I'd like to add a comment that is for the experimentalists and also for the theorists, but mostly for the experimentalist. A good experimentalist is someone that understands what he's doing and can simulate it. So if you consider yourself an experimentalist, at the minimum, you want to play with the equations and simulate them. Otherwise, you cannot really always say, okay, I have a theoretician next door that will whisper in my ear. That is true for everything. Also for quantum, you need to know what you're doing. That's a crucial issue, and you need to master the theory. Even if you will not develop new theories, at the very least, you need to master it and be able to carry out a decent simulation to understand what's going on. The second thing, the second comment related to that is that physicists everywhere miss one very important class, and this class is called signals and systems, where you show that Green theorem is nothing but the convolution on the impulse response, and you need to understand a little bit of what happens with linear systems. And that, I think, is crucial for everyone to understand a little bit, for every physicist to understand that there is also technology, and that class is really the key to technology. So for the physicists in the audience, I highly recommend, don't be shy, go to take that. It's usually being taught in the second year, like the second year, the first semester, the second year. Go take it and make sure to do the homework, because it's a crucial class that will teach you to think a little bit about technology. That's the key to technology.
So far we've had a lot of great thoughts on, the recruitment side through how do we teach this to people, and as we turn to the retention side of the quantum workforce, my thoughts return on Dr. Lane's, excellent observation that there's culture, and that is very important. That if you don't like the culture you're in, right? I mean, that's how you lose people. We're not going to retain people if they're not okay with the culture. And so, one way I kind of want to just break it down, because there's many ways to do it, but I think this one is most interesting to me, is that I think culture can be broken down along the lines of generational divides. That as we look towards both academics and people in industry, it takes a certain amount of years of experience to get a certain position. And so, certain positions are occupied by certain generations. And so I just want to hear some thoughts on, how do we set policies, or how do we negotiate those generational differences moving forward as, we recruit new generations into our workforce, and, we start to ascend into those levels where we get to make policies, and we have to keep in mind that maybe our generation has a certain working style and the other ones don't. And, they bring all sorts of different things to the table. How can we start to look forward to that, anticipate that, and, move beyond just negotiating differences, maybe having symbiosis between generations?
That's a really hard question to answer, but I think the most important thing that you can probably do when you're in a position of leadership is to listen to the people that you hire that might be from a younger generation. I mean, we're seeing all of these older, more established companies now who are losing, huge chunks of their workforce after the pandemic because all these workers don't want to go back to the office, right? And like the older generations are like, no, the office is where we work. Everyone's going back to work. This is where we work. But no, we're done with that. Like younger generations don't want to have to work in the office anymore. And it's really important to listen to the people you hire and listen to your workers, or, they're going to quit. They're going to leave. I think we're seeing a paradigm shift where the power is no longer necessarily on the employer, but it's on the workforce. And so know your power, use it as a negotiation tool. And if you're in a position of leadership, don't be condescending, open your ears. And if you create an environment that people want to be in, they will be in it. Otherwise, they're going to leave. And then, who wins then? Not you.
I'd like to kind of change the question, and I think it's not our duties or our responsibility as educators is not to necessarily fill those remaining jobs in the industry. Yes, that's important, and I think we are trying to do that as well. But I think at a different level, as an educator, we are trying to kind of teach science, teach engineering to kids, to a student. I think that is important, and we shouldn't miss that point. And it's not just about the technology, about what's going to change the world. I think it's more about how do we teach kids to think, to innovate. I think that is very important. And I think related to what Moti said earlier, it is important to kind of communicate those pieces of science very well to a students, and you need to be very careful about what those are. For example, one thing that we do with our students, as I mentioned earlier, that misconception is very important, right? You don't want to oversell a technology. You don't want to just create misconception and all of this to students. But how do you communicate these profound kind of topics? How do you ignite or how do you make students interested in some of these topics? And what you said, signal is one thing for grad students, right? For undergrads, but at the lower level, I think something that has a lot of, you can take it anywhere, is information, right? Information randomness. You don't need to get to entanglement, right? You can talk a lot about randomness. You can relate. One thing that we do, we try to relate quantum data that show randomness to art, at least represent those data in some kind of art that people can look at and try to tell the difference between a true random data and pseudo random data. And when you think about it, like at the art, right? When you try to explain art to kids or to anyone, right? If I draw something, let's say a car, a house or something, if you understand what that is, right, that becomes very quickly boring because there's nothing there to see. You understand what that is not art, right? Art is something, or what we call modern art these days, is something that you don't get to the bottom of it, right? And information is amount of randomness in a message. The same goes for art. If you try to depict, visualize random data and be able to explain randomness to kids, I think that can have that. First of all, there's nothing that will go wrong in terms of misconception. That's kind of open-ended and help a student think about it. And you don't just give an answer to person. You just open a door that a student can just keep reading about it and learning about that. So I think when you say culture, I think what we mean by culture here is the culture of learning complicated, interesting things. And yes, there should be some motivation for that, finding a job, but I think in general, there's more to that.
I think if I am to answer pointedly the question that was asked, is I don't see that there is a real generation gap in terms of the work itself. There may be a generation gap in the preferences of people, how to do the work, whether to do it at home and so forth, or to come to the office or to the lab. But in terms of the work itself, I don't think that there is a generation gap whatsoever, because the people that are project leaders still need to be in the technology, to understand the technology. They can't really be superficially and come with some Gantt table and the Gantt chart they can do it if they are much higher up, but at the project manager level, they can't do it. So actually, I join my opinion is just like his, that we should really articulate very early on, give some inspiring examples to the youngsters, including undergraduates and high school students. And the way that I try to do that is to give examples from cutting edge discoveries. So I'll give you an example. I was teaching like freshman physics 2, and this is like 2001. And Freshman Physics 2 is electromagnetism from Ed Purcell's book from the Berkeley series. I think that you teach that as well, no? From that book. So on that day came out the paper by Ferenc Krauss and Paul Kurkum on attosecond pulses, the first isolated attosecond pulse. By the way, these guys will be receiving the Wolf Prize, which is probably the highest predictor, the best predictor for the Nobel. And they will be receiving it next month, the Wolf Prize. It's Anne Lullier that made the first discovery, and then Paul Kurkum and Ferenc Krauss. So what I did then, back in 2001, on that day, I stopped the class. I said, today, we talk about something that is electromagnetism, but this is something that came out today. Let me explain to you how you do that. And let's imagine that you have a pulse of electromagnetic energy that is so short. Let's see what this time scale says, and let's see and this and this. I didn't teach them the science. I got them inspired and understanding that there is a revolution coming up. And they did. Today it's called attosecond science. And I do it quite often. And I did it on several other major discoveries. I did it when the LIGO started to give some interesting results. My knowledge in astrophysics is not so high, but I was still able to explain to the undergraduates what's going on and what is a LIGO, especially that I knew the persons. So that's, in my opinion, this is the way to get the younger generation excited, is through examples. The examples are not only experiments, but actually to bring something that happens now. Something that, and you can explain, they don't need to explain it deeply, but at least to talk about it and tell them that there is still new discoveries being made all the time.
All right. So your original question, I think, was about maybe a generational. Oh, it's no, okay. All right, I just have to get a little closer. So, your original question was perhaps about a generational divide, right, between people entering the field and then who's in management right now. And that happens everywhere in every industry. It happens in academia. And there's lots of demographic ways in which you could find yourself as somebody entering the field or entering a company at odds with your boss. And so I think it's just a great question in general. Like, what do you do when you're at odds with your boss and you want to kind of tweak things a little bit when you want to tweak a higher up? I've been in that position. I've had to change a dean's mind before. And, it was one of those situations where, like, those of us at the faculty level thought the answer was so obvious and the dean was going a different direction, and we did it. But the general principles I would recommend are respect. Just, this person has earned their position for a reason, right? And, each of us may eventually be in one of those positions where the people that we're managing or leading may disagree with us, and just think through how you would want to be treated, right? How do you want to be treated? You don't want to be surprised in public. People are much more likely to change their opinion about something if you have private discussions with them. So, and I would just, advocate just that mentality of respect, right? Especially when somebody's higher up the chain, they have a bird's eye view that you may not have. That's extremely important to acknowledge. Actually, this, my dad is an electrical engineer, actually, who's been president and CEO of multiple companies, and I just kind of got this perspective growing up of he would have these situations where he's leading everybody, he's got the whole big picture, and people in little bitty pockets who didn't have the big picture would think he was making wrong decisions. Okay, so just be mindful of the fact that somebody higher up the chain has a broader perspective, and just, I would say my advice here would be humble about it. I know I don't have the perspective you have on this whole thing, but from my point of view, this seems like a good idea. And talk to the person in a way that you're going to leave the door open for future discussions. It's never a good idea with anybody, especially a boss or somebody higher up the chain, to be disrespectful and belligerent and act like they're crazy, right? That's definitely not going to get you in the door the next time that you want to change their mind. So, patience, persistence, humility, all these character traits will help you, because this is going to come up. You'll be in that position eventually. There'll be something you want or a team wants that the boss is not on board with, and very humble, persistent, patient advocacy in a way that you feel like you would respond to well if you were the boss is the way to move on those. Good luck with it.
Maybe just like a quick question about entanglement, and maybe we should really, should also challenge the student, Because if you look at the phenomena like tunneling in quantum mechanics, when we teach tunneling, we say this is a quantum phenomena, there is no classical analog for this. And then we know that if you go to imaginary time, you flip the potential and we can run a classical trajectory and get tunneling. And maybe, I mean, now we don't know how to explain entanglement, but the question is what we should do to calculate tunneling using classical mechanics. As we know, like each quantum mechanics, there's a d+1 in the d dimension, there's d+1 classical system. So I'm still struggling with this, but maybe we challenge our student. Maybe they will figure out how to do tunneling with classical mechanics. And then we get to the bottom of this one.
Thank you, Sabri. Okay, that is all the time that we have. No, that's totally fine. Modi, did you want to follow up on that or?
Hey, hello.
On that note, okay, please join me in thanking the panelists once again for this wonderful discussion. With that, we're going to have a break until 4 o'clock, and then Nick Braun is going to be giving a lecture. Hello? Hello? Okay, cool. We're going to go ahead and get started in 1 minute.
Situation where
Wait, so are we recording from your laptop?
no. What
The
gets
Zoom is in
recorded,
here.
The live stream is gonna have the best quality view, but for just no one else, the only way we can get it up to the projector. Yeah.
Good? Okay. Okay. Welcome, everyone. This is the last lecture for today. Today, we have Nick Braun, who is a researcher at IBM Quantum. Hold on 1 second. Yeah. Okay, so Nick Braun is a research staff member in the Experimental Quantum Computing Group at the IBM TJ Watson Research Center in Yorktown Heights, New York. Since joining IBM in 2013, Nick has been responsible for qubit device design, packaging, and cryogenic measurement, working towards scaling up larger numbers of qubits on a device and integration with novel implementations of cryogenic hardware. He's also the unofficial Qiskit guy. So without further ado, Nick Braun.
Thank you very much for that introduction. I actually am also the official Qiskit guy on the Qiskit YouTube. So let me clarify that. So that was kind of an old bio. I used to work on hardware and developed a lot of the hardware that IBM is using today in our, our effort to build a superconducting quantum processor. But for the past 2 or 3 years, I've moved over to the Qiskit side. I'm doing software. I'm working with Olivia, and we are building we're essentially building a group that's focused on helping researchers use Qiskit for their research activities, whether they're using it on our IBM systems or not. So what I wanted to do here was a highly technological thing where I'm going to take you through a Jupyter notebook of a recent publication I have, which is here. This was put on the archive about a couple months ago, and it's about doing quantum simulations. And I'm going to show you how I did it in Qiskit. It is all currently available. If you look in your email, you should have had a link at the Qiskit research repo. I have all the code that we used, all the data we have, the manuscript and everything. So you can see what I did, and I'm just taking essentially a subset of that and presenting it to you today. And what I'd like you to do also is, as you have questions, I want this to be very interactive. So you can feel free to just yell at me. I will repeat the question for the YouTube audience, and we can go and do it that way. So I hope to make this interactive. There's a lot of things to cover. I think if you have questions early on, that understanding is more important than what happens later on, where I just kind of blow through the data and analyze stuff and the like. So far, so good. Okay, excellent. So this is the recent paper. This is a follow-on of some other Majorana work I did. I got in touch with a condensed matter theory group, and we have been working together, me and this postdoc, John Stinger. He was the one that was doing the hand compiling of pulses on our previous project. And I told him we would never do that again. So another project came on,
with my colleague Gilad Ben Shah, who's the first author of this paper right here. He was also a theoretical condensed matter physicist, and he did his PhD on Majorana modes as well. And interesting thing is Gilad went on to work for Boston Consulting. He became a consultant, and then he came to IBM, and we worked together in the IBM Quantum Network with regards to startups. So IBM works with many, many startups, and me and Gilad supported them, and that's how I got to know him. And I think the last thing he wanted to do was he kind of missed doing physics, but not enough to actually do it again. So he decided to bring this to my attention and figure out how we could actually implement his PhD thesis on a quantum computer. So basically, what he's doing is he's looking at this thing, some sort of typically a nanowire. It would be semiconducting, and on the I guess I don't have a. Do I have a pointer? Don't have a pointer. Okay. Anyway, that figure on the upper or on the right there, but the left version of it, what you're looking at there is just a semiconducting nanowire that has some sort of oxide between it and a gate voltage that you can apply. So this can be described by a very simple model given by this Boloigravov, the Jin Hamiltonian. I always mess that up. And that's not very interesting when it's just sitting there like that. It's topologically trivial, but when you add a superconductor on top of it, you can proximatize that nanowire. And so you can make that delta term in that BDG Hamiltonian non-zero, and you can get some interesting physics. Mainly what we wanted to study was this topological regime where the black corresponds to even charge parity states, the white corresponds to odd charge parity states. When you go into the topological regime, you only stay in the even charge parity for this example. So that's considered to be topologically protected, and this represents a topological phase boundary. So that's what we want to study. And then the other thing we wanted to think about is this BDG Hamiltonian is easily solved classically. It's a quadratic Hamiltonian. You can describe with fermion and Gaussian states. What we wanted to do was look at an interacting model where we have electron-electron interactions, because that is actually something that a quantum computer would be able to beat a classical computer at, maybe in the near term, for example. So far, so good? All right. So that was a lot out of the gate. What I wanted to do was take a step back and just describe, what are the processes I go through to do quantum simulation. And the first thing I kind of like is this review paper right here. You can think about a quantum system in the cloud. It just kind of exists there. It does its quantum thing, but you might want to understand how it works. It evolves under the unitary evolution from the Schrodinger equation from time t equals 0 to time equal t. And you say you want to simulate that, but you don't have access to that system. But you have access to something called a quantum computer. So maybe you can prepare an analogous state psi and have that evolve under an analogous Hamiltonian or analogous unitary u prime to the time t, where you have to then prepare the state so it looks like the quantum state you're starting with, evolve it under this analogous u prime, and then do a measurement of it. And then you can correspond those two together. So you can learn about the properties of the quantum system by preparing and evolving an equivalent kind of Hamiltonian. And so this is, kind of basically the idea of a lot of, at least Hamiltonian evolution quantum simulation, is you want to be able to prepare, evolve, and measure. And these things, there's many ways of doing this. And I'm going to show you a couple of them in this kind of new way we introduced that is very conducive to kind of near-term noisy quantum hardware. Okay, the other thing you have is you need to map operators to qubits. So a lot of times we're simulating electrons. Electrons are fermions. They obey certain anti-commutation relations. So, for example, you have this molecular Hamiltonian here that you might describe, and you need to map that onto something called qubits, which obey these commutation relationships, which are not the same because they're represented by the Pauli matrices. So you need some sort of mapping there. And there's lots of ways that are known to map this. Like, for example, you can use the Jordan-Wigner transformation, which just maps the creation and annihilation operators to these Pauli operators. And then you put a bunch of Z's to the left, basically, so that you get what you want out. And as Sabre said this morning, there's lots of different ways. In fact, there's new molecularly efficient ways of encoding that, like IBM has even researched. But typically, you're like Jordan-Wigner, Bravi-Kitaev, or parity mappings. Those are ones that are available in Qiskit and you can just use. So just to give you an overview of what we're studying here, in the Majorana zero modes are these fermionic particles that are hypothesized to be their own antiparticle. They are predicted to obey non-abelian statistics, and they're predicted to arise as a non-local pair in like a semiconducting nanowire that has been a semiconducting nanowire that is also a P-wave, or not also a P-wave semiconductor, but has P-wave superconducting coupling. And that is kind of induced experimentally by proximatizing typically high spin orbit coupling nanowires with S-wave superconductors. So that's how you try to realize experimentally. Of course, that's a very difficult problem that I'm not going to touch on here. I'm going to talk about the theory of these things and how we simulate them. So what this looks like from a very simple model is something called a Kitaev chain, where we have, if you can see right here, the kind of ovals here, there's 4 of them. Those represent the composite fermions. Those are like electrons themselves. But you can think about each of those composite electrons as being made by Majoranas, which are the blue spheres. And normally they're combined like into an electron, but if you have a chain of them, then you can tune the parameters mu, which is like the on-site, which is like the chemical potential, and then the coupling term T, which is the tunneling rate between adjacent modes. And then if you added this superconducting pairing gap delta, you can realize these Majorana zero modes. And then if you added a on-site term, so an interaction between these fermions, then you would have an interacting Kitaev chain. And so then what I'm going to do is I'm going to show you how I broke down this problem with my colleagues, and we implemented this using Qiskit, and we ran simulations on the IBM Quantum backends. All right, so far so good. So just like I said, this was the hardest thing. I can just import a bunch of libraries, and I can have Qiskit do a lot of my work. So for example, these ones here at the top are for building circuits and accessing my account. Here we have ones, I guess you can kind of see the cursor. Here you have ones that are dealing with the fermionic operations and transitioning those to poly operators. This Qiskit opflow deals with manipulating these operators. We have the transpiler, which is a way of turning an abstract circuit into a concrete circuit. And that's kind of where the hardware meets the software. That's where I do most of my work. All my Qiskit contributions are essentially in the transpiler, because what I'm going to show you is that it's actually very good to know a lot about the hardware, because you can figure out tricks, ways to implement it more efficiently, ways for you to reduce errors. And this is kind of an ongoing thing that we at IBM are working on. So that's loaded. I have your basic, some other things I'll show you with visualizations and how we represent circuits. Then I'm just going to load my my IBM account. So I'm using IBM Lagos. It's a 7-qubit machine arranged in an I. And I'm going to only be using 3 qubits from that to represent a 2-site Kitaev chain. And then I'm going to get some backend information. So from all of our backends, you can get information such as the coupling. In fact, you get the whole Hamiltonian if you want. You can get the T1, T2, gate errors, single qubit, 2-qubit readout errors. All this information is available via Qiskit, no matter whether you have an internal account like the one I'm using or an open account. All this information is downloadable and retrievable. So basically, what we want to do is we want to look at this Kitaev chain Hamiltonian. So I told you in the picture there was the mu, the chemical potential, and T, the hopping term. So that's the second quantized version of it. And then if we want Majoranas, we add that delta term. So that adds a superconducting pairing. And we add for the to add the interactions between the fermions, we add the U. And that U term actually is what makes this difficult for a classical computer, because of the non-quadratic term. So basically, there are libraries now, and these libraries did not exist when I did my first Majorana paper on braiding. In fact, we did the Jordan-Wigner transformation, we tridorized, we did everything by hand, and then we manipulated the pulses and simplified those by hand. And we had some functionality to do the pulse scaling, which I'll show you, which is now in Qiskit. So all these things are like in Qiskit now, and I can just use them kind of out of the box, and it makes it easier for you to try, your ideas for simulations, which this is a kind of new one of. It makes it easy for you to try these things out because you don't have to go and do all the legwork to bring yourself to the point where you can test things. So what I'm going to do is I'm going to define my terms, and I can create these fermionic terms, such as doing these things we usually do these things in strings. So this is like a string of a fermionic operator, and we always go little endian, so the least significant is to the right. So this represents the number operator on fermion 0, and this is the fermion operator on 1. And then we have the raising and lowering operator. So this is essentially a dagger A, and this is a dagger. and A dagger, AA, and then the on-site term. And so we can just combine those and store those as a fermionic op class. And then there's a little bit of a bug where nature doesn't like parameters, but I can convert those using a Jordan-Wigner transformation term by term, and then add them together to get a polyhamiltonian, which you can't really see on the screen, but I assure you it's there. It's a summed op of parameters times certain poly terms. And maybe if I zoom in too much, you won't be able to see it either. But it's down there at the lower left. And so what that means is I've completely just taken a fermionic problem. I've written it down. I've used a transformation to encode it. I could have used Bravi-Katea, but nothing's preventing me from just changing my transformation and changing one line of code, and I can test that out. So that's kind of, these mixes and matches is one of the things that allows you the power to try different things to see how well you can get things to work. So here's an important aside I wanted to do is, as far as quantum simulation goes, once you have that polyhamiltonian, you're kind of like ready to go. You just do some sort of trotterization, you throw it on a system. And we know that from universal quantum simulation, we know we can get exponential speed up if we could do quantum phase estimation. Now, that's a great thing that you learn in the textbooks, and you learn how to estimate the eigenvalues of your Hamiltonian so that you kind of know everything about the system. And you can do this by doing these, establishing this auxiliary register with these zeros at the top. Yep. It's 2, so there was no difference in the boundary condition. But that was something we were considering for going to higher systems. Yeah. It's 2. So the boundary condition is trivial. Yeah. Yeah. So for 3, we were talking about, because we did go to 3 in the paper, but the results were not as good. And then we could start playing around with boundary conditions. Great point. So, if I didn't repeat that, the question was about boundary conditions. There were only 2 sites, so there were no boundary conditions. So for quantum phase estimation, what you want to do is Hadamard all your auxiliary qubits, and then what you're going to do is do controlled unitaries to some power on your simulation register of, say, n qubits or whatever. And you're going to do that k times, and then you're going to do an inverse quantum Fourier transform and measure your auxiliary register, and that's going to give you the bit string that will be your that will have weights in the eigenvalue of your Hamiltonian you're simulating, provided you had some weight of in that of psi naught, basically. So this is like kind of complicated, and if you want to implement this on any kind of current system, we're going to be limited by connectivity, especially superconducting systems, which typically have planar connectivity. So doing these controlled operations across all of these qubits, and I bet Sabre can attest to the controlled rotations he was doing. Those need to be decomposed into single and 2 qubit interactions that can actually be done on our hardware. And you end up getting a lot of overhead because you have to do swap mapping. And essentially, the 2 qubit gates are where all the error occurs. So as soon as you start swapping, you get a lot of errors accumulating, and it becomes very, very difficult to do these kinds of things. So why I wanted to show you this is we know how to do this like perfectly. This was from 1998, but what we're going to do it here is not perfectly, but it's going to be a way of mapping the problem to a system that is much more local, so that we can ascertain the eigenvalues of the system without having to go through all this controlled evolution. So we're introducing something we're calling the spectroscopic eigensolver technique. And can I X this off? Yeah, there we go. That was been in the way for a while. Okay. So we have this Hamiltonian here that we want to construct. We call the resonance Hamiltonian. So basically what happens is you have this thing we call the probed qubit. It's qubit 0 in this case, which means we're doing a Z rotation on it with the first term, and that is being scaled by this energy given by omega, or the frequency. We're adding to that the simulation register, which is being simulated by this H poly that we determined via the Jordan-Wigner decomposition. And then there's a coupling term between them. So we're doing an XX term, but just between the probed qubit and the qubit being probed. So this is only a 2-term interaction. And this would apply for no matter how many qubits you are. It's a local interaction, and it's given by a strength C. And so I did my PhD in experimental condensed matter physics, And I did it in tunneling spectroscopy. And this essentially is doing a tunneling spectroscopy experiment on a quantum computer. So this is the way we started thinking about something because it's very conducive to NISQI architecture. So the next thing you want to do once you have this operator and you want to time evolve it is you need to trotterize it because the terms are not in general going to commute. But here I've already kind of done the trotterization because it's very essential to the algorithm. This would be a first order trotterization where basically we have NT time steps. That's my hand. Sorry. We have NT time steps and we're just repeating the same thing. We're preparing the two sites in this simulation register psi, which we trivially are just using the ground state because it has enough overlap. We're doing rotations of minus omega dt on the probe qubit, which is in the 0. We're doing the trotterized U poly, which I just put 1 over n to the t, because that's going to represent essentially the trotter step we're using, where you can see u to the nt, or you can't see, is equal to e to the minus I h poly dt. So that dt is just our total time divided by nt. And then you're doing this 2-qubit XX rotation in the 2-qubit Hilbert space given by 2c dt. So basically, no matter how many qubits you have in this algorithm, well, right now we just have a single probe qubit, and that probe qubit is only interacting with one of the qubits in the simulation register, which means you don't have to worry about controlled coherent evolution of unitaries, which is expensive. You just have an XX rotation in the 2-qubit Hilbert space, which is relatively cheap to implement on these systems. You're essentially not doing a controlled anything to the entire register, which as you increase these number of interactions to transpile those into single and 2-qubit gates is extremely expensive. So this is like a relatively cheap way of doing things. So far, so good. All right, so what we're going to do is just start building it. So I can build my my resonance Hamiltonian with this function right here. I've got the parameters c and omega. And then what I can do is I can just time evolve this in Qiskit. And I just take my time parameter, call it t. I build my resonance Hamiltonian, and I exponentiate it, which gives me this operator right here. And so inside of Qiskit Opflow, it knows how to handle that operator. I can do trotterizations or the like and turn this into circuits. And that's exactly what I'm going to do. So we actually use a second order Suzuki Trotter transformation with one repetition, but we're going to do that repetition over and over and over again because that just represents what was inside the parentheses. And you can see it just spits out a gate here. So this is oops, how well you can see this. Okay, so so this just represents one of these trotter steps, and you have a circuit. You're like ready to go almost. So that's like pretty cool. I just saved myself a lot of work because I use Qiskit. Yeah, question. That's a great question. This question is, what is a second order Suzuki Trotter transformation? So that's kind of where you do half of the transmit, or you have e to the I a plus b. It's like e to the a, e to the I a over 2 times e to the I commutator of a and b times e to the I b over 2 or something like that. So you kind of like do half the trotterization and then repeat it out of order in the second half, if that makes sense. Yeah. So yeah, so it goes to second order. How do I pick the trotter steps? Okay, that's a great question. Actually, I go into that later, and we do that in the supplemental of this paper. But typically, you want to go for longer times because you get better resolution for this experiment. But you're always going to get hit by depth because you're running this on real hardware, so you have to care about what's actually happening and the errors that accumulate when you do it. So for ours, we had 7. Ended up being the right answer. I think our t was 5 and dt was 7. So yeah. It ended up being 7 trotter steps. Exactly, yeah. So there's always a trade-off between those two. And we did a lot of experiments to empirically kind of learn what worked the best. And we think that this technique is really good, but you do get a smearing of energy levels, so it's sometimes harder to analyze. And if we could go to longer times, it would be a little easier to use. But that's great. That analysis that's deep in our supplemental material, but that's very important. So as we tried this out, really, we just wanted to do this circuit, and if you'll notice, the circuit still has a bunch of parameters still in it. So I'm only using a single circuit, but I want to use a whole ton of parameters on it to explore this parameter space. And actually, one of these things was getting all these transpilation steps to work was a lot of development on my part, because it was so essential that I end up with a final circuit that I could just throw parameters at. So when I mean transpilation, I mean things such as, you have all these quantum circuits, these unitary operations, controlled whatevers. Those things don't exist on IBM Quantum hardware. We know things such as C naughts and square root of X's and RZ rotations. Fundamentally, that's the only operations that you have. They're all implemented by microwave pulses, so you can do some tricks, which I'll show you. So you're essentially transpiling down to 1 and 2 qubit gates. You have to put these on physical qubits, and they're on a restricted topology. So you have to lay them out, and you kind of want to do the least swaps as possible. Each one of these qubits has a certain finite amount of error associated with it. So you want to pick the best ones, especially for a 3-qubit algorithm on a 7-qubit device. That's not difficult, but we have, I think later this week we'll have a paper coming out showing you kind of how we can do this a little bit more scalable. And then you can actually look at the physical circuits and get the pulses out and try and figure out how to do things a little bit better, which I'll show you next. But the point is, you have these abstract circuits, which are great. They're great for theory and analysis and writing algorithms. But at the end of the day, you're putting something on a real hardware. And so you really have to consider what you're doing. And that's kind of where I spend a lot of my time and thinking. So what I'm going to show you is one trick we actually developed for, we developed this for the braiding algorithm. What we're going to do is we're going to exploit the fact that I know how the IBM hardware does 2-qubit gates. So I know how C naughts are made, and I know they're made out of, I know they're microwave activated, and they're built out of ZX rotations of pi/2 in the 2-qubit Hilbert space. And if I know that's how C naughts are built, I can ask the backend for the pulse schedule that does that. I can say, I've got this pulse that does a pi/2 rotation. How about I scale it and I change it? Because I don't need as much rotation because I'm trotterizing everything. So typically in quantum simulation, when you trotterize, you're doing things at relatively small angles in the 2-qubit Hilbert space. So that allows us to try to take these quantum simulation problems and then try to use the more native ZX interaction from our hardware and modify that and turn it into whatever action we really want to simulate. And so that's what we did. And I'll kind of show you an example of this. So for example, if you look at this circuit here, you'll see a lot of these combinations of C naughts, RZs, and C naughts, right? So if you have an eye for this, for doing this for a while, you'll know that that's a ZZ interaction. And I know I can represent a ZZ interaction as a ZX interaction with a couple of Hadamard's. And so knowing that, I know I can do that a lot easier. So for example, what I would do is I could look at the simple version of just one version of those. And notice I have this parameterized, which is important, or was important for me at least. And what I want to do is I want to turn that into something else. So I'm going to use something called template optimization, which I'll kind of describe later while we're waiting for a larger circuit to run. But what I can do is use that technique to then regenerate a circuit. And it's very difficult to see here. I can point at it maybe. The RZX here is parameterized as a function of theta now. And I have single qubit gates elsewhere. I've got a pointer. Okay, cool. So this may look like it's a longer circuit, but it turns out this RZX theta is easier to do. I will incur less error for doing this because theta is typically much smaller than the pi rotation I would have done from this circuit right here, because I have 2 ZX pi/2s here. And the 2-qubit gates are on the order of 0.5 to 1%. So, the C naughts are on the order of 0.5 to 1%. So each time I do those, I am incurring more and more error. So if I can do less of those, then I can be more successful. Yes, Alex, thanks very much. So the question was, did I have to do that manually? Because I just showed a smart choice of gates. And the answer was, on the original paper, yes, we did it manually. Now we have a technique, which is an algorithm developed by our Zurich Research Lab, I'll describe how it works a little bit as I'm executing it on the whole circuit. But having to do that manually is like that's what a postdoc did. That's a fact. So I don't know what to say, but a postdoc shouldn't have to do that because we can build the tools to do that inside of Qiskit. And so that isn't inside of Qiskit now. So we never have to do that manually. There's still a bug in it. I'll still have to fix, but I mean, not me, but I have a workaround. So anyway, you'll see it. So just to give you an example of what this looks like, I want to actually generate the microwave pulses to show you what the difference between these are. And so what I'm going to do is I'm just going to pick up an angle pi/6. That seems to be a roughly typical angle that I'm using in the trotterizations. And then I'm going to do this other thing. This actually does a pulse scaling, which I'll describe, but it takes essentially the C0, it pulls out the cross-resonant pulses, it knows how to scale it. And this is also in Qiskit, but this was not in Qiskit in the previous ones. We had to write this and do it ourselves. So what I'm going to do here is I'm just going to schedule the circuits and I'm going to look at how long they take. So our waveform generators generate samples of in steps of dt. And what you can see here, if I blow it up enough, is that if I use it with just C0s, I have a circuit of length 2,752. Whereas if I use the scaled ones, my circuit's only 1,152 units long. So I'm already doing a shorter circuit. So you already start figuring out that, well, maybe I'm just getting a benefit from suffering from less decoherence while I'm doing this. And that is definitely one thing. And actually, I'll blow that up a little bit. This is from the previous braiding experiment, where we were doing all the hand transpilation and scaling this, or writing the scaling code for this. So this is quantum process tomography data. So we're looking at the fidelity of these operations. And there's two of them right here. The orange ones that are kind of flat, those are the digital ones that consist of a C0, an RZ, and a C0. Actually, there wasn't 10, there was a C0, an RY, and a C0 for reasons that was closer to what we needed. And the blue ones up top are what we get when we use this RZX decomposition as a function of theta to build a YX interaction out of ZX. And as you can see, for small angles, you get much better fidelity. And then for larger angles, as you get down to pi, you get no increase in fidelity because you're doing the same amount of 2-qubit rotation. And so what the bottom plot shows you is what's the relative fidelity improvement of doing the scaled circuit versus the digital circuit. And you'll see it starts off like at small angles around 60% better. And around pi/2, it is still about 50 to 60% better. So this is like our empirical thing, is that we're experimentalists. We think that, well, if you do less cross resonance, you'll get less error. And we show that we were right by empirically demonstrating that you get like a linear amount of error in the angle you want to do, which is a nice affirmation of your experimental intuition, I suppose. So I wanted to show you what this actually looks like. Let's blow this up. Okay. So what I'm going to do is I'm scheduling those circuits, and I've actually made them into pulses. And there's ways to understand these pulses. Is the blue are the single qubit gates, and the yellow are the 2-qubit gates. So the blue ones are on resonant, and they're very small error, like usually less than 0.1%. The yellow are the big ones. Each pair of yellow kind of represents 1% error-ish, to give you a flavor. And those are an off-resonance pulse. They're much longer. Well, they're much longer than the blue ones, but the long blue ones just go along with the other ones. If you want to know what these do, and I wasn't here to talk about hardware, but I'm going to be at the dinner. I'd be happy to talk to you over a beer about how all this stuff works. But basically, just trust me, that's what that circuit is. And if I go to do the scaled circuit, well, I see a much shorter circuit. I also don't see the yellow pulses, though, because there was a bug. So they're not being displayed, but you can at least see it's much shorter in duration, where I've fixed the time range so you could see. So the less yellow there is, I mean, there's no yellow, but if it was there, it would still be a lot less. It hasn't been displayed. And I wanted to just let you know that I went and pinged my colleague Naoki, during lunch, and he's already submitted a pull request to fix this. So by next week, I won't have this problem anymore. It's already gone through the merge, all through the code checks, and just needs to go through code review. So I get results. You can too. And I'm just going to move on from there. But that kind of gives you an idea of like these, the less, I like to joke that the only perfect quantum operation is the one you don't do. And so the less you can do, kind of the better. So So this is kind of a demonstration of that. Okay, so we're going to go from here to actually looking at the back end. And so let's just check out IBM Logos. IBM Logos looks like this. It's 3 qubits in an I configuration. We did this experiment on the qubits 3, 1, 2, the middle one, the top one, and the right one. Now these you're calibrated, on a roughly daily basis. They change, I ran I probably ran these, oh man. These were a lot of circuits. So this took a long time to do. And so I don't remember when I ran this, but this was one of the first runs I'm going to show you that I did on 3, 1, 2. But I think the final data was on different qubits because of, defects in the system, like 2-level systems, things that superconducting qubits suffer from, arose, and we needed to pick the better ones. And yeah, so it's something to pay attention to, I guess. All right, what I'm going to do is I'm going to create a quantum register and a classical register, and I'm going to pick 3, 1, 2 as my initial layout. I'm going to call my native gates. I don't want it to compile to the C0s anymore. I want to compile to the RZXs. And so that's what I'm putting there. And then I'm just going to do a quick check. So what this does is it just looks at the gate error. So I only have 2 sets of 2-qubit gates here. And I just want to kind of see, did I do a good pick? And so if you look really, down here, I mean, like right here, I can see my average 2-qubit gate error is about 0.57%. So on our current systems, that's pretty good. That should be doable for a 3-qubit system. But that's something you want to keep track of. And actually, that's something that we can more systematically score and use graph isomorphism problems, subgraph isomorphism problems to kind of more rigorously approach. And that's actually just like going into Qiskit right now. So these are, we're always developing and always throwing in the latest tricks and tools that the researchers use. I didn't even use it because I only had 3 qubits, but we're using it for another project, for example. So what I'm going to do here is I'm going to do the circuit transpilation. I'm sorry, this template optimization. So this is and I'm going to describe it while I talk about it. So this is the template optimization problem. And basically, I'm going to give you a heuristic of what this does. This was, I don't think it's been published yet. It's been on the archive since 2019. Basically, what it does is it analyzes the circuit. It looks at subsets of a circuit, and then it has templates, and it matches those sub-circuits to these template circuits. And these template circuits are just an entire circuit that has a bunch of gates that equal the identity. And so usually you'll put C0s, yeah, like this. You'll put C0s, you'll put C0s, RZ, C0s, and you'll get out RZXs. So you'll build this circuit consisting of C0s, RZs, C0s, some single qubit gates, some RZX of like the opposite angle, and then that will equal the identity. So you can just make these yourself. And the template optimization will go through and it will analyze your circuit and it will say, hey, do I see a C0, RZ, C0? If so, is it easier for me to do the inverse of the template, of the remaining part of the template? So there's a cost function associated with like, is it easier to do the circuit I found or the circuit that's in the template, which is the inverse of what I could replace it with? So in this way, it's kind of a brute force, but algorithmic way for you to go through a circuit and for you to kind of do this substitution. So then you can do the pulse scaling without having to have a postdoc do it for you. So as you can see, this doesn't always successful. I still have some various C0s, RZ, C0s. So this is actually a known error that I've complained about. It's issue 6975. I've put on the GitHub. We'll see if anyone does anything about it. So right now, what I've done basically is I've written code that gets around it. So it forces that template optimization to happen. And I'm going to combine some gates and stuff like that. So basically, just to give you a flavor of what is happening, I'm using something called the directed acyclic graph representation of the circuit, where we have this is qubit 2, qubit 1, and as this goes down, this is showing what order the gates are happening to in a graph theoretic way. So you can see the 2-qubit gates come in and 2-qubit gates come out, and what order they can be manipulated in. So then you can start using like network X and other kinds of graph theoretic computer science problems to help you with this problem. Now, this isn't really super complicated in this problem. I just told it to go in and find the C0s, and if they meet the right conditions, apply the template to them. But this is kind of how you really can think about circuits at a low level and how you can start manipulating them in ways that can maybe give you an advantage. And so what I'm going to do is do all these, I call them bespoke translation passes, and I'm going to get my final circuit out. And I look at it and I see I don't have any C naughts in it, and so I'm happy. So it's all RZXs, and so I've essentially like gotten to the point where I'm ready to put this on a quantum computer. Okay, all right, I think we're doing well on time. Questions so far? All right. Okay, so now we actually build the experiments, and so we're like, well, what are we going to do? What are the parameters we're gonna sweep? How are we going to do this in a systematic way? Well, what we're going to do is rewrite our Pauli terms in terms of the physical coefficients of the Kitaev chain, and we're going to rewrite them as these parameters m, x, y, or lowercase m, x, y, z, corresponding to these interactions. And so this is exactly equivalent to the Jordan-Wigner decomposition we got out earlier, and the circuits that I was getting out earlier, we were getting out earlier as well. So I just have to kind of, set these things equal to what they're supposed to correspond to. So we got the question here. Yeah, my time set is 5 and my DT set is 0.7, so 7 Trotter steps. It's rounded, and I'm going to take each one of those and append it. So essentially, this step is just appending each one of those Trotter units, I call them, into, or each one of those Trotter steps for 7 Trotter steps. So that's all there is. And then we establish our range. So up at the top, you can see we're doing an M sweep experiment, and I want to set the parameters. So I'm going to set the X, the Z, and the C for this one. But there's a lot of and the U. There's a lot of other ones where I'm setting other parameters and scanning other ones. I'll show you an example of those as well. But this is for the main thing I wanted to show. So basically, I'm just going to show you this. We're doing a Y range of 16 circuits, an M range of 16 circuits, and this W range. What is omega range? Why do I care about that? Of 51 circuits. And so I'm just going to go ahead and do that and start building this so I can talk about it, because this is the method that goes through each one of these and builds it. Basically, I told you this is a great technique for finding eigenvalues of the Hamiltonian, but nothing comes for free. It turns out it's a spectroscopic method, so you have to sweep the omega. You can't see the response without sweeping over a bunch of omega and seeing when it's off resonant and when it's on resonant. So you pay for it in a number of circuits you're doing. Number of circuits you're doing right now is a lot less expensive for noisy quantum hardware than is the depth of circuit, which could quickly makes it impossible. This is possible, but it makes it so that there's a lot of circuits. So for example, right now you can see how long it took. I'm only actually doing one Y point. I'm doing the M sweep and all of the omegas. So there's 16 M's, there's 51 omegas. This is 816 circuits. So actually the bandwidth of these circuits gets really, really large. And this is not, clearly not the most efficient way of doing this, but this is what it took. So I've got a job of 816 circuits, but that's for a single Y, and I need 16 of those Ys. So just to show you some things, I was going to look at these circuits, but I'm just going to consider the last one instead of all 816 of them. So I can basically, what I'm doing here is I'm taking the circuits and I'm adding the calibration. So I'm doing the pulse scaling. This RZX calibration builder, it's inside Qiskit. It knows how to scale these pulses in the right way so that I don't accumulate error and I don't cause any problems when I'm trying to do less cross resonance. And then I can ask myself some questions by, let's see, I'm scheduling it here. All right, what I want to do is count the operations. So just to kind of give you an idea, I can look at so the scaled one is the top one. I can look at how many RZX operations I have on, and that's 84. And I'm pretty sure all those RZXs are better than a C naught. And I know off the top of my head from experience that RZXs are easier to do than C naughts, and I know 84 C naughts is probably doable anyway. I look at the next one and I see 168 C naughts, and I'm like, that's a lot of C naughts. That probably won't work, maybe, just maybe. But like you kind of get the intuition for what you can do on the hardware and what you can't. And so without doing this effort, I'm kind of in the second situation where I probably wouldn't be able to get the results that I wanted. But I clearly am in the situation where I can get the results I want in the scaled pulse situation. And I can kind of like do this by estimating the fidelity. Just by calculating from the C naught error that was taken from the backend, I estimate that the scaled one has an 88% fidelity, which is pretty high, and I feel good about that. Whereas if I look at the digital circuit, I see my fidelity is 38%, and I don't feel good about that. So if I wasn't smart about it, I probably wouldn't be able to run this. In fact, I wouldn't have even run this because it's such a low expected fidelity. And I should say that like this is not a proper fidelity. This is like my estimate to the upper bound fidelity where I just consider the 2-qubit errors. And it's really just a sanity check to see if it's worth even trying to do this on like real hardware. So that's just kind of how I roll. We have better, scoring techniques as well that are coming out in Qiskit soon that we've started using internally that you'll see. So if I look at how long these circuits are, I can see the scaled one is 92,000 units of DT roughly, and the digital one is just under 300,000. So this is like less than a third benefit you get from scaling just in decoherence alone. And if you're trying to push the limit of NISQ era hardware, these are things you want to consider. Also, I should maybe at this point highlight that Olivia and I are working to try and make it easier for people like any researcher who doesn't know about cross-resonance pulses or dynamical decoupling or polytrolling or whatever, make it easier for you, the researcher, to interact with by putting out some libraries, some open source libraries that will interface and put all the hardware knowledge in where it needs to be, because Qiskit is nominally hardware agnostic. So it doesn't belong in Qiskit. Yeah, this isn't really going to work because of the bug I showed you earlier. So what I'm going to do here is I told you that was just for a single Y value. I have 16 Y values, so I'm going to get their jobs. And using the internet, I'm going to retrieve all this data from the cloud right now. So what we're doing is I'm pulling all this 816 times 16 jobs worth of data, which does take a while, from the IBM cloud or IBM Quantum services to my laptop, so I can analyze it on the fly and show you what the results are. So we have a moment to talk while that happens. So this might be a good point to ask if there's any questions. Yes. That's a great question. So the question was if these tools are publicly online and available in a repo. The answer is hopefully this week. Any other questions? Yes. The timescale for writing the code or running? Running the code, okay. My answer for you is all of these jobs right here, I could do that in a day. Roughly, but I did a lot of things stupidly. So I had to, a lot of the time was the transpilation of going through all the circuits and turning them into new circuits, which I probably didn't do the best way. So each one of these jobs, for example, took me 15 minutes or so, just classically transpile. And then I would throw it in the, I would send it to the backend, and getting the results back would typically be not very long, within an hour. So just to give you a flavor, this is 16 of jobs. So that's like, roughly a day. But I got really good at just running through these. And what I do is I'd send the job and then I just restart the next one and restart and restart and restart. So I could send a bunch of them, get the results back, and get this. So this is 16 jobs. I ran over 200 jobs. So this was actually took a long time to experimentally run because there are so many parameters to verify or to change and so many things to verify. And what happened? I think I lost the Zoom. Did we lose the Zoom? This is still going on. Yeah, my Zoom just crashed. Okay, then. All right, well, this is still happening, so. Oh, I'm live. Wait, can you see my screen now? All right, sorry, I'm confused. I see me, but I don't see my screen. Should I just like restart it or something? Oh, no, I'm back. Okay. Yeah, I think so. All right, well, this is taking longer than usual. Any other questions? All right, well, let's just keep going on because I can describe some things in a later slide. Let's get rid of this. That. Okay, and then there's another relatively timely thing where I take all that data and I slice it up as a function of omega, and then a function of m, and then a function of y. One thing I'm going to say here, because I didn't think I had enough time, is that I put a lot of metadata. You know, you can see the notes I took on the previous slide, where I could talk about what sweep I did. But it's also a good idea to not rely on the fact that you like left notes in a Jupyter notebook. So we put metadata with all of the jobs that can then be extracted, and we can take that metadata and simulate what we expect exactly using Qiskit-Opflow. So we can actually simulate those operators exactly. We could trotterize them and simulate them. And so we have, you know, something, a basis for comparison for what data we get back versus the data we sent in. So what I wanted to kind of discuss, I guess, here is what is the data that we're expecting, and we can barely see it. Okay, well, I will try to describe this. So basically what's happening in each one of these runs, which each one of these scans I would call the omega scan, which is the 51 values of omega. It's going to go over those 51 values of omega, and the algorithm works such that whenever the omega becomes on resonant with the simulation register, it's going to have a reaction to it. And so you'll see a dip in the probability of it being 0. Or I mean, the 1 is the probability. This is written as the Z operator. So it's starting out as the value 1 is the Z value, and as it goes across, you can see it experiences a slight dip for the value C equals 0.1. So that's like a weak coupling. There is a small response to our system around the correct eigenvalue, which is about 0.8 in this case. And so you can see a dotted line maybe here that corresponds to the eigenvalue. You can see the response. So you could do a little bit stronger coupling. And then the blue, we have C equals 0.3, which is actually what we used for all the data, where you see a nice big signal right at the value that you want, right at the value you know. So there's a lot of kind of empirical testing to this algorithm that we found. That's why our supplemental material is so long. But you can see from testing this, we see, you know, we kind of get the right result. We get a more coupling, so we see a spectroscopic result. And then if you've ever done tunneling spectroscopy like me, if you make a tunnel that's not big enough, what happens is your probe will bleed into your system, and so you'll get an effect. You'll get perturbed too much by your system. And in case C equals 0.5, which is this blue dot down here, this blue line, you have pushed the curve away from the eigenvalue, and so you're not measuring anymore. So it takes a little bit of tweaking to perturb the system in the right way, where you have a large enough signal, but you're also not probing. You have a large enough signal, but you're not interfering with the system. So it's kind of a, you know, you have to kind of calibrate this on the actual hardware and see what happens. So what we see in the next plot is we see omega. So this is the same x-axis as on the left, but the y-axis is Z, and this is a color map of the expectation value Z. This is little z on the left. And what you can see is you can see these dips go, and you can tune these as a function of Z in your Hamiltonian. So you can see this actual technique responding to the actual changes in the simulated value of your Hamiltonian, where the eigenvalues would kind of trace out something that looked like that. So that's how we analyze it, and that's basically what I'm going to go through for the next couple slides. So I see that the code has caught up with me. So basically what we're going to do is we have these codes to look at the derivatives and do some finding the zeros over some smoothed parameter set, and then I can just get the data out. And it is almost exactly like a different scan we published in the paper that's in the supplement. And I just pulled that data and analyzed for you live from the quantum experiment I ran before. So in the end, I have kind of gone through an entire experiment, show you how you do quantum simulation using this new spectroscopic algorithm on an IBM backend, pull the data in front of you live, do it over this piece of technology, and show you how it compares to a result from a figure in our paper. And with that, I'd be happy to take any questions. Yeah. Oh. Yeah. So the question is, if you send a job that is exactly identical to another job, I think no jobs are exactly alike, so it'll just run it. I mean, I don't even think there's quite a possibility the simulator would do that because because that's such a common thing. The simulator might do it, but the real hardware would not do that. So the question is if there's a C0 and a Hadamard and a C0, that's the circuit I use to test everything out too. With the simulator, maybe we'll cache that, but the hardware will not. Because these are also like tests we use to measure fidelity. You want to have like for example, if you're looking at how stable a system is, this is exactly something you would prepare and measure all the time. So you wouldn't want to just cache that result and pull it out all the time, or you would naively think that your system was always calibrated the exact same amount. Okay, so the question is, are Qiskit jobs public knowledge? And the answer is no. Well, let me take that. So the normal way you submit jobs is no, it's private, it's only to you. Only you and your API token have it. So it's essentially no one else. And so we recognize that this is not an easy way of sharing things. So we have a new module, which is kind of in beta testing called Qiskit Experiments. And there you can share jobs across a provider, which is kind of like, basically I can see everyone running stuff internally via Qiskit Experiments, but I can't see it via the way of running normal jobs. And so that makes it easier to share. That makes it easier for, the idea is to calibrate and make it easier to share data, because that's one of the things that's a little difficult right now is I can't just say, here's my API, I can't put my API key on GitHub and ask people just verify what I did is right by downloading my data and, comparing it. But I had to just, export the data in the way that's in the notebooks I had. But yeah, we're trying to make that easier in the future. Thanks. Yes. Right. The question is, if using the transpiler, I did a bunch of stuff, and is it easy? Is there extra stuff that you might want to use? And the answer, I think, is probably. Usually, when you're when you're doing a research project and you're trying to really squeeze performance out, I would say yes, probably. And that is one of the reasons why we're making these tools that I was talking about. We're going to open source this week. Those are essentially transpiler steps that are done in the right order, like in the same order I would do them. And it kind of takes like empirical back and forth, but we're trying to encode that knowledge into this open source repo so that you would know exactly how we did it. And so, I can tell you basically what I would do, and we'll have a paper that comes out about it as well. The first thing you want to do is map your circuit to, you can map your circuit to the backend. There's something called a VF2 graph isomorphism algorithm that is very fast. We have a scored version of that will give you the best layout you possibly could get. Then when you're moving that to the, you want to transpile that, break that down into, break that out on the single qubit gates. It's going to always optimize over like 2 Hadamards will go away, 2 C0s will go away. That's kind of the easy steps. And then it'll map your circuit to that layout based on the minimum number of swaps. That typically is pretty good in the transpiler now if you go to the higher optimization levels, but it's still stochastic, so you won't always get the same thing. So sometimes you might want to seed it, for example, just so you can repeat what you did before. I think that's always a good idea. Then a lot of times you might want to add some error mitigation, such as dynamical decoupling or polytwirling. Right now we don't have zero noise extrapolation, but would be interesting. It's kind of difficult to get that working in a general way. A lot of them are very canned. But in that, like this pulse scaling, if you're doing angles less than pi over 2, like it always works. If you're doing like measurement error mitigation is something we can add to the end, that always works. That's always a good idea. The VF2 layout and scoring that always works. You always get the best. Almost always it's still stochastic, but I would go through those levels, and then if you can apply other things like pulse scaling to them, or you had there was something about your algorithm that would allow you to, be smart about the way you synthesize. So I asked Sabri about, is there purification you can do of the end state? Is there a symmetry that needs to be respected? You can toss some of that data out, for example, and then you get the results you want. So that's kind of a general step, but there's always more you can kind of add. So that's what I think, but we'll have this out soon enough, so hopefully you can take advantage of it. And it'll probably be off during this workshop, so I'll ask that to get sent to you.
Awesome. Do we have any other questions?
Yeah. Oh, that's a great question. So the question is about this. This is a nice. Thank you. That's a nice simulation example. Is there other things in mind? And the answer is yes. I have lots of different projects in mind. I think one of the reasons I got into I like quantum simulation because I study condensed matter physics, and so toy model Hamiltonians and understanding material systems is of personal interest to me. And I love the fact I can try and play around with this with quantum computers. There are like a lot of different simulation techniques. Even within kind of I would say even within the unitary kind of evolution framework, there's a lot of different things you can do, such as, the way you coherently control things, what you're measuring, what are the properties you're looking for. You're looking for an expectation value of the system you're encoding, or you're looking for the eigenvalues of a Hamiltonian. So we're trying out all kinds of different things. And where I really want to help, where our kind of mission exists is, how can I make it easier for you to try out your ideas? And I want you to try them on real hardware and see how it works. So I guess I don't have any great answer for you right now because I'm still working on these projects, but if you have an idea, I want to see how I could, I want to see how you could use Qiskit to get that done on our systems.
Okay. Thank you very much, Nick. Please join me again in thanking Nick for this wonderful lecture.
Thank you.
Okay, now we are all heading towards Rossade to the Buchanan Club for the poster session and dinner. So I'll see you all there.
Thanks. Yeah, thanks a lot.